compute networks. This is the main element of today's talk. So then, lastly, I would like to show you what is the role of networks, to build on digital infrastructure. So in the introduction, the next slide. So you know very well, data is important. So without data, we cannot use AI techniques. So in this regard, currently there are lots of opportunities to link together with the data and AI. So in this context, the one of the important reason to use data is to create a kind of actionable knowledge. So, to do that, we are considering connected intelligence. The network's role is to provide connectivity, very well. So then the lots of important thing is how we create an intelligent ecosystem. So there are lots of opportunities to consider this kind of environment. Next slide. So firstly, from the IoT perspectives, we know very well various kind of sensors are very important. Individual sensors are sources of data. And then recently, rather than just considering connectivity issues to the sensors, we are also considering how we collect data and how we analyze data. So in this context, rather than just considering a kind of intelligent systems, how we correctly model real environments with the digital twins. So actually inside the digital twin, there are lots of models, including AI. So that is the reason why I would like to talk about AI-powered digital twins. So more importantly, when we consider this kind of whole infrastructures, most important element is how we consider data-centric approach. It means that we need to fundamentally change the paradigm, and then we need to build really innovative ways for building up certain network infrastructure. So in this context, if we consider to support a kind of small pieces of our network infrastructures, so then these kind of things start from the system level, and then we consider systems with kind of a large-scale networking environment. But recently, rather than just considering system levels, we need to think about ecosystem. Lots of different elements need to be considered. So in this context, more importantly, how we consider a kind of a federated environment with kind of different stakeholders together. So in this context, lesson 3, I have mainly focused on how we successfully build up data-centric ecosystem. This is not just the networking issues, although we are talking about communications and AI perspectives. Firstly, we should fundamentally understand why we are talking about data and AI. So in this context, there are lots of different ways to consider to develop relevant technical solutions. So most importantly, instead of just considering just a small scope of the various kind of narrowed elements, now we need to think about how we consider to build a new infrastructure as an ecosystem. So in this context, to consider this kind of successful story, I would like to start to introduce composability issues. We know very well scalability problems. So in this context, even though we consider certain particular solutions for digital twins, if we cannot provide a scalable solution, it's not really a successful way. So in this context, next slide, we need to think about what are the useful tools to consider this kind of infrastructure. You know very well, we started a kind of a centralized cloud. However, recently, lots of mobile cloud, mobile edge cloud environment, even in the mobile device, lots of computing powers. So we don't really need to rely on centralized server. It means that we should consider so many number of different level of the cloud computing environment and the computing powers. We should collaborate together. It means that we need to fundamentally change the concept of designing of our networking solutions. Next slide. So in this context, when we consider IoT applications, we already considered some similar approaches with the microservice concepts. So there are small pieces of services instead of monolithic ways. We can interconnect and then create lots of different services together. So in this context, when we consider digital twins in order to represent our real environment, we also need to think about a similar ways. Next slide. For example, in the here, Gartner. So this idea were successfully implemented. So the title was Composable Business Applications. Even here, we are talking about business application aspect. Very important thing is it's not really a new solution or new concepts from the microservice, various kind of different service concepts. We already successfully covered this kind of ideas, but we need to know what are real challenges in order to consider this kind of composable solutions. In the next slide, you can see this kind of ideas. For example, in order to consider digital twins, we consider lots of different entities, certain particular informations in the real environment. How we successfully represent this kind of individual entities with the data in a cyberspace. So in this context, we borrowed the concept of digital twins. When we consider this kind of digital twins, there are lots of different ways, and so many number of data are continuously generating. How we successfully adapt and then also predict, and this kind of very dynamic environment, we really need lots of new ways to immediately adjusting various kind of dynamic and real situations. So in this context, if you go to the next slide, so next slide, there is very fundamental diagrams here. So you know very well Lego blocks. So firstly, if we consider certain particular small pieces of entities to represent in cyberspace, we can just start to create an atomic digital twins. And then we can assemble them, and then we can create lots of useful solutions depending on different purposes. So in this context, this is a very, very useful tools. Even some normal users, it's not engineers, just a kind of a template. So we can easily create this kind of twins and then interconnect them. So that kind of approach is really innovative. And the next slide, like here, for example, if we wanted to consider this kind of ideas, instead of only considering to develop lots of different pieces of digital twins, we need an architecture. This is a composable architecture, like API. We need to specify relevant interface and then successfully compose lots of different elements. So to do that, next slide. So you can see various kind of important things. We definitely consider to identify lots of interfaces. We also need to clearly identify what are the interface for assembling points. So in this context, we should develop or standard. So that is very, very important things. You can develop your own digital twin. Some others also can develop digital twins. If we have a common language, we can easily assemble and we can create lots of useful solutions. So by using this kind of innovative ways, next slide. Now I would like to talk about AI native fused networks. Next slide. Firstly, what is the vision? You know very well conventional networks. We have a concentrate on just a client server model. We simply transport our data to the destination, to the server. We can download the data. However, in the future, in the AI era, we should fundamentally change the concept of networks. We need to best utilize AI techniques. In this regard, fused networks should be a distributed, virtual, and tailored ICT service factory. Service factory network can help to create unlimited number of services. Next slide. In this regard, you don't need to own your own network infrastructure. We, some case, also share our networking functions as a platform. We know very well, we successfully created the platforms. We shared lots of useful functions together, and we can easily support various kind of vertical applications like IoT platforms. Very similarly, network should be a platform. Lots of networking functions should be shared, and then we can consider to continuously create lots of useful functions together. So in this context, let me emphasize the role of the networks as a platform. Yes. So in this regard, if we consider platform, so then this kind of platform should cover so many number of fundamental concepts. So for example, from the beginning, I mentioned various kind of different cloud environment, centralized and decentralized, distributed, etc. Computing powers are very powerful, but just only considering computing is not sufficient. We need to think about various kind of AI solutions. We also need to think about very trustable execution environment. In that case, what are the real purposes? As I already indicated, fused network should be a factory to immediately create lots of services. It means that we can find suitable tools and then easily combine various kind of useful elements and then continuously generate lots of services. These kind of services should be customized to the user. If we do not consider individual users' requirement, it might be really very a kind of no real values, no business models. In this regard, in the future, we should always think about how we successfully meet the user's demand, continuously supporting lots of adaptable solutions from so many number of networking functions. Next slide. So in this context, there are many different ways to consider to building up certain particular networks. We have so many number of contributors. Users are not just simple users. Users can be a create. Users can be also produce. Developers also can be a user. Individual developers can create their own digital twins and then sell their products to so many number of users. The role of networks is to successfully identify and finding this kind of useful solutions and then create many applications. So then issue is how we recognize this kind of heterogeneous types of resources and how we combine them. There are lots of agent roles, and then how we successfully create so many number of services together. So in this context here, I have identified many interesting consideration points, users' perspectives, various kind of different resource perspectives, operational aspects, and then quite a reliable infrastructural viewpoint. Next slide. In this regard, now I am talking about some relational aspect, digital twins and AI. Why we are using AI? Mostly, as you can see here, we always think about a kind of optimizations and predictive maintenance, sort of analytics ways. Whenever we design digital twins, inside the twin models, there are lots of techniques, lots of interactive ways for considering digital twins. That's the reason why we always need to think about AI-powered digital twins. Next slide. In that case, like this kind of manner, we can consider so many different pieces of elements, like Lego blocks. Some case cloud, AI engine, very powerful computing powers, and then lots of data. But some cases we know we should support real-time decision making. So in this context, there embed the AI on the device. These kind of solutions are very important, but intermediately, we always need to think about how we successfully support various kind of agent functions to use centralized cloud and the device together. So in this context, there are lots of things should be well coordinated. It's not just a single networking element. It's not just a single system. Physically, geographically separated element, but important thing is how we successfully operate this kind of solutions. So in this context, in the next slide, very important thing is now we need to support co-creation. It means that many different users can create their own twins or certain particular functions. How we successfully generating this kind of individual small pieces element as an atomic digital twins. And then from the concept of a composable architecture, we should successfully compose them and then building up large-scale federated digital twins with the AI capabilities. Actually, I haven't well emphasized the networking roles. However, these kind of solutions fundamentally require networks because networks become a kind of a factory to successfully assemble this kind of small pieces of elements. Next slide. So in this context, now I believe we know the importance of digital twins, so the particular relational aspect with the AI techniques, AI-powered or AI-native fused networks. Now I am talking about a little broad concepts regarding digital infrastructure. So here, this is not my idea, but currently lots of ongoing activities to build up certain particular continuum. From the cloud perspectives, cloud edge continuum, that kind of point of view. But similarly, we know very well lots of different facilities or systems are required to successfully build up a virtual environment. Some cases we are talking about this one as a digital continuum. Inside here, we can successfully identify so many number of important elements. Actually, network is just one element. Apart from networks, sensors, some security solutions, AI models, data, many computing powers, etc. But issue is how we work together. that is the fundamentally important keyword, or continuous dynamic workflow. So you know very well, recently, there's no particular barriers between networks and cloud, something like this. We are talking about computing network conversion, something like this. Very similarly, huge infrastructure, I emphasize data ecosystems. These kind of ecosystems consist of so many elements. These kind of elements need to be work together. In the next slide, in this context, individual element should be characterized as a twins. So here indicated individual twins, and then each twin has different characteristics. And the next slide, like here, we can also identify certain different roles regarding real-time digital twins. Without having concrete solutions to successfully build up a composable environment, these kind of solutions cannot be any synergetic ways. So we should well think about, although individual pieces of solutions are very small, not so powerful. However, if we well integrate them, then we can successfully support very powerful solutions. In this context, the next slide, we need to think about various kind of different ways for considering this kind of digital infrastructure. AI for digital infrastructure, or some case, digital infrastructures should successfully support so many number of AI applications. So in this context, there are lots of different roles. And then next slide, I would like to clearly emphasize here the roles of AI native fused networks. As a conclusion, AI data is very important. These kind of AI solutions can be successfully utilized to create various kind of small pieces of intelligent logics and entities. That kind of things are digital twins. Then by using composable digital twins concepts, fused network should support a large-scale infrastructure. So then eventually, we can successfully develop digital infrastructure here. Next slide. So as a conclusion, I have emphasized one particular things of how we successfully utilize the composable concepts, a kind of a decentralized infrastructure. But in order to successfully support this kind of key ideas, very fundamentally, we need to think about how we work together. Even standardization viewpoint, many different standardization bodies need to collaborate, and then we can successfully identify lots of important elements and then build a full set of the whole functions. So we need to fundamentally also think about what is the different roles, what is the really different solutions, instead of just concentrating on very important transportation aspects. Networks should well interconnect so many number of useful elements to successfully assemble them and then integrate them and work together. So that's the conclusion. Thank you.
Yeah. We'll take one question, please.
Professor, thank you for the presentation. You mentioned about the 6G, also the digital twin, almost real time. I'd like to highlight the real time. It is very complex infrastructure. Doing this capability with the real time, less than sometimes the millisecond levels, what kind of infrastructure is necessary? Can you share with your opinion?
Yeah, most of the real-time features, we should rely on certain particular technical breakthrough, for example, 6G. So lots of new wireless techniques to support large bandwidth, etc. So without having this kind of concrete solutions, it's not really possible to successfully implement this kind of high, quite dense and high-speed infrastructure. But the issue is, although we have this kind of useful tools, if we cannot successfully create certain particular ways or utilize this kind of solutions in terms of architectural viewpoint, the various kind of innovative approaches. So without this kind of things, it's really not possible to successfully implement. So in this regard, we should well identify what are feasible and quite available technical solutions at this stage, and then how we make a synergy with the various kind of innovative solutions like a composable architecture, so many different ways. Then we can probably successfully create various kind of new solutions. But the issue is, although we are talking about very high-speed networking environment, fundamentally we also need to think about to use existing networking infrastructure and computing environment together. So then, evolutionary viewpoint, we need to well consider how we best utilize best kind of available networking resources. So I think there are many different ways considering some backward compatibility, but more importantly, we also need to think about innovative ways for futuristic solutions with the AI techniques. Thank you.
Thank you very much, Professor Lee, and thank you for the question. We will move. Maybe we can move on to the next one. Sorry, we'll take it during. Professor Lee is catchable during the break. We will catch him. We will move on to next presentation. Can I please request Jakob, please? Yeah.
How much time do I have now? 10 minutes. I try to be quick so that the other speakers have also time to break. Okay. Okay, can you hear me well? Yeah, hey, good morning, everybody. I'm Jakob Hoydis from NVIDIA Research. I want to share with you some of the things we're working on. And one of the topics I'm particularly interested in is actually tools for the creation of digital twins for communications. And I share some of these with some results and ideas and things and areas where we see a lot of potential using these tools and techniques. Okay, let me start by making an analogy between what's happening in the world of kind of processor design and how communication networks could evolve towards 6G. So as most of you know, Moore's law has essentially come to an end, and one of the ways that we can keep scaling efficiency and performance is by moving away from general purpose processors to domain-specific hardware accelerators, such as GPUs. And now if you think, we can now make the analogy by assuming that 5G and Wi-Fi essentially have basically been designed as general purpose wireless bit pipes. And one way actually to increase the performance of these networks is to let them adapt in an automated manner to specific radio environments and also applications. So I think that's one of the areas we have never kind of looked into, and that's where you might expect to see a lot of potential. Now, if you want to achieve a network that can adapt to its environment in an automated manner, you need, I think, three components. You need to have the RAN as much software defined as possible, because otherwise you cannot reconfigure anything. If everything is put into silicon, you can't adapt it on the fly. You need machine learning so that you can actually have networks adapt automatically. And lastly, you need digital twins to actually speed up the training, to train things fast in real time, and also to have a playground for training and experimenting without, causing any disruption to live networks. And I will mainly speak about the machine learning and the digital twin part here. What we're trying to do at NVIDIA is kind of to enable the ecosystem to do research on digital twins. And for this reason, we open source quite a lot of the things that we are doing. These are our internal tools. Maybe some of you know these. So we have an internal tool that's available to everybody as an open source project. It's called Shona. It's a differentiable link level simulator where you can essentially construct link level simulations in the same way as you would construct a neural network. And you have an ML, rather than have a dense layer and a convolutional layer, you have a coding layer and a channel layer. And then you can compute gradients with respect to any outputs of any blocks in the way you want it. And recently I've released a very specific tool for the computation of radio maps. So radio maps, an example would be a coverage map, but you could also visualize delay spread on a map or angular spread maps. And the nice thing about these instant radio maps is that you can compute them in real time, and I think that answers one of the questions we had there. So I think most people believe that computing a coverage map takes a minute or maybe hours, but you can actually do it in real time with up to 100 coverage maps per second. So now I think with the right technology, you can actually make radio propagation prediction in real time and take dynamic scenes into account. And lastly, we have also a system level simulator that actually runs at operator scale. So you can really, it's called the Aerial Omniverse Digital Twin. So it's based on a commercial, essentially software defined code base running the full layer 1, the full layer 2 channels are modeled based on ray tracing. You have full mobility support. You can extract data from wherever you want it, try machine learning model in it. That's if you're interested in this, have a look at the NVIDIA 6G developer program. So that's also available actually for everyone. Okay, good. Now come to the core of my talk. So I would say that we are lucky because creating digital twins has never been easier. So there are many tools that you can use to construct scene geometries or meshes. So we have LiDAR. Now it's even in most phones, you have a LiDAR sensor. So you can get these point cloud and construct meshes from it. There's been tremendous progress in computer rendering based on so-called neural radiance fields. You essentially take a couple of photographs, you train a neural radiance field, and you can actually construct a surface from it. So it's in the top right corner. You see a video. It's the NVIDIA headquarters that was reconstructed based on videos taken from a drone. But if you want to have something maybe a bit less realistic, you can just resort to open source tools. I think OpenStreetMap is fantastic. You can essentially get at least coarse geometry from any point in the world, import this into open source tools like Blender, and use this. Now the issue is that while it's easy to get a scene geometry, if you want to do a radio kind of wave propagation prediction, you also need to know the materials. Is this wall, it looks like wood, but maybe I don't know what's behind it. Most likely it's metal behind it. I have no clue what it is. And that's something you don't get from any tool in the world right now. And that's an issue. So you can so the scene geometry, I would say that part is more or less solved, but you also need to kind of learn something about the materials and electromagnetic properties of the environment. Now, one way of actually dealing with this problem is by using something that's called differentiable ray tracer. And I would just explain what I mean by the inverse radio wave propagation problem. So imagine you have something that looks like what you have on the right-hand side. You have a coverage map, maybe obtained from measurements, drive tests. You do channel measurements. You have a set of geolocalized channel impulse responses, and you have a coarse model of your environment. And now the question is, how would I need to configure the materials of my scene, the antenna arrays, the patterns, the precise locations of these radio devices, such that when I do ray tracing on the model on the left, I can reproduce what I've actually measured on the right. Okay. And now, in order to tackle such a problem and to research on it, we have developed a differentiable ray tracer that allows you to do precisely this. So what it does is it kind of ties into our Shona link level simulator. So you can use now ray trace channels instead of channel models. But because everything is differentiable, you can ask questions like, how would the channel impulse response at a particular point changes if this wall becomes more conductive? Or if I change my antenna pattern a tiny bit, what is the impact on the channel estimation quality? And this is fully differentiable, meaning you can actually do gradient descent on your radio characteristics of your environment. So actually you can think about it as, rather than having a neural network, you have a neural environment, and you can train environments that they allow you to reproduce your measurements and calibrate these things. You can also do then all kinds of gradient-based optimization of system parameters. For example, I think that many people are interested in reconfigurable intelligent surfaces. You could do gradient descent on the spatial modulation coefficients of such things and say, okay, how do we optimize this? You can optimize antenna placements on very large arrays. Essentially, you can compute gradients with respect to the positions of objects, even with respect to positions of vertices in your mesh. So it's all things you can learn. And you can also easily embed neural networks anywhere in this process, rather than saying I'm actually training a neural network to, rather than saying I'm calibrating directly electromagnetic properties. You can say I have a neural network that will predict what are the properties of any point in my environment. And I have an example that makes this much clearer later on. Good. So that's software. You can download it, open source, and play around with it. Many examples are available. I'll just give you, I give you one example what I mean, actually, what precisely differentiable ray tracer does. So this is here a textbook example of a specular reflection. So you have an incoming wave EI that propagates in vacuum. It hits an infinitely large object. And typically you describe such an object by a complex relative permittivity. It has two real valued parameters, real value, relative permittivity and conductivity. And now these two parameters will actually determine how the reflected fields look like. And I don't go into the equations here, but there's an expression that tells you how this looks like. And the only thing that you actually need to retain from this is, so there's a mathematical function that tells you this, how the reflected field depends on these two coefficients, epsilon, r, and sigma. And if you have a differentiable ray tracer, it will compute you the derivative of your electromagnetic field with respect to these parameters. And you can change these things together and make it super complex, okay? Just an example. Another example of something you can do, for example, you can do gradients with respect of the orientation of an antenna. That's a problem people have looked at in, I think, for the last 30 years, called antenna tilting and so on. Now you can solve it with gradient descent. So for example, here in the top left corner, you see an antenna array. We have defined some area behind this Arc de Triomphe in Paris, where we would like to improve coverage. And then you do gradient descent to improve kind of the amount of energy that reaches this area. I'm not saying that this is how it should be solved, it's just to visualize you the kind of things you can do, okay? Good, and now I want to show you an example that this actually works also in practice with measured data. So we have carried out together with the Institute of Telecommunications at the University of Stuttgart. So this is Professor Tenbring's group. They have developed a distributed channel sounder called Dicasus, and they've published a lot of really good measurements that are all open source. You can all download them on their website. And here we carry out a measurement campaign in the institute. So you see this corridor, and we've placed essentially 32 antenna panel on the left and on the right side of this corridor. And then there's this kind of a Hoover robot that has kind of a receiver. And this position of this robot is tracked to millimeter accuracy using a tachymeter. And then this thing drives around and gathers channel state information. And then you end up with a database of geolocalized channel measurements. So here it was like 10,000 measurement positions, 50 megahertz of bandwidth, 3.4 gigahertz of carrier frequency. And that was kind of our data set. And then we wanted to simply figure out how well can ray tracing reproduce these things, and actually can we calibrate the material properties of the scene to match our measurements as closely as possible. Now, one issue when you start by doing calibration is the granularity at which you want to discretize the scene. What I mean by this, so imagine you have this large wall here in this room on the left side. You could either say, this is one object, it's made of the same material. Or you could say, I discretize this into, I don't know, a few thousand tiles and assign a different property to each of them. Okay, the problem with this is that if you take this kind of individual or discretization, this cannot be automated. You need to do this manually, and it doesn't scale. Imagine you do this on a city scale, you end up with billions of parameters, and there's no way you can actually learn this from measurement and calibrate this. It's a bit like the same problem you have when you have super large neural networks and actually sparse measurements. You will totally overfit to your measurements. It's the same issue. And so for this reason, we tried something that you call neural scene materials, where you don't discretize your scene at all, but you rather have a neural network that gets as input the position of where essentially a ray hits an object. This is then positionally encoded, so you lift it into a higher space, and this is fed into a small neural network. And this neural network will output some of the material parameters. So I just put here these two parameters that we've learned about earlier, permittivity and conductivity, but it could actually output parameterizations of scattering patterns, antenna patterns, and so on. Okay, and the nice thing with such an approach is that you have essentially a single neural network that encodes the entire electromagnetic properties of a scene. This scales to essentially arbitrarily large scene, is super easy to implement and train, and you can kind of control in a, let's say, in almost a soft manner, by the size of the positional encoding, you can control the granularity at which the material properties are allowed to vary across space. Okay. And now I just have a couple of examples showing how this actually works and perform compared to I would say, other state-of-the-art methods. So here you see the measurements of path loss in this corridor. So on the left side, you see this is this corridor of this institute. We just look at one transmitter. That's this red dot, and then you have this coverage map. These are the measurements, and now you see three different approaches of calibrating a scene. And the top row shows actually predicted path loss. The bottom row shows essentially the absolute error you make. And now each column corresponds to a different scheme. So the first column corresponds to what you get if you use the well-known, I think, ITU materials. So there's this list of 12 materials, plasterboard, concrete, and so on. And I just did my I used my expert knowledge, look a bit around in the institute and say, okay, this looks like this is plasterboard. This is, I just made the guess. And that's what you get when you make these assumptions. It's not wrong, but it's also not great. You make kind of quite some substantial errors. And the second row is when you say, okay, I take the ITU materials as a first initial guess, and then I start to optimize them using gradient descent. That helps a little bit, but doesn't really make a drastic change. But then you move to this kind of neural material representation. I think that really gives a dramatic improvement. You can see this here. So blue means essentially the error has increased quite a bit. And just to visualize what this means at one particular position, let's have a look at the cherry-picked channel impulse response at one position here. So this is how it looks like in measurements. This is what you would get from ray tracing prediction using the expert ITU materials. Now, this is what you get when you tune them a little bit. And this is what you get using kind of neural materials. And by the way, so we haven't used this is evaluated on positions that we haven't used for training. It's the same like when you train a neural network. If you have a training data set in your test set, so it would be easy with a neural network to overfit to the test set and get perfect results. So this is here, of course, test results. Now, the nice thing is you can also visualize this. So since we now have essentially neural networks that can tell us something about the environment at any point, for example, here I can visualize like a texture, the reflectivity of my environment. Black means it's almost transparent. White means it behaves a bit like metal. And just one thing where you can, maybe it stops this video now. Okay, so you can see that essentially this is the ceiling, and half of the ceiling seems kind of to be much more reflective than the other half. And for those of you who've paid attention to the images of the institute that I've shown, so you can see here, there's actually on half of the corridor, there's this metal, I don't know, cable holder, what it is. So it seems to match fairly well with what you expect. There's also this wall here, it's a big magnetic wall where students can attach the theses and stuff like this. So also in our kind of learned representation, you can see that, hold on. Yep. So anyway, so you can see this wall here, that's also far more reflective than the other things. So it kind of seems to make sense. And I don't know what it's really useful for, but at least it kind of, you can think about it. This is, you can now visualize an environment kind of through the lens of electromagnetic wave propagation at much lower frequencies than light, which might be nice. Okay. How much time do I have left? Essentially over or? Okay, good. I just wanted to make my point essentially now about digital twins. What can you do with it and why it's important? So I think the key message is that channel characteristics are really site-specific. And that means also that the way you design a communication system needs to be site-specific. For example, the algorithms that do channel estimation on the left, somewhere in the Alps, should be fundamentally different from what you do on the right in a city. So there's no reason why one solution fits everything approach works. And so what you ultimately want is that the algorithms you put into communication systems, they totally overfit to a specific environment because they only need to work in this environment and they don't need to generalize to anything else, right? And so we see digital twins actually as a way to allow machine learning models to overfit to a specific environment and then use this. And I think this is where we probably see the biggest gains of machine learning in communications. I just have an example here of a neural receiver. What is a neural receiver? It essentially, we look at the uplink, 5G, and it replaces channel estimation, equalization, and demapping. So that's done by a neural network. We've shown in kind of quite a number of papers that this approach really works. You achieve, I think, almost better than state-of-the-art performance with a complexity that you actually could implement in practice, which is nice. So I don't have time to go here through this, but essentially we always beat our kind of the best human baseline that you could possibly implement. We actually beat this with a neural receiver. And we did a demo at the Mobile World Congress where we then said, okay, now let's do some site-specific training. So this is a poor man's OpenStreetMap mesh from Mobile World Congress. Maybe some of you recognize this. We then essentially, generated a training data set out of this and trained a neural receiver for specifically so this area. And and we saw some gains. You gain 0.7 dB. In this example, that was tested then in a commercial ORAN setup and seems to be worthwhile. So just to finish, so I think that work on digital twins for communication requires quite a new set of tools. We work hard to make these tools available so that researchers can benefit from it. And lastly, I think that so far we really underestimate the potential of machine learning for layer 1, layer 2, and 3. And the main reason is that these things haven't been evaluated properly. And nobody has really tested this in real networks, or at least shared the results. And most researchers, they don't have the tools available to actually demonstrate that it works. Yeah, that's it from my side. Thanks.
Thank you very much, Jakob. In the interest of coffee, so sorry, I don't want to eat up your coffee. So please, can I invite Riccardo, please? And while he is coming, I want to tell you to please catch Jakob during the coffee. It's much more better. We had discussion with Jakob, and it's quite interesting. He has the two levels of simulators, link level and system level. The link level, he told us that you can use CPU to do it from a Google Colab. So let me just hand over and catch him during the tea break, please.
Just one quick announcement. One quick announcement for people who like to use the restroom. We have one right when you get out on the right side, or if you just go straight, you can also find another restroom. So just, yeah, thank you.
cannot share because somebody else is sharing. Yes, yes. Otherwise, I cannot share. Apparently, he's rejecting my. Oh no, now it's okay. Thank you. Let's see. Okay. Right. Okay. Good morning, everyone. Pleasure to be here. I've been introduced already. Just a few more notes. I'm working at the Huawei Munich Research Center, and I'm responsible for the research and standardization of network architecture currently towards 6G. And today with this talk, I'm going to present a vision on actually how recent advances in artificial intelligence, machine learning, as well as network technology may be shaping the future architecture that 6G may feature in the coming years. So as a starting point, I want just to recall the fact that actually artificial intelligence and machine learning already made their way into 5G network architecture. Many of you may be familiar with the introduction of the NWDF into the control plane of 5G architecture, thanks to its service-based interface, as well as in the management plane with the definition of the MDAF functions. So somehow AI is already working together with telecommunications. However, if we look at this picture here, that is a brilliant summary from the work that ITUR is doing, defining the framework for 6G towards IMT 2030, we can clearly see that there is the expectation that 6G system will be stretching beyond communication. And in this respect, in one of the dimensions that 6G will be, let's say, enhancing, the role of intelligence is clearly stretching farther compared to what we have today. In particular, we can see here that ubiquitous intelligence, I will try to put the pointer on. Okay. Ubiquitous intelligence is one of the overarching principles that should be on the foundation of 6G. And at the same time, one of the feature or new capability that the 6G shall have is the closer integration between AI and communication. So interestingly, this initial framework developed by ITUR is actually pretty well compliant with the 6G vision that was formulated and published by Huawei back in 2021, where actually the key concept that we were considering was to move from the previous concept of a communication network for connecting people and devices towards connecting intelligence as a new paradigm for next generation communication system. And in this respect, the envisioned role of AI and machine learning was twofold and still is twofold. On one hand, we have AI and machine learning for communication, okay? One possibility is to use AI actually to enable a vast variety of new services, ranging from immersive communication or ultramassive connectivity or extreme communication, for example, for industrial environment. Or also AI ML, as we have just seen in the previous presentation, as a tool to aid other functionality that 6G system shall feature, for instance, sensing. This is on one hand. On the other hand, the other important, let's say, perspective of AI was to have communication for AI for 6G system. In this respect, the idea was that the 6G network should actually constitute a kind of nervous system providing sensorial and communication capability able of interconnecting intelligent agents, okay, to enable intelligent application working on top. So in this respect, of course, all the features of 5G system should just be enabling the connectivity of intelligent agents. Now, you may have noticed already the recurrency of the term intelligent agent, which is actually the keyword, I would say, that is behind a bigger paradigm shift that we envision for 6G. Now, in this respect, the key point is that each element or entity that will be part of 6G system shall be considered as an intelligent agent. And this, of course, will start from the device side, okay? So in this respect, the baseline is that we should move away from the concept of device that we have experienced up until 5G, where we normally associate the concept of UE to smartphone or wearable devices or sensors, for instance. And going towards 6G devices will be far more complex and will be going towards a connected robot or service robot or intelligent task-oriented robots or even cyborg systems. And in this respect, the agent, in this case, the device also is considered an intelligent agent, will have the capability of interacting with the environment around itself and with other agents, thanks to a number of features provided by 6G system, sensing, reasoning, decision, and action, and also featuring new enhanced user interface powered by, for example, large language model and with a neural processing unit. So capability of computing exactly for executing AI tasks. Of course, the paradigm shift is not applying only to the device, but as I said, each object that we imagine part of the 6G system should be seen as a network agent, intelligent agent. And this applies also to the network part. In this respect, this picture is just showing that each object that we may imagine part of the network will have the ability of utilizing tools, memory, and planning object to then execute actions towards the infrastructure, towards the automation and the realization of the network functions as we expect to be moved away from compared to the current 5G, let's say, assumption. Another thing that I want to mention in this respect is that this idea that each each entity composing the 6G system will be a kind of intelligent agent is part of the vision that goes in the direction of native AI. That's the main difference compared to earlier generation. We will not have artificial intelligence as an add-on feature of the system, but it will be one of the founding principles of the architecture itself. And now this is probably the most important slide that I will show today, because it's actually summarizing what can all this be enabling. The idea is that this ability of having intelligent agents in the system will be, let's say, the starting point for a fully autonomous network that will be able to instantiate networks and services dynamically compared to what we have today. So the concept, for instance, of static network function or static network slices that we have today that are kind of instantiated and managed by the system in a kind of static manner, so they are creating and lasting for quite a long time, is an idea that probably will be overcome by 6G system. In this case, this reference picture is just showing a set of intelligent agents that we imagine will be at the baseline of a 6G architecture. I will go little by little through the main reason behind each of these blocks, but the bottom line is that with this concept of A-core, what 6G will be able to do will be to create dynamically slicing, providing services directly triggered by the requirements issued by applications that can be also AI-powered. So we may imagine, compared to today, where all of you can switch on your 5G phone and connect to one of the available network slices that the operator already put in place for you today, covering this area. The idea will be that the network will be having a much, much higher level of dynamicity, and upon the specific application triggered or specific application request, a dynamic slice will be created, instantiated, operated, and also terminated at the point in time the service will not be anymore needed by the user. User that also in this sense are not to be expected to follow the usual, let's say, common sense related to to devices as we know today, smartphone. So the key elements that we have in this A-core concept are shown here in this pictorial diagram. Of course, it's a vision, so it doesn't represent a real architecture as you may find already in some specifications. But in short, we will have a net agent, which I will explain one by one in the next slides. Net agent that will play the role of a network orchestrator, a source orchestrator. The assemble agent that will have the, let's say, role of interconnecting all the elements composing dynamic network slicing. Planning agent that will be the one powered by generative artificial intelligence to create the network slicing upon the requirement. Connection agent providing the connectivity between all the elements that are composing the network slices. Execution agent, the one that is directly operating on the infrastructure, of course, because each network function or each slice will have to run on some piece of hardware. And the operation agent that we'll also explain below afterwards is relating to the fact that many of these agents, of course, will be featuring machine learning and artificial intelligence, for instance, reinforcement learning, and so coordination among the different intelligent agents will also be necessary, in this case, for optimization purpose. Okay, now probably the presentation is way richer than what we can afford today with the time we have available, so I will not go through all the details, but I will just try to give the essence of each block that we have in this vision. So the next 3 slides are actually including the design principle behind this framework. The first one, as I said, is the net agent. This is the most relevant element to discuss first because it's one of the 2 that will have direct interface with the application, right? So thanks to the new large language model and new different interfaces that AI will enable, net agent will be able to receive directly the requirements for the service to be instantiated. And such requirements will be translated into a topology and an architecture for the specific network slice. So you may imagine what today generative AI can do to generate an image, right, will be done to generate an architecture of a slice, its topology, and the specific infrastructure on which it will have to run. So that is the net agent. Thinking in 5G perspective, you may assume that this will be replacing or enhancing the orchestration capability that we have also today. Net agent, of course, will have this capability of orchestrating, but there will be the need also of interconnecting all these entities. As you know, as of today, one of the powerful enhancement that we got from 4G to 5G was the introduction of the service-based interface, which was actually giving quite some flexibility and a wider ability of composing flexible infrastructure somehow, giving the possibility of all network functions to interact with each other. Anyway, even this concept can be stretched much, much farther if we assume that all the entity that will be composing the slice will be assembled and connected by WASM, for example, WebAssembly, as an example of a platform, let's say, to run and interconnect software that is running in a much more flexible way and also independent from the hosting environment. So in short, the assemble agent, you may imagine to be the entity, let's say, the intelligent agent that will be replacing the service-based interface as we see today in 5G architecture. Going next, we said that the orchestrator is the one in charge of transforming the requirements application into a slice requirement. Then there will be the need of having another intelligent entity, in this case, the planning agent, which will need to, let's say, realize the slice itself, right? So define a specific topology, identifying the infrastructure, and actually doing all the design that today is done with all the activity that are relating to the life cycle management of a network. So in this respect, the planning agent is the block in this intelligent architecture that will be replacing and automating all the O&M capability that we have in network as of today. Of course, this is about the design and the instantiation, but also all these entities that are actually composing the slice, in this case represented by an AUE, an ARAN, and an edge gateway connecting to the application networks, will require connectivity among each other. And in this respect, there will be the a connection agent that actually will be in charge of providing the connectivity among these elements. In this case, if you think about what happens today with session management and resource management in 5G, the connection agent will be somehow replacing the session management of the end-to-end slice. So taking care of the scheduling of resources on the radio, the routing, and the transport resources on the core network side. Last, other two elements that need to be mentioned here. The execution agent, far more intuitive than the other ones, is the one facing directly the infrastructure. So we will also have, let's say, protocol or mechanism to act upon the bare metal or the virtual infrastructure. So that is a bit straightforward. Operation agent actually is what I was mentioning before. All these intelligent agents, of course, will be featuring AI algorithm. Many of you very familiar with the, I don't know, reinforcement learning. You are aware of the problems of conflict resolutions, for instance, or sub-optimization that we may have, or instability or scalability. So task by task, obviously there could be the need of coordinating all these intelligent agents. And the operation agent is the one in charge of it. Okay, now looking at the timing, now I'm going very quickly through a few of the slides that are actually containing more details. Probably the slides will be available afterwards, and we can definitely interact only during the coffee break. From the designing principle, the following slides are actually showing a bit some high-level details of the architecture. Not going into the really the nuts and bolts, but just to mention the key message from these slides. As I mentioned before, the target, the key message here is that applications will be triggering the creation of, let's say, dynamic slices, and all the process will be automated level 5, let's say, theoretically with no human intervention. So application will be interacting with planning agent and the network agent, issuing the intent or the requirements. And then network agent, the orchestrator, and the planning agent, the lifecycle manager, will be using all the entities available for actually producing the slice. Designing it, instantiating, putting it on, and discharging when it will not be necessary. Here there is another slide describing how actually the orchestrator will be based on generative intelligence in this case, of course, because upon the requirements, it will be necessary to devise what actually the topology and the characteristic of the slides will look like. And not to mention, of course, these general architecture are also already expecting the introduction of a vast new set of interfaces compared to the ones that we are familiar with from 5G system. I will go very quickly through this. And the idea finally is here that, of course, all these automation will also finally result in actors that will be actually working directly on the specific elements that will be combining all the necessary functionality that are needed by the network slice to support the service. Yes. So now here we are going towards the conclusion of the presentation. There are just a few slides that are stressing again the key points of some of the entity that I was describing so far, with some additional details that can be relating to the way generative AI is working. For instance, when we discuss the planning agent, of course, the one replacing the lifecycle management, in this case, we will also have the capability of receiving from the outer loop continuous feedback on the actual performance and functionality of the slice. This is, of course, necessary to adapt, to fine-tune the models that are behind the topology and the functionality of the slice. Outer loop that will actually be built on top on an inner loop that will be actually controlling the functionality of the specific functionality that the slice will be made of. Yes, this is again the slide that is showing the role of these two feedback loops that will actually be used by the planning agent for a fine-tuning of the slice topology, functionality, and performance. This slide is also to recall that the concept of the service-based interface was, of course, inherited by IT technology, let's say, And in this case, the idea is to go towards even a more flexible approach taken from WebAssembly, for instance. And in this case, the assemble agent will be the one in charge of this type of capability. The idea, again, compared to earlier generation, is to even stretch further the ability of interconnection between these entities. You are maybe very familiar. 5G was making a big step ahead. However, the service-based interface anyway is confined to the core network. So we don't have the same flexibility in terms of composition of network function when we want to interact with the device or the access node. So WebAssembly could be an example of a piece of technology that could help this flexibility to span actually all the elements of the slice of the 6G system, as I said before, independently from the specific hosting environment of the functionality. Yes, here are some more details that I will just skip for sake of time. And the last one, again, is the connection agent. Also, a few words about this. I think it's worth mentioning this because even when we were assembling this presentation, I was realizing that there is plenty of concept in this presentation that, especially to those familiar with 5G, can really be confusing because actually there is a clear overlaps between concepts that nowadays are either part of the control plane or part of the management plane. So in this case, the connection agent, it could be ambiguous to understand. It could be relating to the creation of connectivity of the element composing of the network slice or the connectivity of the device once the session is established. Actually, this concept will be blurred more and more as the distance, let's say, the distinction between control and management plane in this automation system will become really, really thin. Right? So in this case, the connection agent, considering what I just said, will also be deputed to establish the end-to-end connectivity when service will be established by the end device. So we'll be in charge of guaranteeing the quality of service for the specific slice, for the specific device exploiting a specific slice. Yes. The presentation is also containing a few snapshots showing how actually the configuration, update, and access to this dynamic slice could be actually taking place with reference to, let's say, a kind of representation that some of you may be really familiar, but we don't have time to go into the details of this, neither for the operation agent and collaboration. I would then just jump to the last two slides that actually are conclusive somehow, because as I mentioned at the very beginning of the presentation, the work that we have been doing, putting together this vision, is actually trying to guess, with a big leap in the future, how enhancement in AI may shape the architecture of 6G. And the main point here that we wanted to make with these slides is actually that this new type of technology, LLM in particular, are currently showing it is possible to make a revolution in the way the software is built. Right? Many of you may be familiar already. You don't need to write code anymore, right? You just issue your requirements and the code comes out itself. Now here the picture is a bit more complex, obviously, because we are talking of a code that is creating a network slice, but in the long run, this is exactly what we are expecting. So going more and more towards a pervasive usage of artificial intelligence, we go from earlier steps when AI was actually used just to aid specific actions that we were doing in software design, to a fully autonomous deployment of a piece of software upon the requirements. The only last step issued by humans towards the extreme automation. And the last slide is actually a kind of look back to the past, because all what we were presenting today is actually showing how this concept may be finally giving birth to application-driven networks, ADN, which is actually a research concept that is dating back a couple of decades ago, I guess. So now with this enhancement in AI and machine learning, probably we have the chance of seeing these research concepts going into the next generation standards as per IMT 2030 requirements. And this completes the presentation. Thank you. That was a bit long.
Thank you very much, Riccardo. In the interest of break, let me please take the questions offline. Do we break now or? Can I please request Zoran, please? So sorry about the question. So sorry. Sorry about the question. We will take the questions during the break.
Okay. Can you see this? Okay, so it works. Okay, welcome to my talk. I will try to put it in 15 minutes. Let us see. So this is a talk about the role of 6G in the or communications in general in this AI era. And here I'll provide some insights which are basically coming in part from our 6G RIC project, which is a 6G research hub that is coordinated by Fraunhofer HHI and assembles over 30 partners from academia and research institutes with some advisory board from German industry. So to build my case, and also following the motto of this summit, I will start with a somewhat provocative question, and this is the following. So this is paraphrasing a stand-up comedian who says something like this. So how did the machine become the thing that does art? And why are the human the ones working in warehouses? So shouldn't robots be working so we can paint? So this is, so you'll see where I'm going. So a possible answer to this question could be that actually, in fact, it could be easier for robots to paint than to be involved in complicated sensory motor activities, which for us human come as natural, so to say. Yeah, and this goes back to this famous Moravec's paradox, which basically says that yes, the things that we can consider to be complicated, like playing chess or doing some abstract thinking, is actually difficult for us because our brains, not only human but also animal brains, have evolved such that they were, they evolved to do this kind of sensory motor activities, basically related to their ecological environment. So basically there is one very old and powerful mechanism, which is unconscious and innate, which supports this sensory motor activities. So this is to say that if you would like to go now to some applications at the network edge, like edge intelligence applications, and people in 6G also talk about collaborative robots and similar. So actually, these kind of tasks, as shown here, are difficult for, let's say, machines and for artificial intelligence to perform, even though they come simple for us. Yeah. So where I'm going is basically to say is that if we would like to enable edge intelligence, computation should maybe borrow some insights from the way that human and animal brains are built. Yeah. And the role of communication, of course, here is also kind of a specific, as I will say, because at the network edge, basically, will be a kind of, I can say, a battlefield where actually a next generation of communication systems will meet the next generation of AI. So here you have one depicting something which has basically 3 building blocks. So let's say you have an application which is related to human-robot interaction or collaborative robotics. So you can think of this to work, you would need to have 3 blocks. So one block is related to sensing, which is basically the perception of the environment. And the other block is basically taking this input from the environment and doing some kind of computation or pre-processing, some kind of intelligence, which will be this then embedded on these edge devices. And then also you will have a connection to the base station or access point where you will do some kind of a final inference, maybe to have a control loop or similar. Yeah. So this kind of a system model which integrates sensing, computation, or to say AI, and communication is very rich, because you have a lot of options here, like where is the inference done, how much processing do you do on the device, what kind of a sensing do you do you optimize your sensing process together with your let's say computation and communication process, and so on. So in this project, basically, the building blocks that we are looking at are the following. So the first research block is related to the concept of semantic communication. Simply put, here we are talking about this notion, and a lot of people also say it in this way, when they say, okay, communication links are not only bit pipes. Yeah. So in a way, communication is not the aim per se, but communication is done with the aim to perform a certain task. Let's say the task is robotic control, for example. Obviously, you don't need to send all the data, let's say full scale images and so on. Yeah, so this is a very intuitive understanding that you can somehow extract and transmit only task relevant information, basically. So this is closely related to this concept of semantic interoperability, which extends the notion of data exchange through standard interfaces to include the meaning of data. So in a way, if you have a task, something like, for example, classification or object recognition, then obviously if you have something like a local model, you don't need to extract features which are related to the source code, basically to data compression of the source, but actually you can extract features which are only related to the classification task, basically. And of course, this works under the assumption of a common information model that the transmitter and the receiver share. So if you look at this picture here, you can think of this as a kind of an extension of this AI native radio interface framework in 3GPP, with the addition here that you are basically including this task-oriented communication. Yeah, so the idea is when you are extracting, let's say, features, the metric is kind of a semantic, and semantic means that it accounts for the final objective. Yeah, and if the final objective is something like control or just classification and so on, then of course you can compress a lot. So this is, I would say, closely related to this AI native framework, but with this twist related to the task relevant operation. And a similar, I would say, perspective is, or just one addition to this viewpoint, is to say that this kind of architectures basically consider the process of data acquisition, computation, communication, and let's say also control from a joint perspective. Yeah. So, for example, if you what you can do here, you can jointly optimize your traffic generation process together with the parameterization of your physical layer, let's say MAC layer transmission, such that you save on overhead, energy, and similar. And this requires a kind of a cross-layer perspective on protocol design. But for example, let's say if something like data generation is typically assumed to be exogenous, so this is not something that the physical or the MAC layer controls. So if this is something that's related to application layer, so there will have to be some kind of an interface such that you know, they can talk to each other without going through this typical full layer of the protocol stack. So, and the third block here is basically this what people call next generation AI. And the point here is that for these edge intelligence applications, one should look closer into computing paradigms that are closer to how our, let's say, human brain or animal brains work, also in particular in relation to what I have mentioned before. So one way to, or one direction that we are looking and exploring is these neuromorphic architectures, where which are basically, let's say, not only vaguely inspired by the working of the human brain, but actually also process in the domain of spikes and employ spiking neural networks instead of conventional neural networks for computation. So people will not agree easily what means the neuromorphic, but let's say, roughly speaking, a neuromorphic should have at least some features, and one feature is like in memory computing, processing with the spiking neural networks, and then communication basically with spikes, ideally information also in the timing of spikes. Yeah, because this provides the opportunity to have energy efficient operation, meaning that you know, energy is spent only when spikes are produced. And in a lot of applications like this event-based scenarios and so on, as I showed with this camera, you really don't need to take the full picture. You only need to record some events when you have a change in the scenery. And this is, for example, what these neuromorphic sensors actually also use and benefit from. So now, if you, I can maybe go quickly through this. So if you combine this concept of semantic, meaning that you only extract task relevant features, and also employ some kind of neuromorphic computing where processing is done with the spiking neural networks, so you can also achieve state-of-the-art results. So there's nothing, let's say, restricting, at least for some applications, that when computing is done in the domain of spikes, that actually you do worse or much worse than when you apply other neural networks. Of course, it depends on the task, but some kind of classification tasks and those other kind of tasks, actually, they can achieve quite a good performance. So at HHI, also within this project, actually, we are also interested in building test beds. So this is one, let's say, our playground for edge intelligence. And we are integrating here aspects of communication, sensing, and neuromorphic computing. So here we have implemented the proof of concept of what we call, not we, but what other people call neuromorphic wireless cognition. So it is basically semantic aware communication with when processing is performed in the spiking domain. This is an example of a human-robot interaction, but you can also think of other examples, for example, in medicine or similar. And the block diagram here is really the one that I showed at the beginning, where you have this neuromorphic sensor, then you have processing or computation by using a spiking neural network when you only extract features which are relevant for the task. In this case, the task is this gesture recognition for robotic control. Then we communicate over a wireless channel. We do we learn over a noisy wireless channel, and we do learning based on this directed information bottleneck, which is just extension of the information bottleneck to account for these effects coming from processing trains of spike signals, basically. So what is missing in this framework is, for the moment, we were working with cameras as sensors, and it would be eventually interesting to integrate radio sensing into this picture. And of course, integrated sensing and communication is considered a key 6G technology, and there is a certain interest also in industry. So for us, it is also interesting to see how we can perform sensing efficiently on devices. Yeah, so not only doing infrastructure-based sensing, but also sensing on devices. So for the moment, we are doing infrastructure-based sensing. Actually, we also have sensing going into the D-band, so very high frequencies. So this is just a video where we show that we can, you know, recognize and the movement of targets. This is actually one of the first implementations in this D-band for sensing. We see that it's really very sensitive. You can really even the smallest change in the environment you can really catch. So this is also something that you could use for medical imaging, basically. But now to make this such that it also works on devices in an efficient way, something that is the next step. So the next step will be basically to have radio sensing, AI, this next generation AI, and communication embedded on those, let's say, on devices. So I will end up on a somewhat speculative note, I would say. So there are some other lessons actually from nature or from biology that we can take in the design of future artificial networks, actually also for communications to be correct. So one of these is there's this famous paper by, at least famous for me, by Anthony Zader, that is critic of pure learning and what artificial networks can learn from animal brains. So this goes back to our discussion at the beginning that that some of the functions, I mean, let's say, the reason why animals and human master this kind of tasks, which are difficult for AI, but which are very relevant for these edge intelligence applications, is because they have an innate structure which is there and which is also passed genetically. So there is not the concept that not everything is learned, you know, but some things are, you know, let's say, prepared such that learning can be quick and efficient. Yeah, I mean, this is I mean, there are a lot of examples in this paper that support this. So one of these is this, as I say, this interesting observation, also supported by experimental evidence, that sensory representation and behavior in animals, they are largely innate, and rudimentary space maps are already present in let's say, in this case, in rats, which are already 2.5 weeks old. So innate prior speed learning. Of course, this might seem a little bit philosophical, but the point is that you can think of this in the following way. You can think of this about the fact that a lot of neural networks, like for example, structures of human and animal brains, there is a lot of structure, there is a lot of sparsity, and there is a lot of, let's say, hierarchy there. Yeah. And in other words, you have the structure induces computational function, basically. So this is to say that this could be also a lesson for model compression or for deploying models which are easily compressible and also kind of efficient on edge devices, because you know, if you have a structure which could be let's say restrictive, but on the other hand suffices for the type of task that you would like to do, then actually that could also be the way to go. And in this respect here, the interpretation is that these models are then compressed and encoded in the genes. And this is what these people call genomic bottleneck. So this is exactly something which has some analogy to basically model compression also in the systems that we are interested, so to say. So my endpoint here is that I mean this does not really cover everything we do in this project, but I put it such as something which is relevant to edge applications. And I have just taken one or two examples here. So for more, you can also check. Other things, of course, that are of relevance for us are related to Operan evolution towards 6G. I think some people in working architectures are also interested here. And we're also working on digital twins and integration of contextual information. For example, this topic of channel charting, which is based on unsupervised learning to provide localization, beam management, and so on, is also of relevance to 3GPP. This is also what we work on, but as I said, I try to focus only on some of the aspects to have it some kind of let's say self-contained presentation. Okay, thank you for the attention. Yeah.
Thank you very much, Zoran. I think we will break for coffee, and please catch Zoran during the break. We will come back in 10 minutes, and let's go out and enjoy the coffee. Thank you.
Just for those who have the leaders pass, we don't have VIP lounge open today. It will open tomorrow and Friday. So today you can buy a coffee. And for speakers who registered and did not get the leaders pass, please see me so that I can sort you out. Thank you.
Okay, we will have the next presentation. Ammar, please.
Send me WhatsApp.
Yeah. No. We use
Ah,
yeah, just share it here. Yeah. Yeah. And put it on full screen.
my screen, yeah, that's
No, you need to put good. That's that.
So, hello, dear colleagues. Thank you for inviting me to this event. It's my pleasure to be with you. I will try shortly due to the time. So if in my slides you will have questions, maybe we can discuss them in details later in next meeting or in breaks. My name is Ammar. I am a professor from St. Petersburg State University of Telecommunication. And in this talk, I'm trying to talk about intelligent telepresence robotics, challenge, prototyping, and solutions. First of all, for robotics, we will try to discuss this based on integrated 6G networks. So in this picture, you can see how to communicate all together. So I think use cases for robotics can be anywhere. So underwater, ground, sea, and space, air and space, and they should be communicate all these together. So we have a lot of works in this field, how to integrate all together. Some interaction between air and ground, and some protocols for this area. So here about application 6G, I think a lot of people already mentioned. So about smart city application, holographic application, industry, autonomous vehicles, healthcare, extended reality, UIV application, and so on. And in this talk, I will focus in robotics, telepresence robotics, and their problems. So first of all, about some application and use case. In this, we prepared our mind map robotics infrastructure for 6G. So here you can see some for robotics infrastructure, we need about network generation and IMT 2020, IMT 2030, network 2030 in infrastructure facilities for delivery transport facilities, sensor networked robotics, transportation systems, telepresence suite. I will show one example in prototype in our lab for telepresence suite. Also, we have demo today at evening. We will show this again in details so we can discuss robot cleaner, robot miner, robot avatar, robot humanoid, robot avatar, and so on. And about application use case in subsea, in urban infrastructure, mining, space, direction, transport, medicine, and education. And also in some technology in use, for example, AR, VR, machine learning, deep learning, federated learning, and microservice architectures. Also the use of artificial intelligence. In this case, I will show some examples in my talk later. Objects, parameters, technical processes, surfaces, and so on. So here you can see the application use for mining factories, for transportation system like unmanned vehicles, round traffic monitoring, sustainable transport systems, and also in medicine for smart hospital system application, the remote surgery with needs very low latency in this, and also for underwater and surface infrastructure, so smart ships, smart submarines, and here you can see
For example, robotics assisting students with science short grade robots required very low latency. In this robot performing and ultrasound, other diagnosis, drones monitoring traffic and so on. Also for autonomous cars, moving city street with robotics inside handling driving tasks. For underwater robots, remotely operated vehicles, and underwater robots also in the whole of large ship, with searching for science fair or so on, and robots traveling inside to inspect for corrosion leaks in package. In this, we propose how to solve problems with quality of service, quality of experience, and in this I will try shortly because due to the time about integrated network architecture, some virtualization network slicing. In previous presentation was a good talk about this. Service current and 2030 networks, algorithms in time, service, comprehensive meta structure, logical services, and some proposed timestamp systems and so on. So for slicing, here you can see some for integrated section networks. In our laboratory we use some orchestration like Mano. We have a system built based on a platform where we build these kind of systems for different use case applications. For example, in 3 categories 5G networks like URLC, machine type communications, and for video, 4K, AR, VR, XR, and all these applications. For URLC, we need low latency applications. For augmented and virtual reality, we need like big bandwidth and another requirements in network. So in this, we based on this, we can build our slice in the network. So here, the layers of slicing, like business layer, service layer, infrastructure layer. First is to provide support for use case, collects information about the required applications, and important application information before passing it to the service layer. Service layer enables to provisioning of a specific slice service by grouping network functions into network function layer and directly link it to the business layer and enables a various of application. And infrastructure like edge core and radio access network. So in very important here, we mentioned in traffic engineering, there are a lot of different applications in with different requirements like in this Internet of Things, tactile internet, holographic, digital twins, and so on. And based on that, in traffic engineering, they use 3 in-time services, on-time services, algorithm on-time services, and also coordinate services. And based on that, we can provide the quality, the required quality for each applications. Here we prepare comprehensive meta structure for quality of service, quality of customer, quality of experience, and time generic model with their parameters. You can see the slide. And to counter all of this together, we can use system interaction using, for example, this cloud. And here you can see the logical service-based QX system model. And one of scenario, we propose timestamp system. So here for extending possibility of robotics, we can use drones. So drones can, for robot avatar, extend possibility in some places where robotics cannot move. So this how it works. You can see, and we use we suggest to use some based on a global robotic architecture based on edge computing cloud to solve problem with latency. Here you can see Telecommunication suite, for example, robot humanoid, and we can robot avatars built using swarm of drones. These micro drones, we provide some prototypes and some solutions in our laboratory. And see here you can see the functional modular architecture where the physical interaction, network control modules, and applications. So in using artificial intelligence for robotics, I think is one of the hot topics. It's need a lot of research in future. First, to enhance autonomy and navigation. So there are a lot of to use improve simultaneous localization and mapping, moving of how swarm of robotics can move. They use some swarm algorithms for example, obstacle avoidance. The second one is for advanced interaction and communication between human and robotics. First of all, is the natural language processing. So also, there are a lot of works in this field, and they also need to extend in this. Need a lot of works in this field. And emotion recognition, we in our lab we are trying to use some gloves and to basing on sensors to get feedback between robotics and the humans to feel, for example, temperature or something like this. But emotion recognition is also one of the important direction in future. In integration with other technologies, for example, telepresence services, augmented virtual mixed reality holograms, how robots can react in data from these devices for augmented virtual reality, and also for improving calibration capabilities, haptic feedback, advanced control interface. Artificial intelligence algorithms can be used in these specialized applications for healthcare. For example, in Buse Bilgin remote surgery, we can use the requirements for this very low latency. It's around 1 millisecond. That's why we are working in network layer to solve problem to connect through networks. So in healthcare, a lot of use cases for robotics is already in education. For example, remotely professor can present talk through. I think I don't. Next time, I hope I don't have to come here. Maybe I can present my seminar from Russia. Workplace interaction, also security and privacy. To enhance security and privacy, also we need artificial intelligence mechanisms and algorithms. For robotics in healthcare, healthcare system analysis, for example, but for diagnostics, virtual health assistant, automated image diagnosis, robot assistant surgery. So the artificial intelligence also, it's very important in this case. We have some works in model mediation. So at the end of edge computing, we distributed edge computing to predict, for example, movement of the robotics, or to predict some to solve problems with delay through the networks. In our prototypes, we are working in this architecture. Okay. So robot human avatar, tactile internet, telepresence suite. So we have these layers, the cleanse layer with onboard chips, sensors, central cloud with robotics edge layer. And here we are trying to solve problems with latency in physical layer using some algorithms in this, and we built also Telecommunications suite, which we will present later at evening today, like demo. In these layers, we can use some protocols interaction at physical and data link layers. There should be different protocols in this component layer, set of sensors, actuators, onboard computing equipment for controlling and monitoring individual subsystems of human robotics. And the third layer is edge computing, limitation by the edge cloud servers hardware is, and the center cloud layer is open software platform to support a wide range protocols, and client layer is set of sensors, feedback actuators, as well as interaction interface. Here is, you can see one of solutions. So we can use micro and mini drones. As I mentioned before in previous slide, for example, if some catastrophes which happen, for example, in Turkey, or maybe you need some help, robotics can scan, help people. In this case, so in areas which robots can move, so we can use this kind of micro mini drones. So this is the infrastructure which we propose in this work, and some interfaces and protocols which can be used. And we have some works. I will try to give links later in this area. About Telecommunications suite, I will keep it for the last session, but I will show, we will show this demo later. I think we can discuss it. The main idea is we build this we have gloves, for example, Telecommunications suite, and remotely we can move the robotics. So we will discuss in the last session in details. We will try to show this prototype in our laboratory. So we have also a lot of, for example, scenarios and protocols for robot manipulator here. Okay. Here you can see the swarm robotics, and using drones here, maybe to solve problems for swarm robotics. We build this architecture. This is shortly about what we are doing in our lab. My colleague Artem will discuss more details about research in our laboratory. Also, we propose application layer protocol for robotics. This was accepted in recommendation in 11 group last meetings in May. Here we propose application layer protocol for robotics. We have multi-level edge computing. Using this, develop a lot of offloading algorithms using artificial intelligence and other algorithms for multi-level edge computing. And for drones, we propose also, you can see in these links our works, some protocols to connect between drones, and some offloading algorithms between different layers of edge computing. We have air, edge, and ground edge, and how to for our offloading, we use a new technique in these works, using swarm algorithms for optimization tasks, and we use for NP-hard function in mathematical, we use some kind of deep learning, machine learning algorithms to solve these problems. So here for swarm robotics, we have some works. We have also prototype. We emulate in physical layer using SDR UAV base stations and some emulators in In this case, we also propose a new architecture for autonomous vehicles with different layers of edge fog computing, and in ground we can extend the coverage using device-to-device communications and other algorithms. Also, we have platform. This platform was presented before. Is this extended also in for telemedicine services? How to use dynamic fog computing and multi-level edge computing with microservice migration. Also, we have Rex platform. It's also one of our solutions in core networks. How can use migrations of following services. And also Nebula in advanced communication network telemedicine services. Also, we propose some algorithms in this field. For intelligence edge computing, here, for example, for robotics, we can use virtual local model. We have a model mediation to solve problem with latency. We use neural networks algorithms in the edge computing layers. For distributed edge computing, also we have some solutions. So in future we are going to use federated learning also algorithms. Some of our prototypes and solutions for AR/VR holograms. And the last one is to use light version of neural network at the distributed edge computing. Also some solutions for vehicles networks. Thank you so much. Sorry for delay.
Thanks. So Ammar is having a demo. So he is at the end of the day, he will be here with 3 more participants for a demo. Please catch him during the demo and he will show you the video as well as you can ask him all questions that you like. Thank you so much, Ammar. Now, can I please request Jose, please?
You need to stop sharing the screen. Nice to see you. Absolutely. Let me share. Hello, everyone. My name is Jose Alcaraz. I'm coming from University of the West of Scotland. Broadly speaking, just to be very quick in terms of the presentation of our capabilities, etc. So we are going to be today, we are going to be focusing on AI cybersecurity for operations. Okay, so I'm going to be focusing on that. But our team is a really strong team. We have been present in all the 5G BBB phases in the European arena, phase 1, phase 2, phase 3, phase 3B, SNS 1, SNS 2. So here you have some of the links. I'm not going to present them today, but every of them is a link that you click and we have a recorded demo of 30 seconds with the things already achieved. Let's say, okay, so everything I'm going to be presenting is a bottom-up approach based on experimentation. Okay, just to clarify. Now, coming back to the present, today we are going to be focusing on cybersecurity. And in terms of the cybersecurity, I'm going to be presenting the talk. First of all, I'm going to be a very quick introduction in this closed control loop, because we should all be familiar with. But at least I'm going to be moving from that on something what we call the shortcut architecture or the shortcut version of these control loops. Okay. Then after that, I'm going to be presenting some of the challenges we are going to be facing and how we have already sorted them. Okay, so, and finally, I'm going to be presenting some of the architectures that are related to the ongoing, some of the ongoing European activities in the agenda. Okay, so let's start with the fundamental. I mean, I'm not going to explain here in the room what is a network, but this is a 5G pre 6G multi-tenant network.
So in summary, I'm putting this figure just to have a common ground. So we have GUIs connected to the edge, connected to transport network, connected to cloud. And this architecture, what makes it different is it is multi-tenant. So we have different infrastructure providers and service providers. So up to here, everyone has the common ground. So what is going to be happening is I wanted to put this figure to highlight the challenges associated to the architecture. First of all, we cannot forget that we have here polymorphic traffic. I mean, traffic that is saving in every single jump in the network. So the traffic in the edge it has a different shape in the traffic in the core, and before the core, encrypted, not encrypted, encapsulated, no encapsulated, so on. And this is a challenge from the management plane and from the automation of the network, okay? The second one is the multi-stakeholder. So this kind of separation of roles is a significant burden. So cloud has not been easy to be implemented. So then there is also a mismatch between the physical and the vertical and the virtual perimeter of the network. So this is putting a lot of challenges in the cybersecurity threat. Finally, so the 5G networks and now the 6G networks are putting a lot of pressure on the speed. The speed is incredibly good and the low latencies are incredibly good, but the number of flows per second are exploding our management plane. So we are now able to handle to receive 1 million or 10 million flows in 1 second. So we need to have a management plane able to sort out this. So that was coming back to the question about these low latency things that were coming before. Also the high dense network. So we are having 5G, even 5G, not 6G, use cases with 1 million devices per square kilometer, if I remember correctly. So that means 1 million of different things to be managed, just to think about that. But on top of that, so just wanted to open up what we have as an infrastructure. Now let's focus a little bit more in that management plane. We have been presenting here some architectures in the focus working group. So this is a traditional closed loop architecture. We have sensors in the network, security sensors, because this talk is about security, but sensors. So later on, we have aggregation and prediction. I guess that Vehbi was referring at the beginning of the presentation about this proactive reaction of the cognitive loops. So this is this kind of modules that will allow us to have. Every of these modules has been implemented in our team. So it's not a conceptual architecture. We have prototypes. We can tell you about any detail about every of them. Okay, just to let you know. So then we have the analytic module that receives some metrics on the analytic layer and provide alerts. Later on, we have the decision-making module that takes alerts. For example, we have an attack, and then it takes decisions. The decision could be, you need to stop that attack in that point in the network, okay? Or this is what we did in the Arcadian project. I'm going to show you a demo about that right now. For example, Riccardo was presenting today that the 6G is about the dynamic management of 6G slices. So this is exactly what we achieved last week in one of the ongoing activities in the Rigorous project. This is an initiative from the European Commission that we achieve an end-to-end network slicing dynamically managed or triggered as a result of a cyber attack in order to mitigate that cyber attack. We call it disadvantage network slicing. So we create a network slice of 10 kilobits and we put 100 kilobits and we assign those flows, those malicious flows to that slices as a mitigation. Why? Because the cyber attacks are becoming really, really expert these days, and if you close or break that flow, the control of the side channel control with the bots will realize about that and will try to behave differently. So it's better to have some disadvantage than close it. So later on, we have the planning stage. The planning is the one that is decision is high level. Planning is a very concrete implementable plan and a set of steps that need to be implemented in the network. Later on, we orchestrate that plan. We have been seeing orchestrators in 5G for 10 years already. So, and finally, the enforcing of the action points in the network, make them enforcing along the different points in the network. So far, so good, no? So this is a loop that starts here and finishes there. This is the classical approach. Problem with these loops, in every of these components, we either implement them using a rule-based approach. I mean, we onboard metrics, we onboard analytics, we onboard decision-making rules, or we onboard AI models, right? So let's call it that in 5G, what we have been onboarding is rules, and what we have in 6G is to start onboarding AI models. Let's try to cap these things. So what you are going to be seeing now is, first of all, this loop has, this inventory agent, Riccardo was also mentioning before, the topologies 20 times, is always the forgettable in all this architecture. The inventory is sending information to all the components. Otherwise, we don't have a spatial aggregations of understandings of the network, okay? Because every of this one took 3 years full time for a PhD student to be creating the loop, okay? It's not this talk is based on 20 years of development. So then problems with these loops is, it has, the first problem is back propagation on cascade. I mean, if you have any bug in any of these, the loop close breaks. So you have, it's a very tough challenge to be sorted out. Requires production-ready components, otherwise we don't scale up at all. We also require complex sensor inventory and actuators agents, because every time we change from 5G to 6G, 7G, or any other technology, we need to re-implement all these agents. So at some point, we need to standardize this significantly, okay? Also, what happens with the rule base is error prone. So you onboard a rule, you try if it works, and if it don't, you need to reiterate. So with the AI, the problem is that it's data-driven, so we really need that data set to make the AI models. So, and also the main problems here is a very slow loop, because you need to pass by all the components. So what we have been proposing in the European project, Rigorous, is the shortcut version of the loops. So we don't have interfaces here, so standardization bodies are big. So that means that every component can communicate with each other, okay? So no matter how it goes. So the interfaces are defined, however, the flow is defined by the use case. So this is what we call a shortcut architecture. So what is happening here is, but you only have one limitation. You can only communicate in the sense of the loop. So don't communicate back, otherwise we start to have more complex systems. So any possible loop is valid and is use case dependent, and only limit is to respect the sense of the loop. For example, in the loop you have in the screen is for security purposes. I'm going to come in a second. So we have sensors detecting alerts in the network, I mean cyber attacks. To be concrete, I'm going to be showing a demo on DDoS. So then that sensor is really smart already. The device is, some people call it inner loop. Okay, so I call it signature-based detection, for example, okay? So then we have a detection, and when you detect an attack, you already know that this should be stopped. I mean, there is no one need to tell me. So this component can directly inform the planner, stop this attack wherever you find it. So you don't need to pass the whole loop. And the planner will understand the network, receive the topology, remember, and will say, okay, for this flow, it has been detected here, 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 and here. So now I will send my actuators as soon as possible, block, 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 block. And I will perform the automatic mitigation of the cyber attack. Is it clear so far? Okay, so no AI yet, just automation. So now, let's remember the multi-tenancy. What we are going to be seeing here right now is, this is a loop, a shortcut version of the loop. So we have sensors to detect attack. We have the planner that receive the topology of the network and determine where the action or the mitigation need to be done. And we have the actuators. You call it SDN, sensor controllers, well, actuators. And what is going to be happening is I'm going to be launching the legitimate traffic from the network. This traffic, remember, is polymorphic. It's changing in every step. Later on, we are going to be sending malicious traffic. And what is going to be happening is I am mirroring. So we do the mirroring. It's a mirror architecture because we don't want to put penalties in delay. So we do the processing of the attack offline, not online. Otherwise, we had penalties on delay, okay, on latency. So later on, when we detect the attack, the planning will come back to the actuators and will block the attack in that exact point in the network, according to the intelligence. Okay, so at this moment, the system will mitigate the attack. What is happening here is, now let's talk about cybersecurity. So a DDoS attack has some peculiarities. And I'm not talking about an emulator of a DDoS attack, I'm talking a real DDoS attack. And the first one is, topology-wise, is coming from 1,000 different points in the network. So you really need to understand the network to determine 1,000 different actions in different points in the network, okay? The second one is that we have every network has different topologies. I have 20 UEs associated to one UE, one edge in that particular network. In another one, I have 3 edges with the same 20 UEs, but distributed in the 3 different places. So the source of the attack is completely different. And the third one is that we have plenty of different types of attacks. I mean, UDP, only in DDoS, TCP, different payload, different sizes, different blah, blah, blah. I can continue for half an hour on different types. So you get the idea, no? So what is happening here is what you will see right now in the screen is we have legitimate traffic here on the top, okay? So later on, we are gonna be launching an attack. It's a 10 gigabit attack of 1,000 different points in the network. On that moment, the whole loop is triggered and the reaction is happening already here in 7 seconds. We did the mitigation of 1,000 different flows coming from different points in the network. So this is the level of automation that we need in production, right? So it's just to put you an idea of the context of what the context of these closed control loops. This has been already achieved in the Arcadium IoT platform, and just wanted to show you at the end of this presentation, we have here a small screenshot worth to have a look, because this is the operations, description for operations, let's say. Can I? Yeah, it's not coming up. So in this description, what you will see is the attacks in the left side, the plans coming in the middle, the intention sent to intent-based architecture, and the action being enforced on the different points in the network. It's just to show that everything is real. It's not academic. I mean, I'm coming from an academia, but this is a pure experimental-based research, okay? Then later on, coming back, I'm lining with that in the this is a rigorous architecture. It's coming from that European project. In that architecture, we are really following that shortcut version of the loops. This is why I'm not going to enter in detail. I'm not going to explain it, but you see that the workflows are jumping hundreds of components. So all the left part is jump up to the middle of the orchestrator, for example. Okay, so we wanted to push this back in the rigorous architecture. Now, and what we have been doing here is, first of all, creating the end-to-end point in the network. In rigorous, the use case is really ambitious because we want to put simultaneous attacks coming from different points in the network. For example, 100 attackers from the UEs, 100 attackers from inside of the DSP, I mean, compromising the management plane, and 100 of attackers from the ISP side, I mean, compromising even the virtualization layer. And the end-to-end slice, dynamically created according to the vision provided by Riccardo, should be protecting them all. Okay, so we achieved that a week ago, so not yet ready. It's being presented that we speak in EUC and SUI as a demo, just to tell you, but it's just to put you an idea. Then challenges on the AI-driven cybersecurity. All what I said before, everything is rule-based. There is no AI, okay? Now, first problem or first challenge is we really need that data collection layer that we were talking in the coffee break. This is to have a data-driven AI training. So what we have been doing is creating the data layer and pushing everything, every information we have in the network into that data layer. It took us some years to achieve a scalable version of this. So after this, the attacks are not welcome at operations in any place. So we really need that digital twin, especially for cybersecurity. So we all agree, right? So then what is happening here is we need a digital twin that either we do a lab-based environment or we do a digital twin that mimics with high fidelity, and I want this to be capital case, at emulation level, the production-ready infrastructure. Otherwise, sorry, but any model that we are going to create is not going to be working on production. So we really need to work on the system that is the production system, okay? So this is why we have been working for a number of years on creating in the ITU standard, we call it engine platform, experimentation engine, AI model engine. In summary, this is a digital twin of the network. We have achieved a digital twin of the 5G network. So this in the right part of the screen, you see how we are able to set up 4,000 nodes, and these are real nodes. I mean, Linux nodes, not so real containers. Okay. I'm deploying the whole 5G data path and VXLAN, I mean, cloud layer encapsulation on top. For example, 4,000 nodes took us 1,000 seconds, maybe 5 minutes to create the digital twin, okay? And also after this, we set up the experimentation. For example, we launched a DDoS attack. But we have automated this in such a way that we are able to create thousands of topologies. So we create a topology, we run an experiment, we gather data set, we destroy topology, we try another topology, and so on and so on. Different attacks, different topologies, different things. This is how we gather the data set for training, right? So then, after this, the third challenge is that that data set should be really relevant and applicable for operations, for production-ready infrastructure. Because otherwise, all the academics invent some data sets that are never going to be working in production systems. So this is why we need different sandboxes in topologies. We need different communication architecture, for example, encapsulation technologies. Some people are using for cloud VXLAN, some others are using Geneva, some others are using, someone use a core, another core, So we need also different attacks and network conditions, congested, not congested, legitimate traffic, not legitimate traffic, so on. And also some sensing and actuation technologies. For example, we have been implementing cyber attack firewalling at least in 6 different technologies, FPGA accelerated, BPF, IP tables, TC layer, P4, so on. Every technology in the control plane. Different IP addresses, different MAC layers, different victims, different targets. So when you do all this together, so you create a big data set, right? So we have already automated the pipeline of AI training. So we have been testing a lot of AI models against that data set in order to tell you exactly which one is the model that works better in terms of different topologies, different attacks, different things. So as a summary, you can see over there that right now we have been testing many of them. As a result, we have been able to detect attacks with different types of attacks, different network conditions. All this series already testing different AI models. As a result, we have been able to achieve an accuracy of 96% of the detection of the attacks, okay? This is how, after we got this, we put the AI model in the network, replacing the rule base by a AI base. And the result is working as expected, with a 96% of availability. It's tested in real network, okay? So another approach that we did is the Gen AI approach. This is completely different. So in our previous loop that I mentioned, the onboarding of every rule is using the same language. Yes, we are a university. We can take the advantage to use the same common language for onboarding a metric, for onboarding an analytic rule or a decision-making rule. As a result, we have been creating, using generative AI, SQL sentences. We are using SQL to define the semantics of our, let's say, relationships in the data set. So as a result, the Gen AI is starting to learn how to produce useful and meaningful SQL sentences for detecting the cyber attack. Okay? So it's a preliminary result, but I wanted to bring it because it's a different approach. It's using AI to generate those rules that are onboarded in the system, not to replace the rule by an AI model. You leave the rule, and then you put AI to generate the rule that isn't going to be onboarded. Okay? So, and it's producing very good results. Then, later on, Professor Chiwan also, we are both leaders of the same team. We'll be presenting more AI models on the control part. I've been more focusing on the analytics part. He will be more focusing on the control part. These are some recent words where you can see key of the things that I have been mentioning are always in the context of this project funded by the European Commission. Okay, so potential topics in this project are AI for federation of unknown cyber attacks. After you have the AI model, we have been starting to learn, I mean, it's going to be published very soon, that we are starting to look for unknown cyber attacks, never seen before, with a very good result, okay? Another one is a federated AI for privacy preservation and AI for optimization of mitigation plans, okay? This is, Professor Wang will talk more about that third aspect later on. Potential standardization opportunities. So we have an AI-driven closed control loop architecture. We have a specification for any interface in the control loop, a specification of the data collection layer we were talking in the coffee break, and guidelines related to the digital twin capability that we were mentioning. Professor Gyu from the first speaker, I can't remember the affiliation, I guess it was you. He was talking about the digital twin interconnected. So we address this by distributing the emulation of the digital twin. So our digital twin is distributed across multiple physical infrastructures. So otherwise, we have been able to emulate 65,000 containers running a virtual network, a digital twin version of the network, okay? And we achieved that by doing so. These 5 presentations here are already published, and you have here the 5 references associated to those works, okay? I'll be more than welcome to answer any question you may have in the coffee, in the next session. Okay? Good. Yep.
Thank you so much. Can I request questions during the lunch? And we request Thierry to be, please. Thierry, please. So while Thierry is coming up, I just want to update you that both Professor Chi and Jose, they are authors, co-authors of ITU recommendations. We had a good collaboration with both of them. And it was very interesting to work on the ITU recommendations along with them.
Okay. Okay. You know, okay. Okay, good morning already. So big pressure just before the lunch break, as always. So I'm pleased to be here, and thanks for the opportunity to present what we are doing in TII, Technology Innovation Institute, in Abu Dhabi, especially within our center, Digital Science Research Center, which is dealing basically with telecommunications and cybersecurity. So thanks for introducing cybersecurity topics again. I guess we connect some dots there. Okay, and as you see, okay, from the title, I'm going to address, with the tip of the iceberg, what we are doing for next-gen mobility, especially through what we are going to propose, the large action model infrastructure, the LAMI. Okay, so let me just introduce you that. Basically, the rationale why we are, focusing on the smart cities and especially, safe, sustainable, autonomous, and electrified infrastructure, because we believe that this is the backbone of many different verticals and business where you can get many gains, okay, especially if we are from a carbon-free, economies, close to the technical divide. So basically, again, this is the backbone. And within this backbone, we are, again, addressing the particularity of intelligent transport system, right? Because, more than 50% of population is, again, living in urban areas. It will be like more than 70% very soon by 2050. And again, transport for the road or even UAV, again, this is a lot of carbon emissions. Okay, that's why we say, well, let's start, okay, baby step, if I may, to address intelligent transport system, right? And let's see where we can have some benefits. Definitely, we'll get many sensors. I think the whole morning we're discussing about that. The edge AI, with many sensors of different categories, okay, video more and more, LiDAR, radars, you name it. And of course, all this is producing a lot of data. Okay, all of this, we require more and more, AI capabilities on the edge, and we believe that we can get that. I will show you that. So basically, this is why, okay, of course, we need 6G, okay, for getting this new dimension of native AI. Okay, again, the whole morning we could see this collective intelligence, okay, that we try to bring on the table and to bring to the real life. And this is what we are pushing for, okay, in TII. So definitely 6G is going to be, a business game changer, okay, thanks to native AI, and also based on virtualization, disaggregation, that you were also mentioning, okay, the whole morning. Time for action. So yeah, okay, so I'm not going to, again, to show the timeline of 6G or ITU, okay, standardization. We all know it by heart, but also I think I wanted to mention this move, okay, from the US Department of Transportation by creating this ARPA-I, okay, no need, it's not DARPA, okay, so it's ARPA Advanced Research Project Agency for Infrastructure. So which means, they are investing a lot of budget, a lot of money there, because they understood, okay, again, this critical need for deploying this new generation of infrastructure. Some of the topics that they are addressing, of course, this is related to what we do. Okay, so this is good news for us. IoT, artificial intelligence, of course, connectivity, networking, cybersecurity. Well, no need to mention it, but okay, cybersecurity by design. Now it's native AI by design. Okay, and just to name a few challenges that we are deploying, early this year, with AI for road safety, with intersection safety challenges, with like $6 million reward dollars only for US entities, I'm afraid. Okay, we cannot compete. But yeah, there is something happening, and that's good. We need to make sure that Europe, of course, is also behind it. There was a lot of development of V2X, okay, in China. US is really, acting on that with the waiver, for instance, for the V2X, the FCC action, okay, on the frequency band. So, and now, okay, again, with innovation agency. Then, of course, and when we say bringing something to life, and I think this was the topic as well of the workshop, okay, implementation, TII, we're all about it, okay? So we are clearly not doing blue sky, okay? I think we have quite a good positioning, which is about, again, being pragmatic, operational, and to be an applied research center. So I always wanted to show you, this is just an example what we did, 2 years ago, okay, again, for AI for road safety, where we are addressing, this famous, well-known challenge of the lane, okay, on the motorway, the merging lane, and especially if you go to Abu Dhabi, you will see this is quite an interesting, topic there, okay, with a roadside unit, and of course, with camera, lidar, and some AI on edge, okay. The whole point here is, of course, about the applied research center, and I think this is what I'm glad, to see here. There are many focus on implementation, okay, for proving the concept, the feasibility, and pushing the maturity for the industry. Because at the end of the day, this is really our goal and mandate for us, okay, to support the industry, the next part of the challenges. So you see, the simple simulation on the left, on the bottom left, and then step by step, once we manage to validate the concept, again, we increase the sophistication of the case with digital twin, it was mentioned, okay, digital twin, which is, quite a nice one that we have, okay, thanks to Cognata, one of our partner, okay, and then we always come back to the test bed on the labs, okay, on the right-hand side, and ultimately we always go for the field trial, okay. So even though we can, of course, synthesize very nice and more very nice, synthetic data thanks to digital twin, okay, so we can learn a lot, if I may, to use that term, okay, for the AI. Ultimately, we need to face, the reality, the real world, okay, so test bed and then field trial. So this is one of the example of project that we have, which is about, of course, trajectories, okay, prediction, okay, here. And as I mentioned, okay, we are, in my center, we are taking the approach, okay, of the infrastructure. We have another center, autonomous robotics, which is, of course, addressing that from the self-driving car itself. And for us, this is what I said, okay, magic behind the curtain, we're working on the infrastructure. So this is maybe not where you have most of the hype, okay, but this is where you need something, okay, to be done to support all these different use cases and challenges. The inference time improvements, we believe in that. Okay, I've been there for many years, as you could see, okay, and addressing IoT, okay, in that time. And we had, let's say, a kind of similar approach where many people didn't believe about machine learning on IoT devices. And then obviously, we had a tiny ML, okay, so which means people could understand a bit better how to modify the models, okay, for the machine learning, okay, and how also, to feed that much better on MCU. So tiny ML is there. Now we get machine learning on the edge IoT devices, even low power ones. The same will happen anyway, okay, with AI and Gen AI. Okay, we strongly believe in that. So then, our global approach, okay, that we are doing is network for Gen AI. So network for Gen AI, basically, we are working hard on building the new communication and computing framework for LLM in the network. So basically the multi-agent, okay, clearly. In order, okay, to bring to life this collective intelligence, so collaboration, okay, for some of the vertical that I mentioned here, and I will show you, which is about the intent-driven autonomous networks, okay, clearly, for 5G and 6G. And of course, again, okay, for the ITS. So then this is about, again, combining together the planning, the reasoning, the semantic communication, and the emergent protocols. So we are pushing now much more than just, if I may, just the LLM, okay, just to avoid ambiguities. So I introduced the large action model, here, okay, to make sure that we get, maybe all together the right understanding. And okay, this is something that we can debate, but for us, again, large action model is really the next stage, okay, for us. So leveraging the expertise and know-how that we have within TII, especially Falcon LM that was led by AI center. So we have many experts there in different centers with LLM and Gen AI, generally speaking. And for us in telecommunication and cyber, we're working now on the large action model because we need to interact with the real world. We need to interact, okay, with IoT devices, with sensors, to take decisions. We were mentioning automation. And of course, here we are trying to go beyond that. We see the challenge, okay, to get these autonomous networks, autonomous entities, but interacting with the real world, okay. So the example here, of course, the autonomous network, this is one of the big part of our challenges and investigation, I mean, nowadays in telecom units. Well, just mentioning, for instance, okay, of course, the Open RAN RIC, okay, which is quite a nice framework and architecture, okay, to be deployed. But then again, you will see, okay, the agent, okay, with the perception layer, the knowledge base, okay, the memory, the action, okay, from the LLM agents and pushing the boundaries in order to get an autonomous network, okay, for optimization especially, okay, this is something very important for mobile operators. This is very attractive for private 5G or private 6G, which is finally there, okay, in terms of private networks for the industry. This is very attractive there. So, instead of getting, of course, the plan by rules, then for us, this is pushing the plan by reasoning. And from the protocol side, the emergent protocol, this is something which is a bit less mature, okay, from our side yet, okay, but this is something which is very attractive, okay, and very promising. So here is one of the big parts, a big program that we have on the next-gen mobility. So bringing to life, again, this collective intelligence for a level 5 ITS, intelligent transport system. So you will recognize, again, I mean, the agents here, I mean, for large action models with the multimodal sensors, with the actions, the control units. So here we see the example, of course, of a car. It could be also for infrastructure, again, okay, roadside units. So then it will depend on the sensor that you have. So you will have different capabilities based on the sensors, different capabilities in terms of action, depending on the roadside unit that you have, okay, there, if it is a very simple one or more sophisticated one. At the end of the day, all these agents are going to communicate with each other, okay? And this is for the challenge to make sure, and 6G is well positioned there, I mean, in terms of time scale, to take that into account from the very beginning, okay? It could be deployed on 5G Advanced, okay, on the top, but we know that if we want to get that efficient, well, 6G is a perfect framework in terms of timeline, okay? So this is just an example, okay, of this is a digital twin, okay, here to illustrate again, okay, how it was going to work. So you could see Falcon LLM on wheels, which was on the car, and then each roadside unit, then we get his own agent, again, with different capabilities in terms of perception, action, and interaction, okay, so CV2X or on top of it, okay, because we strongly believe in that, okay, in the cellular V2X. Okay, so we see traffic light, for instance. So we don't say it would be everywhere, okay? Okay, we are trying to be practical. This is just a digital twin, so we can play with that. Then, of course, we need to discuss with, of course, with the industry. Okay, does that make sense to put, I mean, this kind of agent everywhere? Or we can use that, okay, on depending on the architecture or more sophisticated, I mean, product. Then this is about productization, okay? The pricing, the bill of material, you know. So, but let's say from a resource perspective, and this is where we can push the boundary, you know, and this is where, through discussion with industry, we can put the limits. Like, well, this is relevant, okay, at this stage, given the maturity of the technology, given the pricing and the revenue, okay, and no need to get these things everywhere. Still, it will be in many places, okay, and we see the advantage in terms of collaboration. And for us, it's even faster, I would say, compared with getting, let's say, the LLM or a large action model on the vehicle, because infrastructure, again, we see the action that we have and nowadays in terms of people releasing small models because people are, you know, the technology is improving, okay? So we don't need any more of the 180 billion parameter, okay, to put that on street light, no way, okay? But we can go, okay, smaller models, more efficient and better, let's say, tuned, okay, for particular actions, okay? And this is where we see the beauty of it. We could deploy that much more efficiently. I just wanted to mention, of course, Neuro, Ghost Autonomy, or Wave, especially Wave, which raised like 1.05 billion US, okay, which means we are not alone in the field, okay, and thanks God, okay, if I may, you know. So there is a lot of traction again with, I mean, LLMs, okay, for and large action models, okay, for this particular area. On the infrastructure side, we like to believe that will be more and more people, okay, to challenge each other and to share the right ideas. And again, to get the traction from the industry there. And speaking, I mean, industry and devices, this is what I mentioned, okay, the new era of AI devices. Again, 6G is very well, it's a very good timing there, okay? We need to make sure that we are progressing in terms of understanding and maturity. But this is our belief, okay, that for the 6G, definitely we get this new kind of devices, okay, so AI-based with large action models. Of course, I mean, you know, I mentioned Andrew Karpathy, sorry for my French accent, okay, with LLMOS, okay, and then we could see that this idea, okay, was pushed again and again by many of the community. The Rabbit Air one, okay, I don't get any share in that, okay, I think it's just a good example for me to say, well, finally, some people are bold enough, at least, okay, to come up on the market with some new devices, okay, I mean, emphasizing getting, let's say, the spotlight of large action models. Okay, and for us, this is what we try to do, humbly. Okay, now to get this approach on, let's say, roadside units, okay, for intelligent transport system, because we think this is, again, safer, and this is faster, okay, to reach that, compared with getting a device which is very generic, that could potentially replace a smartphone. For us, we are focusing, this is still IoT, basically. However, the difference is that this is based on architecture, leveraging the large action models. Okay, so I took, I mean, the example, for instance, of, and thanks Huawei, okay, I think this is from Huawei, okay, the smart poles, okay, where you have so many sensors there and communicating capabilities. And for us, again, we try to see how we can break down, okay, the architecture in terms of software architecture, OS and kernel, okay, to get that kind of flavor for the Rabbit Air one, okay, for smart pole. Okay, that's the intention for us. Okay, so assessing the performance itself in terms of communication, in terms of collaboration. And then once we get that, because we are an applied research center, for us, this is like, well, let's dive into the architecture itself and get this kind of Rabbit Air one, okay, but for outside units of ITS. So another aspect that we are dealing with, of course, this is GenAI for network. And here we are working on a pre-foundation model, okay, for a kind of telecom GPT, okay, with actually some actors in the room here, okay. And then, I mean, to apply it, of course, for wireless communication, we had many examples, and very good example this morning. So very briefly, of course, we are applying that, okay, for meta-surface, I mean, transmissions, okay, RIS, I mean, holographic MIMO. And the whole point for us, again, this is here, it's like, okay, you get these multimodal inputs thanks to perception layers. Okay, you try to steer the beam, okay, the action, okay, thanks to your algorithms, and here large action model. So we see like, well, let's get a LAM MIMO, large action model MIMO, okay, and being ready, okay, for the 6G itself. Cybersecurity, I mean, to almost finish with that. Cybersecurity, you mentioned it, I mean, very clearly, and thanks again. It would be, we get more and more, I mean, vector of attacks, okay, because we get more perception layers, many more devices, you were mentioning that, okay, so more bandwidth for the data rate, so we can get more complex attacks, basically, okay, so more opportunities for vector of attacks. FOTA, SOTA, okay, will definitely there, I mean, massively. So we need to be careful again, okay, regarding the software. And this is what we do, okay, of course, within the cybersecurity unit, we are using, I mean, LLMs, we especially Secure Falcon, okay, for self-healing, so basically self-repairing the software, okay. So this is very important, I mean, project for us, and we get pretty good results and achievements already. And of course, we are not staying that, again, at the model itself, we are implementing that on hardware and see how it behaves, okay, with the right quantization, etc. So we are facing the real world, and that's the whole point, again. But we have very good results, and okay, again, we are pretty happy to share that more, okay, with potential partners. You are mentioning networks. So definitely, okay, I can just agree. So we are working on network intrusion detection systems. Here we get security BERT. It was published, I mean, a couple of months ago. We get more and more results and achievements, again, thanks to hardware implementation. So, and for us, we are pushing the boundaries to see how far we can go with the zero trust approach. So which means how far you can downsize the model, okay, and get it that working good, okay, on very limited performance, I mean, devices, okay. That's the whole point, you know, and so far, so good. And you see the compact size of security BERT, which is quite small, and 16 megabytes, very fast inference time, which is very important as well. So again, this is just the tip of the iceberg, what we do in cybersecurity, but of course, telecom and cybersecurity needs to work together. No need to mention that. If I take very briefly, I mean, the usage scenarios we've had from IMT, we are in ITU, okay. Again, I mean, integrating sensing communication, well, very good for us in the ITS world. Okay, it gives us much more capabilities, okay, in terms of sensing and positioning, for instance. Integrated AI and communication, I think you were mentioning that with the multi-tenancy. I'm glad to hear that, especially when we are dealing with smart city. There are so many different actors. And for us, that's obvious that mobile operators are going to deploy many AI capabilities on the edge. The grid operators with energy, okay, are going to do the same. Transportation as well. So we have seen some partners, okay, which are bringing on the table some solutions like how to distribute the AI, okay, among the different actors, which means you can aggregate these capabilities and then you can share, okay, the load if you need to, well, not only for the inference, but also if you need to train it. And we're also working on federated learning as well, you know. So cyber reasoning, I mentioned that already, okay, in terms of the capabilities and what we need to be prepared for, okay. The last slide, again, this is the momentum which is happening in the UAE. Okay, so I think thanks to Falcon LM, I mean, we managed to get, let's say, on the chessboard of AI. Okay, for the 6G, I like to believe that this is going to happen as well. I mean, we have, you know, for the past 1.5 years, okay, with many partners like California University, Etisalat, okay, we are working together to push a complete 6G ecosystem in the UAE. Okay, I should also mention New York University, Abu Dhabi, okay, for instance. So we get quite a growing and very performing, I believe, I mean, ecosystem in the innovation sector, but also from the industry. So TDRA, which is the regulator in the UAE, they released the first 6G roadmap document earlier this month, okay? And this is just the beginning. So we are working now with a 6G committee, which is going to be set up and officially, I mean, released very soon, okay, and the 6G investment plan, okay, for the complete UAE. Okay, so I like to believe we have to count on us, okay, to reach consensus, of course, in ITU, in 3GPP, okay, at our humble level, okay. So thanks again for your attention.
Thank you so much. I think we will break for lunch, and let's catch up during the lunch. Thank you, and we are back at what time?
So for the lunch, we have a cafeteria in CICG. You can access it on the second floor, if I'm not mistaken. But also you can access the ITU cafeteria using your badge. So you can enter ITU. We have so cafeteria, and also there's some restaurants around. We should be back in an hour. So 10 minutes past 2 is when we are starting the second the session in the afternoon. So thank you and see you after lunch.
Of course. It will be great, yeah.
Recording in progress.
Yes, thank you. Hi, everyone. It's Buse from Turkcell. Today, It's really good to be to have an opening speech of the AI native. Since I'll open the AI native session, my presentation will be centered around what is AI native, why do we need it, and how we're going to reach it. So, but before that, let me briefly introduce who we are. Actually, I'm from Turkcell's R&D team, and Turkcell is one of the largest mobile network operator in Europe. But more than a mobile network operator, we are also describe ourselves as a technology company. So we are working on the different kinds of technologies like the blockchain, AI, IoT. And one of the most important technology for us is AI. And we are using the artificial intelligence for different application in our network right now for the predictive energy saving, smart network planning, network chatbot, and different kinds of application. And the studies, the solution that we developed, actually we awarded by the FutureNet, the Network Sustainability Award for the best intelligent automation solution. So the AI is something really interesting for us, but in order to understand why a mobile network operator is, taking too much time to understand the AI, we need to go a little bit back to understand what is happening in the network itself. Actually, the mobile communication journey started with the 1G, with the analog voice transmission. And with the 2G, as you know, we also started to send the SMS. So the mobile, the phones are started to become more, a tool is using to connecting people more. And after the 3G, when we able to transfer data, the mobile phones are, the definition of the mobile terms in terms of our daily life is changed. And on top of the 3G, we designed the 4G, and the 4G is brings another value, not just connecting the people, but the connecting people to some other universe, that the technological universe, and we call it Internet of Application because it brings another value to the people's side. We are not using the mobile phones anymore just for the calling our friends and colleagues. And on top of the 5G is bring another value onto the table. It started to connect the things, not the people. We are talking about the connection of the IoTs and the vertical applications such as this healthcare, the agriculture. And with the capabilities of the 5G right now, we transfer more data and we connect the different kinds of technological devices with each other. But with the 6G, we are talking something else. We are not talking the connecting of things anymore. We are talking the connection of the agents, the connected intelligence. So after the 6G, we want the AI models, the AI agents to connect themselves and understand and evolve themselves, the self-evolving architecture. So it will be a paradigm shift in terms of the definition of AI for the mobile communication. So in order to more understand why we need AI native in this frame, we need to just dig in the difference between the 5G and 6G. With the 5G, the Vishnu was presented at the beginning of the workshop. We are using the AI for solving the existing problem or enhancing the network performance. And as you already know, the ITU standards, we are using more overlay the architecture. The AI is integrated as a plug-in, a plug externally into the network itself. But when we go to the beyond 5G, we are started to use the AI for more cross-node analysis to coordination between the different nodes of different agents. So we are started to use the AI for more the managing the network nodes. So but still it's just the nodes that we define, the capabilities that we define, but more automated infrastructure. In order to reach the connected intelligence, we say that we need a native AI framework, which is, we don't want the AI be an add-on capability to the network itself. We want the AI will be a native component of the network. So in order for me to explain the AI native more, it's a really good figure that shows what we want to explain when we say AI native. Previously, we used the AI either replacing an existing component, adding a new the capability, or adding some controlling the management platform. But when we say AI native, we want each and every building blocks of the network itself is AI capable, including the AI ML algorithms, and then can connect each other and then evolve each other. So it will bring the different capabilities into the network itself. The network will be tested itself with new configuration without needing any human interruption. It can solve the complex optimization problem, and one of the most important thing, it will adapt and continually learn the new the environment or new problems. But when we explain like this, it's a really the complex problem, and it needs some holistic the approach to solve it, because there are lots of different bottlenecks arises. And today, when we think about the all of the things that we discussed, I just want to highlight the three important, from our perspective, of course, enablers of the native AI that we need to understand, and that we need to integrate it to the 6G architecture. The first one is the generative AI. We listen a really fruitful presentation related to the LLMs and the generative AI. And right now, the generative AI, after the NLP improvements are in our life, and every day everyone is almost using the Gen AI for different applications. But the generative AI right now, of course, is an also evolving technology, and some of the capabilities that generative AI has, or that will be have or integrated in the generative AI, will be really important for the native AI framework development. And I want to highlight the six of them. The first one is the coordination with multiple agents. This is something that we wanted native AI, the framework, because as I said, the different AI agents needs to be seamlessly connected and collaborate into the framework itself in order for us to reach the AI native 6G framework. And the creativity is the important capability that will be really beneficial for us, because the data generation and augmentation is really important, because we want the network is evolve itself. So we need some what if analysis capability with the real data, or a data that is really close to the that has a real world the noise and the real world insights. And the logical reasoning and problem solving is really beneficial for the network optimization and configuration. And the generation novel patterns and categories are really interesting. The capability of the Gen AI will be really important for us, because for the security manner and the anomaly detection, we need to understand the different architecture and the different patterns that can be arised in the network itself. So it will be important for the anomaly detection, which is one a really critical application in the network. The sensory perception will be really beneficial for the future network simulation and testing. And the social and emotion reasoning is critical for creating some personalized services. If we can integrate the Gen AI to understand the customers, the end users, we can dynamically adapt the services and also have a more high accuracy the prediction for the network. So I want to show what we have. For the 6G right now, we are more focusing on the service layer application. So just if we just divide the network in three different section, the physical networks that we have, the physically, and the network function and services, and the management and orchestration. We saw different the architectural framework today, and also there are different architectures discussing. But for the high level, this is something that we're going to discuss in the 6G. So everything with the Gen AI, of course, is not limited with the Gen AI, but the AI-related things, it's we call it the ubiquitous intelligence. So it will be integrated into the network and control and take action using the management and orchestration capability of the network. But from the operator's perspective, it has some bottleneck. If you say, okay, the AI will be directly controlling to the network itself, it is from the implementation perspective, it creates some the problems, because if AI has some wrong decision, it directly affects the network itself. Let's say for the Gen AI, I know it's hard to say accuracy, but let's just say the optimization problem. And if the network, the AI model has a really good performance, 99% accuracy, the 1% determining the variable means that the one city of Turkey will not have any connection anymore. So it's really the problematic for the operational perspective. So we need to have a playground that the native the AI models can test and learn, also not directly touching it, not network itself, and also self-improve themselves. So the Professor Lee made a great presentation about the digital twin. So digital twins are fitting there really well, because digital twin will give us a really good playground that we can use for the network automation, for testing the networks, the AI's decision directly onto digital twin, and understand what will happen if we change the parameters and anything that we're going to do onto the on the network. When we see this, the picture, actually, there was a question previously. Another main problem is the data and the security part, because the 6G, we are talking about the billions of end devices, so lots of data, and the network needs to be fast to adapt themselves and to provide the KPIs, the SLAs seamlessly. So we need to also increase our data processing capability. The Professor Lee mentioning, of course, there will be different the technologies that will be evolved, and one of the promising technology from our perspective is the quantum. When you just go and check the quantum computing roadmap, we see that there's a really good overlapping with the 6G and the quantum computing. And it's the quantum computers has some natural parallelism advantage. So we can use the quantum computers for not all of the computation, but some of the computation in the network to optimize and make a decision using the more the complex data. And also in terms of the energy efficiency, the next generation quantum computers, let's say, it's expected to be way more energy efficient. So when we consider the processing the billions of data, the quantum computers will be also an important role in the energy efficient network automation. So I don't have too much time, but really fast. But of course, there are some limits. For example, one of the limits is scalability and real-time synchronization. Especially digital twin, we need to, when we consider this 6G, we need to have more scalable architecture. And there is one of the bottlenecks when we want to integrate the digital twin into the network. The robustness and reliability, when we consider the Gen AI and other AI models, the robustness and reliability is one of the biggest issue. And security and privacy for the quantum computers, as you already know, right now we are reaching the quantum computers via the cloud infrastructure. So sending the data to the cloud, it creates some security and privacy concerns. And also one of the biggest things is the cooperative functionality, because this is just the couple of enablers, but we will have different kinds of enablers that will be different technical aspect, different bottlenecks. So we need to be sure that their cooperative functionality. So there are lots of different, the solution, again, I'll be really fast, also different solution that the researchers are working on. So I want to directly skip the last part. What we are doing in Turkcell to answer this question, the last year we established our the 6G lab, focusing on the AI native network design for the 6G, and also we are working on the 6G enabling technology that will help us to reach there. We are working on the RAS, the ISAC, the NT, different kind of application, and also the quantum is one of them. The quantum, both the quantum security and computing, is something that we are investigating to integrate it into the future 6G architecture. How we can benefit from them and what kind of different architecture that we can have. For the development part, the digital twin part, this is something that we are actively right now. We are working on creating the digital twin of the service layer of our network. So we are working both national and international researchers. So our aim is creating a virtual replica of our network on the service layer, so we can test, especially the software-defined solution onto the network itself without directly integrating it, and it will be the core of the autonomous network architecture that we are working on in our lab. And the last one is one of the most important part, the cooperative functionality. Of course, the standards are really important for that. We are actively working under the ITUT study group 13, and we are working on to create some new focus group on the AI native networks, because with the 6G right now, of course, we don't have any 6G architecture, but the service-based architecture is one of the most promising the architecture that we have right now, that is the suggested right now. So with the different services and the different kind of technologies integrated in the network itself, we need to work on the overall architecture and how they're gonna connect each other and cooperatively work with each other. So thank you, and sorry for the 5-minute delay.
We would like to thank Buse. We can take one question, but let me just tell you one thing, that Buse is actually co-convener of the correspondence group. In fact, we are fortunate to have both co-conveners here. So Leon is here as well as Buse is here. Thank you so much. One question, please.
Thanks for the very good presentation. You mentioned something in one of the slides that the 1% error can cause an entire city to go out of coverage, which is theoretically true, but at the same time, have you considered the implications on sustainability and energy consumption that would result from pushing to have that extra 1%, right? Does it make sense to have the 99.9% accuracy in terms of energy consumption versus to have 100%?
Yes, the energy consumption is a really good question, actually. The thing that I try to explain is more the KPI optimization, network parameter optimization, the thing that I was talking directly optimizing the network parameter itself. So it can, you know, affect the all of the base station and coverage and everything. But for the energy consumption, of course, you're right. And also we had the previous project, the EU funded project, and right now the internal project, an international project, that we try to integrate the AI-based energy optimization solution. For that, you're definitely right. We previously had that experience that we can, with the integration of the AI, we can create some the 4 and 6% of the energy efficiency. And when you consider a mobile network operator like Turkcell, it's too much. The 4% is not maybe too much, but the application is too much. And right now, for example, for the PSU energy, the optimization that I just briefly showed, but the mobile battery backup estimation and the energy optimization, we are working and integrated right now. We are on the POC the phase with the lower accuracy AI model actually. But when you consider the network architecture optimization, it directly affects all of the connection, not the energy, not the, you know, the sleep mode or not something like that. But for the energy efficiency perspective, you're totally right.
Thank you, Buse. We will, Buse is here this week, so we can catch her for questions. I strongly suggest you quiz her on the activities of the correspondence group. Can I request Frank, please?
Okay. Okay. Hello. Hi to everyone. First of all, I would hate to losing the opportunity of thanking Vishnu, Thomas, all the organization of this amazing event, which every year is getting bigger and bigger, and it's always super great pleasure of being here at ITU headquarters, a very important place. So yeah, I think I made some notes, not to forget anything, but let's go with it, no? So yeah, basically today I wanted to provide an overview on what's going on Wi-Fi in terms of AI/ML. So basically how Wi-Fi standardization has started to deal with AI/ML and what kind of outputs can be derived from this in the future years, in conjunction with all the activities that have been running, like from ITU, 3GPP, ETSI, many other organizations in terms of AI/ML integration into networks. So first of all, quick kind of introduction to Wi-Fi. I think that every time I come to Switzerland, I realize how do I love Wi-Fi, because if I use my cellular kind of subscription, my operator would charge me like 60 euros or something like this. And the thing is that Wi-Fi is a very popular technology. It is in fact the one that is used the most in terms of traffic offloading compared to other wireless technologies. And the value of Wi-Fi is massive, no? In the sense that nowadays we have like more than 21 billion devices in use. So basically Wi-Fi is everywhere. And you know, it's a very interesting technology as well because of its nature, in the sense that it operates in the licensed spectrum, which is free, which is kind of regularly available worldwide. So it's quite of an appealing technology, So yeah, then Wi-Fi, as you know, it's a radio access technology. It defines the MAC and the physical layer. And since its introduction in 1997, it has evolved a lot. It includes many features, and many of them are common to 3GPP radio. But some examples are multi-user MIMO, channel bonding, which is kind of getting channel aggregation, and many other features. And there are not only the features defined in the amendment itself, which are the PHY and the MAC features, but there are also other practicalities, other practical solutions that are defined on top, like what the Wi-Fi Alliance is defining, like to quickly connect to a Wi-Fi network, to creating a mesh out of Wi-Fi. And all of this in conjunction has made Wi-Fi to kind of increase the set of use cases where Wi-Fi is used, going from residential, which is kind of the most important one use case, to now shift into industry as well. So Wi-Fi is also very widely used in industry, and it will continue to be like this in the future. So yeah, and just to provide a bit of context of where Wi-Fi is now and where it's heading to. So basically now Wi-Fi 7, the 11BE standard, was officially released. So we have now Wi-Fi 7 products in the market. And Wi-Fi 8 standardization has also begun. It started last year, and it is going super well in the sense that next year we will have the first draft of the specification. It will be in May, as scheduled. And it will continue adding more and more features. Now we have this multi-link operation, which is the one from Wi-Fi 7 that I would like to highlight in terms of importance. And for Wi-Fi 8, we will have features like related to coordination, which will aim at providing reliability, which is something that Wi-Fi didn't provide in the past. And in all this ecosystem, I think that I can jump directly to here. So basically, in parallel to Wi-Fi 8 pre-standardization, there was the establishment of a topic interest group within 802.11. So basically, the 802.11 working group created kind of a focus group in IEEE terminology. It was a topic interest group to start studying the feasibility and the appealingness of AI for Wi-Fi use cases. Now, this topic interest group is closed. They finished their activities, I think, last year. But the good thing is that this topic interest group became a standing committee, which is kind of a living group that will continue studying the application of AI/ML into Wi-Fi. And more importantly, it will act as a liaison with other SDOs. And this is important because before, in 802.11 standardization, there was no such a thing for AI/ML. And now there is this kind of interface. And this can be very good for Wi-Fi to kind of interact more with ITU, 3GPP, or the SDOs that have been working on AI/ML for quite a long time, like 5-6 years now. And yeah, basically this. So very quickly, the topic interest group, in the end, what they did is generating a report which collected a first set of use cases for AI/ML in Wi-Fi. I will go through them very quickly. I think I can skip them. But basically, there is one that is CSI feedback compression. So basically, for beamforming, you have to send these CSI feedback matrices, which increase a lot in terms of complexity when your MIMO systems increase in terms of spatial streams. And with coordination, it's even worse because you have to share even more information from different access points. No, so one appealing solution, which is also being studied in 3GPP, is CSI feedback matrix compression through deep neural networks or autoencoders, so that you need to send much less data. No, other use cases are kind of enhanced roaming, which aims to use kind of mobility prediction to facilitate the switching from one access point to another. Then there is also kind of deep reinforcement learning based channel access, which is for optimizing the parameters for accessing the channel, because in Wi-Fi the channel access is distributed. It's not like scheduled where you have a base station that tells you when and how to transmit. Here is like random. And finally, there is some other use cases on this coordination that will come in Wi-Fi 8. No? Okay, so now knowing that LJML can be important in Wi-Fi, and knowing as well all the background on LJML for telecommunications, so what can we expect from LJML in Wi-Fi? No, and basically the thing here with this figure is that in the end, standardizing or introducing LJML into communications is quite of a super complex task, because it entails a completely change of paradigm. And we have seen that, no, because it takes a lot of years to define solutions, to define mechanisms, to define kind of signaling. And now there is kind of a change of mind. So basically, we have gone from these overlays now to AI nativeness. Maybe later it's something different. But the thing is that it takes many years, and it's not only how the technology itself is evolving, like Wi-Fi in this case, but how all the different components involved are involved. No? So basically here we have advances in LJML in general. We have standardization of LJML. We have as well LJML in telecommunications in general, like from the activities derived from ITU, 3GPP. And then we have LJML in Wi-Fi. No? And for LJML in Wi-Fi, there might be these three kind of stages that I added here at the bottom. And basically, there is kind of a first stage on early LJML adoption, which is kind of where we are now. And here you can find smart access points or solutions that use some kind of LJML, but from above of the Wi-Fi protocol. No? So basically, it's like for network management or basic self-configuration capabilities. No? Then there is the second stage, which has started, especially thanks, in my opinion, to this creation of the topic interest group. And here there will be kind of interest in, I mean, we have now the interest from standardization that LJML can be something, appealing for the standard. And this may lead to the, let's say, creation or opening of interfaces so that vendor-specific solutions can be deployed on top, like this CSI compression. No, it's a good example, I think. And then in the future, we may have as well AI nativeness, whereby the existing protocols or new ones will be defined if fully oriented or driven by LJML. No, and this entails a kind of new way of creating protocols, no, which is beyond what we have nowadays. No. Yeah, of course, there are the challenges that we all know. Of course, there are challenges that are specific to Wi-Fi, like this backwards compatibility. In Wi-Fi, you need to be compatible with the previous generation and the previous generation and so on. So this is kind of a very specific challenge for Wi-Fi. And the enablers, I would say that the work done so far in terms of defining LJML-aware infrastructure for telecommunications, start thinking about trust or in LJML and so on, is very good for this. Okay, so the interesting part, no? So now what? Basically, first of all, the first question that we should make to ourselves is how AIML can be, of greatest benefit to Wi-Fi, no? And I think that the answer is a bit obvious, because Wi-Fi's main problem is the lack of reliability, and this stems from its nature, in the sense that it is a kind of free of use technology. You need to have this kind of fair channel access, which is the basis of everything. And this makes the technology to be a bit unreliable in certain situations. So basically, I would say that any feature, any functionality in terms of AI/ML that can provide determinism, ergo reliability, would be a very positive one and very well adopted. Sorry. Then I wanted to show you kind of a use case about how the different phases of adoption of AI/ML could have a good impact or potential benefit to Wi-Fi. The good thing is that we collect all this in a paper, so I will refer to you to the paper so that I can skip this part and keep the presentation shorter. So, but basically we showed a bit what was the advantage, no, of this transition from kind of solutions that operate on top of what is built, and going a bit beyond and doing something that is has more flexibility in terms of tuning parameters or stuff like this. And yeah, this brings me to the last slide. I think I don't have anything else, but basically my takeaway is that now is the time to really develop these tailored solutions, specific features, mechanisms using AI/ML for Wi-Fi kind of protocols. And the thing here is that you need to prove that this is working, and you don't need to show performance gains, but also feasibility in terms of, does the solution that you propose fit into the firmware? How much computation does this need compared to what is being done today? I mean, if you have a function or whatever there that is doing the job that you want to improve, so you need to kind of measure these kind of things, no? Then, yeah, of course, I think here there is a big gap in terms of simulators, because typically you use standard compliant simulators to prove that the feature that you would like to propose is working well. But in terms of AI/ML, we were a bit behind, no? So basically, there should be more effort in that direction. Then I also understand that there is a huge opportunity here for Wi-Fi to collaborate with other technologies like cellular, because the target is AI/ML in the end, which is a kind of general purpose technology. And there are many similarities in Wi-Fi 3GPP, so that one technology could learn from the other, no? So I think that this should be kind of in collaboration, which is something that today isn't happening. But in the end, if cellular, for instance, wants to use the licensed spectrum, which is the case, and Wi-Fi is the king of the license in a sense. So I think that the learnings from Wi-Fi community to cellular would be beneficial, and the other way around, no? Wi-Fi is also including kind of a scheduled type of transmissions, and their cellular obviously is the king, no? So I think it's a two-sided collaboration that should be kind of fostered. And yeah, maybe last thing, which is a bit of guideline of what to do once you have kind of defined the feature, AI/ML feature that is kind of appealing and feasible, you have proved that. So basically, what are the steps then in a standardization that should be taken? So basically, you need to consider a few things. One is, in my opinion, how do you want to shape this model in terms of inputs, in terms of outputs, so that you derive what are the capabilities that the standard needs to extend. So basically, here the less you touch, the better. But obviously, you need to think about this. Then there is the question of how do you train and use the models for inference, for instance. So here the data collection or the capabilities for collecting data are very important. And finally, how do you test and audit these models? No, and in this sense, I think that there should be kind of a standardized procedures, like for standardizing data sets. You may think of I don't know, kind of a stable data set that you use to validate that a given model is not behaving crazily, so that the output is kind of bounded. But basically this, there should be also kind of standardized mechanisms for doing this test of LJML solutions. And maybe this is not purely for 8.2.11, but it can scale up to Wi-Fi Alliance, which is the entity that is actually certifying Wi-Fi products, and so on. If we also have a tutorial that we kind of do or deliver at conferences. We have all the materials online. So if you have interest in the topic, you will find much more there. We also have kind of code and stuff there. And that's it. So many thanks for the attention. I think I overpassed the time.
Thank you so much, Frank. Actually, I was trying to take without Frank knowing his picture of his notes. He has a very, very nice set of notes. that looks very nice. You should get a copy of that. But one question, please. Anybody has one question? Yeah.
Hi, thank you for the presentation. I was wondering what are from your side the specificity of Wi-Fi with respect to the cellular network when looking at this topic?
I would say that the main difference is the channel access. So basically in Wi-Fi you have a distributed one, and things are a bit more chaotic. You don't have interference kind of management in the same way that you have it in cellular. So here it's more about how do you grant the access to the channel to different devices. And so far this is kind of too protective in Wi-Fi, so that you don't generate mess between transmissions. But there is much more that you can exploit. The problem is that you don't know from your point of view if you're a transmitter. So using LJML to kind of infer what's going on and act accordingly could have kind of good potential, I would say.
This is also maybe a challenge for implementing AIML on Wi-Fi?
It is a challenge, of course, but at the same time, it's the opportunity, because otherwise we would do the same that cellular does. So we shouldn't then do anything. Everything is done. But yeah, I think it's more an opportunity, but of course, it's a challenging one. Many thanks. Please, Paul.
Thanks for the presentation. I don't dispute what you're doing, by the way. I'm just trying to spark a conversation. So if you take 11.11ax, that's scheduled. So to me, that's very similar to cellular, right? Already.
Yes, I appreciate this a lot, Paul. Thank you. So basically in 11ax, Wi-Fi 6, they introduced OFDMA, which is for uplink transmissions only, in the sense that the access point schedules the users to use the OFDMA resources for the upcoming transmissions. But you still have the interaction with other networks, with the other networking networks in OVSS. So in the end, you are kind of condemned to the distributed channel access. It's like part of it.
Okay, so my second question is, So then I understand there is an appeal to use ML because you want to solve, you have mostly a distributed access channel access, and you want to use ML to kind of preempt those problems. But then don't you have another challenge now, because now you need to run ML at the device side, and you might have computational capability limitations.
That's true. But I mean, the same happens with, I mean, here there are these few use cases which are very high level, but in the end you could think about any type of integration. There is also the AI native air interface that has been kind of proposed for cellular a lot, and which you could use here as well. No? But if you take a look at the different kind of use cases, there are different requirements and different kind of deployment options. Some of these options include or need for the participation of the station, which has this kind of limitations in terms of computation, storage, and so on. And this is indeed a challenge, and I think that it hasn't been explored enough so far, at least when defining these use cases here. Yeah.
Okay, thank you.
Thank you very much, Frank. Okay, we have Lina waiting. So yeah, we will go to the next next presentation with Lina. Yeah.
Okay.
Okay.
Yeah,
Yeah, I can. All right, so good afternoon, everyone. I'm Lina Berria, a lead AI scientist at Open Innovation AI, and I'm more a telecom engineer with some background on AI, and I'm recently focusing on exploring how large language models or large-scale AI can be integrated into telecom network, particularly for RAN. So I will not take much time, maybe maximum 15 minutes. But I would like to give you more into a landscape and a vision of how AI evolved with RAN, starting from the first generation to the fifth generation, and then to the sixth generation. And at the same time, maybe discussing more about what are the directions that we need to pursue in order to ensure a reliable implementation of large-scale AI in RAN. Okay, so AI in RAN is not new. However, we are seeing this hype, or this is spread of large-scale AI happening in the last few years, and definitely AI and its RAN and its operations is an important application and use case for large-scale AI. And this is for several reasons that I will be discussing in a few minutes. But let's first discuss why this happened recently and why we have this large-scale AI just over the last few years. So in fact, this evolution in large-scale AI is a result of the evolution of computing. So early machine learning era, around 2010 or before that, relied primarily on CPU-based computing, which have limited processing capabilities, computing power, and they are incapable of handling the complexity of large-scale AI that we are having these days. They had some applications and some use cases. However, their real-world impact were limited due to the limitations in the computing. And then the shift happened to more GPU and TPU-based computing, where we witnessed more advanced applications like AlphaGo. And actually, the use of these GPUs and TPUs accelerated
the training of neural networks and enable these advanced applications. And then the transformative era happened around 2019 or 2020, where supercomputers appeared with their unique parallel processing capabilities. And they enabled a lot of applications around natural language processing. And this was reflected with the emergence of this large language models that we started to see starting 2019 until today. Every day we wake up with a new model, including the Falcon of Technology Innovation Institute. And we expect these models also to see new models in the coming few years. For those who don't know large language models, which I doubt it, I think everyone is aware of it, but just a quick definition, there are unique AI systems that enjoy large sizes and are trained over a large amount of data sets using a huge amount of computing. So going back to the context of RAN and how it evolved from voice-centric around 1G and 2G into more data-driven networks around 3G and 4G. And then around 5G, we had a massive networks of connectivity where the Internet of Things actually took place. And then, of course, with this evolution between 1G, 2G, 3G up to 5G, we also witnessed a huge development in terms of data rates, reliability, latency, and so on. But what we are expecting to see in 6G is more about ubiquitous intelligence or AI native networks. So AI has been there. As we can see here, it started around the second generation, but it started in a very simple way where we had rule-based systems with simple algorithm, with very simple applications, including traffic predictions or simple network management tasks. And then it evolved into machine learning or deep learning based algorithms with more advanced tasks around load balancing, traffic management, and so on. But what we expect to see in 6G, it's much more than having modules that are intelligent, but to have ubiquitous intelligence that is the fabric of the network itself. So to see more, let's say, generalist, inclusive AI in telecom networks, and definitely in RAN. So okay. And why we envision to see large scale, particularly in RAN in future, is as RAN is evolving over the last couple of years, we see a huge increase in their complexity and their operations. The massive connectivity with all these elements and parameters, it requires more than the conventional AI that we are having these days. So in order to achieve the full autonomy in RAN that we are looking for, which means that end-to-end automation without any human intervention in between, conventional AI will not work. And that's why we will resort to more large-scale AI or large-scale generative AI. If we look to the timeline here, the development of more self-driven or autonomous networks that we have been talking about since the beginning, we can see that it emerged from fully manual configuration setup and reactive networks that do not do any actions until triggered by a particular flag or error in the network, into more AI-based networks in which network optimization and configuration is achieved through AI agents, which continuously interact with the environment, adapt, and evolve. But what we are looking for is not networks that are driven by learning, but more about networks that learn by themselves. They can self-organize, they can self-heal, they can self-reconfigure, and so on. And this is what we are currently referring to more self-driven networks or intent-based networking. So having a look to the global landscape of RAN. So the vision of having AI in RAN is verified by this study for the global market of AI in RAN, which is rapidly expanding with the market expected to grow at an annual rate of 45% by 2028. So within 4 years roughly, or 4 years now, we expect the market of AI in RAN to grow by 45%, and particularly for the application of traffic optimization. The application of traffic optimization, we expect to see a compound annual growth rate by roughly 32% within the same period. And this is indeed will drive a huge wave of innovation in AI and RAN. So again, why large-scale AI or large-scale generative AI? Why not conventional AI? Now, large-scale generative AI have several unique capabilities that make them appealing for the operations of RAN and for automating RAN. So among of these several capabilities, which is starting with their generative capabilities, definitely, because there will be always a need to generate some content, and these generative models are the optimal solution in order to generate this content. But apart from this, one of the most appealing, let's say, properties of these or characteristics of these large-scale generative AI is their capability to, or their generalizability capability, which means they are capable of extrapolating outside the training data set, which means that it will be, or it will provide more adaptive frameworks for all network changes. So even if there is a scenario that's not experienced or represented by a data set, these models will still be able to perform reliably. And another appealing also characteristics of these models is that these large-scale LLMs, large-scale AI models, are considered super compressors. And this is very essential when we are talking about employing AI and everything in our network. So what does this mean? It means that instead of transmitting the whole message that we are looking to exchange between two nodes, we can transmit a much smaller message that can be constrained by a prompt. And then if the two nodes are sharing the same knowledge base, then the other node will be able to regenerate and recreate the message that was intended to be sent. And this is definitely in RAN will be very resource efficient. So when we integrate large generative AI in RAN, what we are looking for is introducing signal intelligence. So when we're talking about having in AI in the past with RAN operations, we're talking about having more adaptive schemes. So we need adaptive modulation, adaptive coding, and so on. But when we integrate large generative AI into RAN, and in order to enable signal intelligence in the way that we are looking for developing more of emergent modulation schemes, emergent coding schemes that can adapt and that can change based on the network scenarios. And definitely introducing this intelligence to the spectrum, to the nodes themselves, to the signals, and everywhere in the RAN operations. But are large language models what we are really looking for in RAN? Now, this is the initial vision that we have been discussing so far with large-scale generative AI. And when I'm talking here about large language models, it's not only language models, so it's incorporating multimodality, including all network language. But is it enough to realize the full automation that we are looking for in RAN through using these large language models? The answer is no. It requires much more than large models that are general and that can create content and that can understand. And there is several reasons why these large language models are not only the future for full autonomy and RAN. So the first thing is the reasoning capabilities of large language models are basically limited. While they showed some reasoning, let's say, skills, but they are limited, and it was shown that these are not sufficient to take decisions in complex scenarios. And when we are talking about RAN and the massive number of nodes that are connected and need to be operated, the number of transmitted signals, the number of parameters to be configured in the RAN, large language models by themselves cannot provide the needed reasoning and thinking that will lead to an informed decision-making. So large language models in this sense will fall short of achieving this vision. Also, functional competence is an issue. So large language models, for them to reliably perform a variety of tasks within RAN, they need to have more, let's say, domain-specific knowledge, which is these general LLMs do not have. And finally, which is the main point here, or the important point, is that large language models are not capable of translating their insights into actionable steps. So they are not capable of implementing these actions, or not capable of integrating or performing these tasks once the decision is made. And this definitely limits the vision of full autonomy when we are talking about RAN, because we don't want only to take the decisions, but we want the machines also to implement these decisions, and then to monitor the network after that, and to see if that decision was the correct one, and then to self-reconfigure, self-reheal, and so on. So what is next? Or what is in addition to LLMs? Because LLMs will be there, their capabilities are important, but there should be definitely additional technologies that should complement large language models in order to achieve the full autonomy in RAN. So I guess everyone heard about large action models, and thanks to Thierry for introducing this earlier before lunch. So everyone started to talk about large action models, these models that can implement actions, that can use your application instead of you, and these all capabilities beyond only content generation. So large action models are built upon the base of large language models, in the sense that they are large models trained over a huge amount of data set, but they take this a step further, which is implementing these actions. And if we see also the market study here, it's mentioned that by 2028, 1/3 of interactions with generative AI services will use action models and autonomous agents for task completions. And this period is in line with the evolution of AI in RAN. So by 2028, we envision the blooming of AI in RAN. At the same time, 1/3 of these AI will be action models and autonomous agents, which confirms the vision that in order to realize the full autonomy and to realize the performance that we require from RAN, large action models should be there. So as we can see here and the diagram here, large language models are still here, and it constitutes the core of large action models, where it's needed for intent recognition, for generation purposes. So if we envision it in this way, we have the query coming from the network. And for a RAN agent, first, it requires an LLM to understand the RAN language. So we need initially a RAN language model, and then we need a reasoning module that is capable of converting the tasks by the LLM into multiple subtasks that can be achieved by different agents. And then according to the outcome from these agents, the action will be specified and implemented directly to the network. So here are some examples of what kind of actions that can be taken through a large action model when we have different types of data or RAN data. So starting with network logs, using an action model, we expect the model to not only to recommend the optimum threshold for handover, but actually to adjust that threshold. Not to recommend the optimum frequency allocation scheme, but to implement this scheme, to optimize the routing path. If we have configuration files, if any deviation happened in this configuration of the network, we expect the action model to identify this deviation and then to fix or to adjust these readings. The same for technical documentation, incident reports, and traffic data. While traffic data also, it includes both, not only textual data, but still we expect the large action model to understand this. And this is one of the important things that need to be considered when implementing large-scale AI within RAN, is to develop the architectures that are capable of handling the RAN data, including textual data as well as traffic data. So the action model can do some bandwidth reallocation, edge caching, a traffic shaping policy. So to recommend at the same time to implement these ones. And definitely large language models here will stay in the picture. So out of these all configurations, all this data that we have from the network, we expect the large language model also to get some insights, to summarize, to generate some reports. So it will complement the large action models. So large action models will eventually lead to the emergence or to the, let's say, bloom, because they are already there, of autonomous AI agents. So if the LAM will constitute the brain, we consider these autonomous agents more as the operational tools that will act, react, and interact with the environment. They will be responsible for perceiving the data from the environment. And then based on the action or the decision taken by these models, they will implement these actions back to the network. And that's why it's important to ensure that these agents are grounded in the real environment. So they are perceiving the real environment, they are perceiving multi-sensory data from the environment in order to perform an informed decision-making. So finally, I will just be highlighting a few points, which referring it can be like more into the skills that these agents will need in order to realize full autonomy in these RANs. But also it is considered as different research directions or directions that we need to pursue in order to ensure the good implementation of these agents in RAN. So the first one, as I mentioned, the multimodality. All large action, let's say, large language models currently are based on textual data, some on visual data. But so far, we don't have the models that will be capable of handling traffic data or RF data. So developing these models, because these agents will need to understand this data, will need to generate this data. So we need to develop such a framework where multimodality that is suitable for RAN can be accommodated by these autonomous agents. The second one, which is also important and related to generation, is seeing agents as programmers. I already started to see some frameworks around developing large language models as software and as programmers. I don't recall all the names, but Devin is one of the ones that I went through. And basically, this is very important because when we need to implement an action into the network, it's basically generating a code. So having these agents capable of generating the needed code in different languages is essential in order to implement these actions back into the network. Definitely, we'll need efficient interfaces. We need to work on building these interfaces between the different nodes, between the agent and the environment, between the multiple agents. And finally, developing more agents as optimizers, because current LLMs cannot do optimization. And when we are talking about RAN, there is a huge amount of optimization that needs to be done with a huge amount of data sets, sometimes with even multiple objectives, with a lot of constraints. So in order to also automate this part of RAN, we need to enable these agents to work as optimizers. And in this way, we can go into two directions. The first one, either the conventional one of fine-tuning over optimization data sets, which is not very promising and not, let's say, scalable. The other way is to go more into collaborative agents or collaborative radios, where we integrate multiple agents that have generative capabilities in order to interact with each other's and to solve particular optimization problem. And the aim here is to develop this framework in a way that these agents can converge quickly to solve or to find the optimum solution, regardless of how many parameters we have or how many objectives we have. And that's the end of my presentation, and thank you.
Thank you very much. Anybody has, yeah, please.
Thank you very much for the excellent presentation. I have a question on the slide. Sorry, they were not numbered, so I don't know which one, but it's the slide where you had all the this one, exactly.
Okay.
No, the next one? Yes.
This one.
That is very insightful to me. And what I wanted to ask you is, I think I got the rationale behind proposing the large action models, and here you have a set of situations where actually this could work. I wanted to ask you if you could elaborate a bit more on which one of these use cases or blocks, let's say, may really need this large action, and which ones actually the large action model could not provide such a gain. For instance, my attention was going to the first block on the left when you were mentioning adjusting and over thresholds. So there is plenty of optimization problems relating to mobility, for instance, where actually intuitively I would assume that the action space is not that wide. So if you need to tell about these 15 blocks, are there some where you tell the large action is really providing an edge, and some other where we could live without?
Okay, while still being an early topic of study, but in my opinion is more about having this reconfigurability capabilities of a network. So whenever you have any deviation in the network configuration, these large action models can adjust these deviations. But it's not also about one block. It's about having a large action model that can perform the full autonomy regardless of what the use case we have. So we don't want to implement large action models for particular scenarios, and then for other scenarios we need human intervention. So when we are talking about using large action models to provide end-to-end autonomy, we envision that large action models will do all these use cases in order to prevent any human intervention or to have it more autonomous networks. Yes.
Yeah, thanks for the presentation. I have two mini questions, right? So they're related to each other. The first one is, when we say large action models, first, is it a necessity to actually have these models rely on language? That's one thing. And depending on the answer, if we say no, then probably they're not going to be large, because the reason why we have large models is because of the vast interrelation between words in a given language or multi-language. So if we take the language out of the equation, we can reduce the size of a large model into a normal model. So the question here is that, do we really need to have language dependency in our models? And if no, then would we really have large models, or would they reduce significantly in size?
Okay, so it's two ways. Language is still in the equation, but also other languages. So when we're talking about automating these networks, we don't want only the large action model to understand, for example, textual data, but we expect it to understand the configuration of the network, the traffic data, the RF, the readings of all signals. So it should read textual data, because out of these data, input data, we still have textual data. So we have around these ones, the technical documentation, the standardization documents that are essential for the model to understand in order to implement the right policy. But at the same time, there should be other kind of languages. And when we're talking also about large, it's not about also or only having a language. Now, the notion of having a large model is to have it more a generalizable one, and more a model that can extrapolate. So that's the notion of having it large, but still we have both languages or different kinds of, let's say, modality than languages.
The reason why, because Marwan often talked about these large telecom models, right? And the idea was, would these large telecom models actually be language dependent? Is it a necessity to have language in the equation? Because like you said, it's the way we have a common denominator for data input. And if language is there, do we need to capture the contextual relations between words in a language, as we have to do with ChatGPT that is generalized, or any other open large language models that is generalized for language use?
Definitely, because these are all parameters that play a role in the decision making. So when you are having a decision for any of these actions, it should be based on these parameters that are in the log of the network or the technical documentation and so on. So it should understand the overall context in order to perform this task.
Thank you.
Colleagues, Paul, can I
piggyback on that?
Oh, yeah, sure.
Because I think there was a really good point being raised there. So if you look at large language models, you train them on some huge corpora, right? Whereas if you look at network documentation, logs, and so on, that's a highly unstructured and heterogeneous data.
Okay.
So maybe training a large language model is a bit of a stretch, because if you look at, okay, let's take, okay, you take a book and it's translated in I don't know how many languages, and then you can learn across different languages, so you can do all sorts of multimodal in a way learning. But is that feasible here, or is it more of maybe the approach is like, why don't we go back and revisit how we did SON, which was broken and it never worked, and maybe that's something that we can do better now that we have better tools. I don't know what you think.
Yeah, this is actually still, that's what I mentioned. We still don't have these architectures that can deal with this kind of data of, let's say, network data, I would say in general, because of the difficult nature of this data. So this is yet to be studied and understood, but this doesn't like deny the fact that still it has a lot of potential and promising capabilities that can be introduced into automating these networks.
Let's say it's a subject for coffee. Can I please, I mean, if there is something left there, that's a different matter. Thank you, Lena. Thank you. Can I request, yeah, Lucian, please.
Hello, everyone, and thank you, Vishnu, for having me here. Today, I'm gonna approach a topic which none of the other speakers spoke to depth about, which is efficiency in the implementation of these AI models and the AI native approach. So, if we are to have native AI as a sort of pervasive AI approach where the AI components are everywhere in the network, and obviously the components will also be somewhere at the edge in our networking components. So this means they have to be efficient. There is no two ways about it. They have to meet specific requirements that are the requirements derived from the parameters of the network itself. And therefore, we have to make sure that the AI component does not slow the system down, does not introduce power constraints, or does not take us over power constraints, and so on and so forth. So my talk is about AMD's research in and specific tools that we have developed for deploying AI-based real-time network security solutions to FPGA. In this particular case, although some of the tools here are applicable to other types of computational fabrics that can be used to execute AI functionality. So I'm giving this talk on behalf of a team of brilliant people in AMD and my laboratory. This is called the Integrated Communication and AI Lab. It was established as part of Xilinx research, so there comes the focus on FPGAs. But we have been merged into AI research recently from the acquisition of Xilinx by AMD. We have a large number of researchers working on a equally large number of research topics across many different locations. But generally, our focus is on AI applied to and serving communications. And our approach is hands-on and end-to-end. So we do architectural exploration, benchmarking, optimization, and so on, either internally or in close collaboration with partners in academia and also in industry. So please come talk to me after this presentation if any of the technologies here are interesting to you. And also, if you're a student, we have an active research internship program. We can integrate you with a number of different topics that are going on. So let's get to the presentation. And I would just want to say from the outset, I'm not referring today to large language models or any of the AI approaches that are being served successfully by the data center right now. So ChatGPT, image generation recommenders, all of these are applications which are served just fine by the cloud. But I'm talking about the long tail of applications where the cloud can't be the source of computation. So in communications, in the medical space, aerospace, IoT, specifically, you have to have computation at the edge if you want to do AI on it. So therefore, my talk will focus on this long tail. And this long tail of edge AI applications, which includes network security, comes with a new set of requirements. Right, so we usually worry about power, performance in terms of throughput, latency, and jitter, and so on. We worry about costs, of course. We worry about accuracy, but with the move to the edge, we start to worry about new things such as the I/O footprint, temperature ranges, and so on, which come back to power, but come back to the delivery of power specifically, the functional safety, and so on. So we need to solve a larger set of constraints, and we need to solve them very efficiently. Now, in the space of communications, more precisely, you kind of inherit the requirements of the data path of your network device. So let's say if you are to deploy some artificial intelligence in a network interface card, then you kind of you inherit the throughput requirements of that card. You have to, if you want to look at all of the packets, then of course you have to be able to do 100 million inferences per second if that's your maximum packet rate. If you want to ingest all of the data that comes in to make a decision, then you have to ingest multiples of hundreds of gigabits per second for a recent Ethernet. And of course, you have to do this with low latency. You can't simply take some data away from the network, crunch it, and take your time, and then come back, because that means your packet that's being decided on needs to sit in a buffer for God knows how many milliseconds, and the data accumulates, and therefore you have to then start back pressuring the network, or your buffer becomes too large to be economically feasible, right? So all of these are very important constraints when looking at network systems specifically, and especially if you're talking about network security, because then you have to look at packets as they come in. You have to make decisions quickly to mitigate against an attack, and therefore you simply can't take the time to do this processing offline. And of course, in wireless especially, there are opportunities to fuse AI with the signal processing and lower protocol layers. That is not something that I'll touch upon today, but we are interested in that research topic. And we couple this expanded set of requirements with challenging dynamics coming from the AI space itself, right? AI is not a solved problem. Every single day, new algorithms come up. We used to do MLPs before, then we moved to CNNs. Now vision transformers are being used for image classification. God knows what will be next. And also data types are constantly in flux. AI started on FP32, now we're moving into int8, block floats, smaller floats, and so on. So you have to always keep an eye on what's happening, so that when you deploy an application with AI in it, it doesn't come out to market being 2 years behind the curve. Right, so this creates kind of a very challenging task for the people in your organization doing solution specialization. What you want is you want to meet this very strict set of requirements, and that means you probably want to build a specialized compute fabric for it, right? And maybe that means an ASIC for that specific product. But then you start from a specific algorithm and a specific data type, let's say. You start building your product for that, and then a few months down the road, everything changes, right? Let's say you started with a ResNet 50 and int8 as your parameters. Now vision transformers are the state of the art with FP8. You have a decision to make, right? You go down to the end of the waterfall and have a product that will not be state of the art, or you start over. But if you start over, this can happen again, right? You might never reach the end of the waterfall. So what you really need is a way to compress this development time, and you need tools to do that. And this is what I'll be presenting today in the rest of the talk. I'll first kind of focus this discussion into AI-based network security, which is for which I will present some use cases at the end of the talk. So again, other people have made the point before me. I don't need to make the point again. AI-based network security is happening and will be in products in the future. And actually, it is in products right now. There are several ML-based firewalls on the market right now, and we expect many more to follow. And generally speaking, the firewall solutions that have been deployed so far take these kinds of two forms, one of these two forms. Either they are flow-based and they look at packets as they move through a network interface card. They might look at the core header and derive a classification from that, but more complex ones also look at header options, which is a variable size data, flow characteristics generally, and so on. And this helps you take a decision without looking at the data. And the decision might be, for example, if you detect distributed denial of service attack, you might drop the packets or do any of the sorts of modifications to the flow that Jose has talked about before. So that's without looking at the data again. And if you want to look at the data, that's called deep packet inspection. You want to look at the payload. That makes everything more complicated, not conceptually, but practically, because the packet payload is variable in size by its nature. It can be fragmented into multiple packets, so you have to reassemble. It might be encrypted, so now you have to be part of a trusted domain with your firewall, and so all of that is extra challenging. Now, from the point of view of how an architecture to do this computing looks like with AI embedded in it, here we have a network interface card with the AI component for network security specifically. So we have data coming in from the ingress interface. It goes into a header processing component, which extracts specific information that is relevant for the classifier. It might also go into a flow status manager, which also extracts some other information, and all of that goes into this feature vector, which then acts as the input for our DNN-based malware classifier. And this, of course, needs to provide a decision for that particular packet. Do I pass it on into the rest of the NIC, or do I drop it right here? And of course, the rest of the NIC is just the same as usual. There doesn't have to be any additional intelligence there. But what matters here for the classifier is the time it takes for it to deliver this decision. Because while it's doing work, as you can see, the payload is sitting in this buffer. So if it sits for too long, the buffer fills, you back pressure the network, you start dropping, you lose your throughput. Of course, for deep packet inspection, the picture looks pretty much the same, except that we have this additional input from the payload. Typically, what you do is you will do some encoding on it and then use potentially even a separate DNN to do fingerprinting of that data. And then that turns into a separate feature that you add to all of the others. And then you go into the malware classifier as before. So conceptually not different. But there's much more work to be done here, right? So maybe if you were capable of doing the previous one in real time, this is unlikely to happen unless you pay a lot of attention to it. So then the rest of the talk will be about tools that we provide and work that we have done to kind of ensure that these types of systems are deployable and can act in real time on network security threats by inspecting packets in a network interface card. So let's start by looking at three aspects that we believe are important in the efficient implementation of embedded AI for cybersecurity. So there are three layers here, starting from the bottom and going up. First of all, you have to make sure that you're utilizing an adaptive computing fabric, which you can change, into which you can change the algorithm if that algorithm evolves. Like I said before, you don't want to rely on something that is hard-coded and baked in for some specific AI algorithm that you think is state-of-the-art now, because state-of-the-art will change. So you need an adaptive computing fabric, and for us, in our laboratory, that is code for field programmable gate arrays. The next layer up is being able to build customized and specialized compute architectures to achieve the specific performance requirements that you have in your application. And then on top of that is providing the automation required in the deployment flow to keep up with the agility of the AI stack on top. So you want to be able to quickly take some new development at the AI stack level, some new algorithms, some new operator, and then convert that quickly into an FPGA image that you can program into your device. So we have two open source tools to help with that. Those are Brevitas and Fin, which are illustrated here. Brevitas is a tool for neural network quantization, and Fin is a compiler from PyTorch and Onyx down into FPGA bitstream. And I will talk about them in the rest of the presentation. So first of all, let's start with a primer for those of you that don't know what FPGAs are. FPGAs are sort of the chameleon amongst the semiconductors. They are almost an ASIC. They are almost a hard-coded solution, but they are flexible enough to be changed after deployment. So what you get with an FPGA is the speed, almost the speed of an ASIC, but you get the ability to reprogram the functionality in it if the functionality needs to change. Of course, what you can change in the FPGA is the configuration of the sea of programmable lookup tables that you see here, the configuration of a number of digital signal processors that are embedded within the lookup tables, and also contents and functionality of embedded memories. So all of this provides a good substrate on which to implement AI accelerators. But the key point that I want to make here is that FPGA is a compute fabric. It is not an accelerator in the sense that a GPU is an accelerator. You can implement, let's say, a GPU compute unit inside of an FPGA, but that is kind of a specific choice that you make, and you have chosen an architecture and you've implemented on FPGA. And the key challenge is to find what is the best architecture for an accelerator to implement in the FPGA to get your efficiency. So again, coming to the two tools that I described before, what we provide is an end-to-end flow from the neural network to an FPGA bitstream that will help you find this correct architecture and will help you find the correct parameterization of your neural network to be able to get your efficient AI implementation. And a general schematic of it is illustrated here. I'll come back to this in a few minutes. So then let's go to how to build these customized hardware execution architectures for neural network acceleration. There are three key concepts here that I want to touch on. So we first start with topology specialized custom data flow. Now, if you have deployed a neural network on a CPU or a GPU, you probably understand that the GPU is not constructed to execute that specific neural network, right? It is constructed to execute any neural network. So that means it is super flexible. It will execute whatever you throw at it, but it also has limits to its efficiency because naturally it is not very specialized to the specific neural network that you want. Data flow means specializing for individual topologies. It means changing the structure of the FPGA to reflect your neural network, not any neural network. So that means the hardware instantiates the topology as a data flow architecture. So this is your neural network as represented, let's say in PyTorch. It has several layers that connect to each other. This is exactly how your accelerator will look like. Then you customize everything to the specifics of the given DNN, the operations and the connectivity itself. So just like layer 1 feeds into layer 2, feeds into layer 3, and so on. So the first sub-accelerator will feed into the second, will feed into the third, etc. And additionally, if some particular layer requires more compute to execute in a specific amount of time, then you will be able to allocate more compute resources to it such that it can meet its deadlines. And that's very important in the sense that the data flow must be rate matched. All of the layers have to execute in the same deadlines. And this allows you to be lower latency, higher efficiency, and higher throughput. So the way that it works then is, let's say you have some data, you push it into the first accelerator, and then it never goes out of the FPGA until you have final results. And that means you don't exercise I/O. It means you can get away without much I/O if you don't actually need external memory for something else, and you get the results very quickly. Now, an additional benefit is that you get an architecture which is scalable to the limits of your device. So let's say you need 100,000 inferences per second, then you can fold, this is the term that we use, you can allocate a specific number of resources to each of these sub-accelerators in the data flow so that they finish in such time that overall you get 100,000 inferences per second. And that might mean you only need 1,000 LUTs. That means the smallest FPGA device will be sufficient for your use case. It'll be cheap, it'll be very efficient. But then if you move to a different application, let's say you're at CERN and you're trying to classify collisions in the accelerator and figure out what type of particle they are, right? That means you will need 100 million inferences per second. That means you will have to scale up to let's say 1 million LUTs. You will need a large FPGA, but it is doable with the same architecture. There is nothing changed here. It's the same accelerators connected the same way, except that I have allocated more resources to each of these accelerators such that they can do more operations in parallel. So that's an advantage. It means that you don't need to redesign for every new set of constraints with regards to throughput and latency. You can simply scale up and down one data flow. And the way that you do it without having to be an expert in all of these things is by using the FIN compiler, which is a modular graph compiler with well-defined abstraction levels. It absorbs ONNX representations of neural networks, and it transforms them into a data flow style FPGA deployed neural network accelerator. It also, on the way, it performs several optimizations, layer fusion, and so on. But that doesn't have to concern you as the user. It has its own heuristics, it has its own optimization passes like any compiler. And what you get at the end is simply an FPGA bit stream that you can deploy in your target FPGA. So that makes design much easier. It makes it accessible to people that are not FPGA experts, but are perhaps domain experts. Physicists have used this to good effect, and I expect people in your research community will be able to do so as well. What we use as a basis for this data flow is a library of parameterizable kernels. I won't go into too much details, but this is a simple C++ library that can then be compiled to FPGA logic, and it's understandable for anybody that has written C++ in their career. So you don't have to understand VHDL or Verilog to be able to debug the outputs of FIN, for example. Now, moving onwards, the next step is taking advantage of quantization. Of course, data flow is fine. It provides some advantages. But if you try to deploy a single precision floating point neural network accelerator to an FPGA, you won't get very far. So what we already know is that going to smaller precision provides massive benefits in terms of efficiency and performance. What you can get by combining the concept of quantization with data flow is that you can customize each layer in your data flow corresponding to each layer in your original neural network to the maximum, or let's say minimum precision that layer can take without losing accuracy. So you can do individually per layer and specifically per weights and per activations quantization, such that you turn the original, let's say, floating point representation of the neural network into something that is very specialized, but still high accuracy. And then you deploy that, right? So the advantage would be that once you, let's say, discover that layer 2 can work with 2-bit weights, then that will turn into much less resource utilization when you do deploy this to the FPGA. Of course, having all of these separate knobs to turn makes it very complex for the user to figure out, like, how is the user going to know that it's supposed to use int2 for the first layer and int3 for the second layer. You simply don't know. So what we provided is a PyTorch library called Brevitas to do quantization-aware retraining and calibration-based quantization post-training. And this library implements some mechanisms to be able to discover the correct precision that will give you an amount, a specified accuracy for your neural network. And then you'll be sure that that particular configuration of precisions per layer is the one that is optimal to implement. It does so by using a set of differentiable cost functions that take the final resource cost of the FPGA implementation into account. But the takeaway for the user is there's a simple optimization path that you can implement here, and you can get some results that is perhaps not optimal, but is close to being so. And you don't have to be, again, an expert in training DNNs with quantization to do this. And finally, I want to talk about a more speculative direction of research that is happening in our labs with regards to sparsity. And I want to first highlight the fact that sparsity is tightly connected with energy efficiency. Now, we talked about quantization before. Of course, with quantization, you can go from 32 bits down to 1 bit in precision if your neural network will allow you to do so. But when you're at 1 bit, there's nowhere else to go, right? So the next direction that you can go in is explore whether you can sparsify your neural network. And the good news is DNNs are naturally sparse. Both artificial neural networks and natural neural networks, and there is scope to improve efficiency through sparsities. If you are kind of thinking back to the data flow model that I proposed before, sparsifying the neural network on the actual computational fabric means removing resources that are serving specific neurons that aren't actually being used when the inference is happening. So that means from an initial representation which is dense, you turn that into a representation which is sparse by removing neurons of the structure that are not being used, and that means that those wires are not toggling, power is not being consumed or dissipated for that. Now, there is a different way that you can build neural networks to take advantage of sparsity. And we call that logic nets. It's a more recent approach to building neural network accelerators for FPGA. But the idea here is that rather than starting from some specific dense neural network and then trying to find the sparsest representation that you can for it to maximize efficiency, you go the other way around. So you start from a binarized neural network, and you represent a neuron using a lookup table. Of course, lookup tables take binary inputs and provide binary outputs. And a lookup table with 6 inputs and 1 output represents a neuron with 6 synapses and of course, 1 output. Now, then if you design a highly sparse circuit in an FPGA that enforces a specific sparsity configuration, then that can represent a neural network, and you can state at the beginning, this is how my neural network will look like when implemented in the FPGA. And then if you can represent that in the training tool, then the training tool can make sure that it finds the correct configurations for each lookup table such that that circuit actually implements a classifier once you have done with the training. So this is the way that we go kind of backwards from structure. We deploy a structure to the FPGA, and then we reconstruct that structure to be understandable to PyTorch. And then we tell PyTorch, find the correct configuration for each lookup table in this structure, such that when I do inference with it, I get high accuracy. And this actually works to everyone's surprise, including ours when we first tried it. The training tool does find good solutions for this, and then the end result is super efficient because we built it to be super efficient. And the kind of neural networks that come out of this tool can provide one inference per clock cycle at frequencies up to 700 megahertz. So this is the most efficient way that you can implement a neural network on FPGA. And of course, you can have good surprises from this process as well. So like I said, you enforce a specific sparsity on the structure when you map it to the FPGA, but it might be that the resulting neural network is actually more sparse than what you try to build, right? If some neurons in that structure are still being unused, what will happen is when you put this structure through the logic synthesis tool, FPGA Vivado, for those that know FPGA design, the synthesis tool will find and remove the neurons that aren't being activated. So this is incredible. You're doing neural network sparsification with a logic synthesis tool. And we are very proud of this result. So the takeaway here, I would say, is that you can achieve amazing throughput, latency, and efficiency by starting from AI-first principles with the adaptive FPGA compute fabric in mind, rather than going from some existing AI algorithm and trying to map it to the compute fabric. And so I'll just end with a couple of actual results that we have in the cybersecurity space. So we have implemented a traffic classifier for the UNSW data set. Here, this is a structure that very much mimics what I've shown you before. Traffic classification is made by inspecting packet headers. We've quantized this to 2-bit weights and activations. It achieves 91.9% accuracy and 300 million inferences per second with 18 nanosecond latency. And all of this in 8,000 LUTs. So you can deploy this in your production system. It will not slow down the pipeline. It will be able to kick packets off of your data path as required at the line rate of the network. We're also working with Fin to implement a DDoS classifier trained on a CIC dataset. Again, 2-bit weights and activations. We're currently achieving 85% F1 score. This is currently optimized up to 19.2 million inferences per second and 52 nanosecond latency. It uses more LUTs, of course, about 20,000 LUTs, but keep in mind, 20,000 LUTs is not a lot of LUTs nowadays. And we have work in progress, which we expect to scale this result to 300 million inferences per second and the same latency as before. So I would say results are quite encouraging for this set of tools in this particular space. And I will just give you a customer example in a network security application. I can't disclose a lot of details, but I can disclose some. So the original network that came to us was Ent8, convolutional neural network. They used some custom operators, which we had to add to Fin, but they are currently supported inside of Fin. The initial deployment was on CPU, so you can see here the performance. Initially, about 200 millisecond per inference. The first prototype that we did without too much optimization went to 7 milliseconds per inference, right? So that's already almost a 30x improvement from the CPU baseline. And then, of course, we explored quantization on it. Many times users come to us with networks that are not quantized to the full capability of that neural network within the accuracy bound. So we work with them to kind of discover a better quantization scheme for the neural network. The result was the final Fin prototype was able to do a 0.1 millisecond per inference. So that's 2,000 times improvement from the initial baseline. So I would say that's quite encouraging. So talking about Fin generally, we've used this tool for a number of different domains. Of course, networking and specifically network security is just one of many. And it is open source, just like Brevitas, the quantization tool. So you can find them both at these links here. And of course, you can talk to our team through the communication channels that we expose on these repos. They are quite successful now, so I hope they will be useful to you as well in your work. And of course, if you want to know more, ask questions or come talk to me in the break afterwards. So that's my presentation. Thank you very much.
Hello to everyone. Thanks for this opportunity. My name is Artem Volkov, and I represent the Research and Development Laboratory, MegaNet Lab. My colleague previously showed you our results in the robotics, and now I will share our vision on this relevant field as 6G networks and our research and our test bands in the particular robotics, but I will concentrate on the fog computing, on the holographic type communications. And first of all, the telepresence services is one of the most important now research field. So regarding the challenges, now, as we know, we live in a time when technology is charging faster, and then we can fully implement it. And there are planning that 6G will be in some years, and we have new capabilities, new services, and they start a new era of internet and services too. And I will show our vision about that. And of course, more and more countries adopt their digital strategies and related to sustainable development goals, which are defined by UN Assembly, and taking account their synergic effect. And anyway, now in the telecommunications, we are considering first of all, the gaps in the technologies and how to implement some methods, protocols, solutions, first of all, in order to enhance the necessary capabilities, necessary requirements for future our immersive. So, and regarding a little bit our methodology of our research, we did research in the 6G field. We are considering the principles, expected services, requirements based on the 3 types of surface. There are the science papers, of course, the IEEE and so on. 2 recommendations. Also, we used the documents from focus groups. It's the main one of the main documents, I think, on the pre-standardization processes. And of course, the white papers from some companies, also from some standardization organizations. And it's necessary to take into account the current problems that can be traced as a part of the deployment of the new telepresence services. And for example, there are domain interconnecting, device identification in the networks, and also positioning in the networks. And as a new field in the new research, we faced that holographic positioning, how to make the position in the metaverse. It's one of the interesting now research direction, and I think we can make some contributions, all of us, to this. So one of the interesting slides, I think, that is an analytics. We made it based on the database of ITU draft recommendations, and also recommendations which were approved during the last study period. So as we found the following criteria, such as this security, trust, networks and systems, architecture, methods, models, quality of services, quality of experience, and other related tools for ensuring the traffic traffic requirements. And one of the new directions, such as the low Earth orbit and space-to-Earth integrated networks. And so that's important point here, that the new standardization topics related to 2030 network are making more relevance now. And we found many draft standards now in this study period,
in topics, for example, like AI and ML, and here we have some confusions. I mean that at the same time we have a standardization process and we have the pre-standardization process in these focus groups. And this is an interesting experience. And as you know, we have the same experience now in focus group 11 and 13 and 6, and when we are considering some issues in the metaverse and their related fields. So challenges, yeah, I know that maybe this figure knows all of you, and you know that of course the 5G consists of 3 main directions, and now we define the 3 new dimensions such as integrated sensing and communication. Here we considering not only IoT or industrial IoT, we're also considering the extent our immersive experience, for example, for control robotics, for control our robot humanoids, and so on, based on, for example, television suites. And we have also these test bands, and I will show you on the next slide. So, of course, we have new capabilities, such as sensor-related capabilities, sustainability, and one of the important, this is AI and communication. We need to use some AI, firstly, as a method, as a tool for solve some problems, to provide capabilities to ensure our necessary requirements. So, and as we know, the 6G network will be integrated heterogeneous in each of our understanding. This network will aggregate technologies from different dimensions and user capabilities and get us a better immersive experience. So here presents key architecture principles such as simplicity, backward compatibility, of course, as standard principles. Native slicing, now we have resilience, and one of the new, there are network determinism. And first of all, I think that simplicity now is a first of very important principles in new technologies, in the new architectures of 6G network and our future services. So it's our vision of space series integrated network. Of course, we use this picture is the view of for future integrations. I mean that we have a native slicing modular-based principles, microservices as a native integrated architecture of high-load services of distributed network in computation with a dynamic for computing availability, and also that a native slicing. And AI, we consider it as an end-to-end technology and end-to-end processes with the ML model conveyor and system serves with a swarm intelligence as a highly effective approach for resource allocation. Firstly, here I talk about the dynamic fog when we use the non-standard mathematical approaches. So, and I would like to show shortly our results in our lab in each of the mentioned above directions because we have a time limitation. So here's our architecture. So the core of lab based on the multi-controller SD network. Here we can make the research, for example, how to make the base better. I mean, controller allocation and migrate it as the containers via the network. Also, as you can see, we have the vertical slices. They means that we have the different interfaces on each of the level of technology and each of the level of the stand, and can integrate some AI tools and test it. For example, we can we developed one of the new methods and approved in ITU the method which describe the traffic recognition based on data metadata from OpenFlow flows. in order to save some traffic, we can make some recognition based on the metadata, and that's great for the future our requirements. So of course we have interfaces for measurements, and it's make our lab and our architecture very flexible. Of course, we have segments such as robotic infrastructure, and I mentioned my colleague, and telepresence suites, which consists of telepresence suites, robot humanoids, industrial of things, I mean the robotics, industrial robotics, which I can control by internet, and holographic type communications. So here show it's some of our developments. There are HoloLink platform with the multi-access. We can use different devices, holographic terminals, which we developed too. And these holographic terminals with the low request to network, and new methods for holographic type communications with reduced traffic volume. So yes, this don't worry, this skeleton is not a user, it's a typical our hologram which we're sharing between terminals to make some measurements. We not use the X-ray technologies. So okay, here we present our results in ultra high dense 3D network and for computing. For example, we can use a fractal math. You can see the picture of the city, and it looks like a fractal models. We can use it for testing. We can use it for planning networks, and someone else. And also we use the industrial robots to make the dynamic platform for fog testing. Dynamic fog testing. We modeling, for example, how users can go out, and we should control these movements and migrate the containers to other fog devices. And here we use the heuristic mathematical algorithms, for example, particle swarm optimization or gray wolf optimization on someone else, and modified it, and suggested the new protocols for microservices, routing microservices protocol for computing segment. So here presents our telepresence suite, which we can use for transferring data of your movements. You can control the robot via the internet. Of course, we use the digital twin as the technology, and digital twin of your user, which used this telepresence suite, and we can test in some algorithms on edge computing, because this digital twin located on this edge computing. So, and what's next? I mentioned during the presentation about this area, and I think all of you know that, and it will be the metaverses and multiverses in the common. All of us who are working on the telepresence, on the 6G, on all of these technologies, we make the contributions to the metaverses in the common and multiverses. And now we have a huge work in this field, and the metaverses is an integrative ecosystem of virtual worlds, offer an immersive experience to users, and can improve our experience. So here our concept. We also participate in this year in the Think-a-thon challenge, and we are one of the 3 teams who won it. And we present the whole netverse. This is first of all educational verse, where we use the holographic type communications and telepresence suite for improve your immersive. First of all, for internet of skills, and I think later it will be the video about it. So that's all. Thank you very much. Also, we participated in AI/ML in 5G challenge, where we organized some regional hosts. And thanks again. Thanks for your attention, and have a nice evening.
Thank you. Any questions for Artem, please? No? Okay, thank you very much. Thank you, Artem. So we have the next speaker is Karim, please. Yeah.
Yeah, thanks Vishnu and Thomas for the invitation. I'm really happy to be here for the second year. My name is Karim Rabia. I'm a principal architect, Red Hat. I'm leading the delivery and the transformation engagements in the Middle East and the Africa. I think that's why Vishnu always invites me, because I bring like some insights from the actual market. Today I prepared like a small presentation to assess together the role of cloud platforms in accelerating the AI adoption. And actually, when I was preparing for the presentation, I tried to figure out what would be the best start. And I decided to start with the one of the last slides that I had last year, so that we may think of this slide or this presentation as a progressive set of slides, completing what we have discussed or what we discussed last year. So last year, we spent some time putting definitions for AI native. The term itself had several definitions from several sides. And there were like two directions or two angles of defining the AI native, at least in my slides. So the first one, and what you see like the red architecture, was a reference to the necessity of defining some sort of overlay AI ML reference architecture and help operators and telco operators and customers to understand how this overlay AI ML architecture integrates or interlocks with the existing telco reference architectures, the one that is commonly published by 3GPP, and I refer to that architecture with underlay. And that fits well with the effort done by this focus group, former focus group, and the hopes that we will have in 6G. The second thing, what you see in the southbound was a definition that next generation applications would be AI native. And we said that it would be AI native by architecture and design. And the definition by that time is that these applications should natively be developed in conjunction with machine learning models to govern the lifecycle management of these applications using ML model. But by that time, we didn't have, I would say, a solid definition, or at least myself. So I hope today we can like complete the drawing and see exactly how can we reach this state of AI native applications, and how actually the cloud helps and how the cloud platforms helps in that. But before doing that, maybe a foundational step, just like a reminder why actually cloud is always coupled with AI, and why cloud is brought whenever an AI ML is discussed. So the cloud, as I'm saying here, it's a very classic option for hosting AI ML, other maybe like AI workloads, AI testing, ML testing, and deployment. Why? Because usually most of telco operators, and I work with the telco sector, they have already existing applications, existing investments. So they have some sort of private clouds, and they are trying to fulfill, the cloud promise of bringing the cost efficiency. And there's the fact that actually the majority of the applications of the telco operators are on the cloud. So it makes sense that whenever you want to deploy a machine learning model or bring a certain value, most probably it will be in the cloud, because this is where the applications are positioned. Also, the cloud brings a set of offerings and capabilities that would harden the AI stack, like monitoring, observability,
in addition to the classic infrastructure as a service, container as a service, platform as a service. And the last thing, the fact that you will not get the scalability and resources scalability if you go for some sort of a silo deployment. Most probably the cloud will give you this kind of resources scalability. And that applies on both private and public cloud, because in the presentation, you'll always see the term hybrid cloud. So hybrid cloud refers to the mode of deployment of cloud being private and public. So in order to assess how the cloud platforms or how the cloud actually accelerate the adoption, I will spend a few minutes just assessing or understanding what are the obstacles and see actually how the cloud platforms can counter these kind of obstacles. So I try to bring some like market analysis reports to give us or to highlight what's happening actually on the market. So this is coming from IDC, and it seems that the result of the survey, it's called Worldwide Artificial Intelligence Software, that was 3 years back, that 78% of the data science project, they don't make it into production. And one of the key, I would say, obstacles was to actually the lack of the process to go to production, or the lack of the process to go to implementation. Like you do a great effort doing the testing, and then you get stuck, you fail to deploy on production. And that was somehow mapped to the, not on lack of collaboration, but working in islands. For example, maybe data scientists, machine learning engineers are working in one environment. There is one environment have the cloud administrators, and maybe in another island there are the business like decision makers. So these three are not working in harmony. So at the end, the project never go to production. Second thing, the infrastructure complexity, and we will talk about that. For the whole value stream at the end to have a machine learning or an intelligent application into production, the value stream spans across multiple personas, multiple domains. So you don't want to waste the data scientist, for example, time by understanding exactly where are the GPUs, what are the resources, and going into these cloud details. These kind of the obstacles, we at the Red Hat, and me personally, we saw that exactly when in the first wave of the cloud or in the first wave of app development. So for instance, you can sell the brightest and the smartest product, but because you don't have an efficient operational model, you find that there is no adoption. You have like hundreds of applications in the pipeline, and at the end of the year, only 10 go to production. So it's not about technology. The operational model, or the how to make the technology operational, this is one of the lessons learned. And with that slide, I recall also the first wave of the telco clouds. So the first wave of telco clouds in 2015, when the telco started to build the private clouds, the VNF, or the network function onboarding time, was a disaster. Like they can spend from 6 to maybe 10 months deploying a certain function on the cloud. So they were just wondering, where the agility? Did you bring the cloud to spend 10 months in the doing the onboarding? So it looked to me, when I saw this survey from Gartner, that the the time from idea to realization for AI ML application or project can also take the same. So I still acknowledge for sure the complexity of the project, the time or for do testing. But guess what? We had also the same difficulties in cloud, but after like 3 or 4 years, several articles were published, like wondering why telco cloud failed. So we don't want to have the same with AI and telcos. We want to make sure that we have successful AI projects. So again, having an operational AI is the key here. Having a proper definition of the process, it's not just about technology, like defining the process that eventually would lead to deploying machine learning models and intelligent application in production is a must. Here I'm bringing like some sort of a process visualization on actually what does it get? I mean, to go from idea to realization. For sure, it's a very high level, but it shows at the end how many personas, the variety of personas, or the number of personas, or number of domains that somehow the value stream should span to at the end have the machine learning model deployed in production. So you have the business leadership that actually set the goals and set the business KPIs. You have the data engineer that actually do his best to gather the data. As the colleagues here explained, from the radio, from the core, from the transport, from the devices, from everything. So, and at the end, consolidate that to be data meaningful, to be fed into the machine learning. And data scientists interested in developing the machine learning model, and instant also for doing the monitoring and doing the reiterations. And maybe you have the new role of ML engineer that actually complement what or connects what data science is doing with the app dev or with the DevOps engineer. And we have the classic DevOps or the app dev role who's actually doing the application development. And at the end, there is one guy always waiting for us, which is the IT operations. So multiple personas, and you need to have a capability in your network that will allow each persona, each entity, just to focus on what they are doing and not to go to the complexity of the other domains. For example, you don't want the data scientist who is developing the model to understand exactly how that model would be transformed into a container image or a container or microservice and be deployed in production. You don't want the data scientist to care about the infrastructure resources, where are the GPUs, as I said, and the same thing for each one. So you need a platform that can provide a self-service tools for these personas, for all of them to do his part, and eventually the whole process is streamlined, and you get a streamlined delivery pipeline. And when I say delivery pipeline, this is a very key term that we always use at Red Hat and anyone working with software. So we know how to develop software. And you know what? Developing a machine learning model is not an exception. It is the same, follow the same concepts. And you see, there will be a step that you need to apply whatever processes and framework you do for the app development into the machine learning. So it's like a mix, or like a platform that will help you to combine the DevOps framework and the MLOps framework that would eventually help you to streamline the onboarding or the delivery of intelligent apps into production. One also characteristic that we see, and I'm trying also to back my words here with some data. And these are like two extracted figures from IDC and Gartner about actually where are these models are being deployed. So one may think that, okay, these models are trained in cloud. They most probably they are deployed in cloud, but not necessarily like that. We see a significant rise, for example, in the deployment of ML models or intelligent apps on the edge, but the training is happening on the cloud. So the AI by nature is hybrid. Okay, AI by nature is hybrid. The deployment is hybrid. And guess what is actually hybrid by nature as well? It's a cloud. So most of the operators, most of the telecom operators, they have either current hybrid clouds deployments or a hybrid cloud strategy. So now no one is keeping his application only on IT cloud or telecom cloud, but most probably most of the operators are adopting hybrid cloud more or less. So here, when you think of a machine learning platform that helps the data scientists to develop, to train machine learning models and eventually have these models deployed in production, then this machine learning model or platform should have the capability that has somehow a unified testing or development environment and the capability to deploy these machine learning models everywhere. So you develop a machine learning model, you develop an intelligent app, and then you go and deploy this app in the edge, in the private cloud, in the public cloud, And guess what? This is actually the bread and butter of the cloud platforms. This is what they do. So you have a central place, you have the tools to develop your application, and then you have the luxury to onboard the application or deploy the application anywhere you want. So enough negativity. Let's go to the positive side. So this is like a visualization of what I was saying, that you can simply unleash the power of hybrid cloud. You can actually have the modern ML platform that is working in conjunction with the cloud platform concepts, so that you can, as I say here, you can train data on-prem, and on-prem I mean like on a cloud environment, private cloud, and then you can inference, you can serve, you can deploy in production either on-prem or on cloud, and that goes to any environment. So this is the thing that cloud platform can help you natively, because this is the DNA of a cloud platform. Similar to, as I said, similar to software development, we adopted already the DevOps framework to run our application. This is if you go to any IT department of any telco operator, they are experts in DevOps. They have the DevOps tool set chain in production. They create CI/CD pipelines, and they have already streamlined the application onboarding or the application delivery. So we need to have the same concepts applied to machine learning or to AI. And we actually have to do that before we introduce the technology. So if you don't define the process and you introduce the technology, most probably it will not be adopted. And we have a lot of examples in the technology and in our work. So the platform that you're looking to have should give you the capability to streamline or to give you the tools that allow you to, in one place, to develop, to test, to train, to deploy your machine learning model. And as you'll see in the next slide, it's not just about the machine learning model, because most probably that machine learning model will be somehow integrated with a specific app, turning this app to an intelligent app with the machine learning logic to provide a specific value, either KPI optimization, maybe in the marketing segment, whatever value. So that should be the role of the cloud platform. And just let me remind you how we see it from software perspective. So usually, as I said, the IT, the software developers, we are very good in doing that. We are very good on having developers doing the code. And once he commit the code, he doesn't care about anything. He just commit the code, and that code goes into the pipeline. Quality analysis does their job. And then at a certain stage, by automation, that code is turned into, let's say, a microservice or a container image. And then eventually that microservice or the application is deployed on a certain container platform in production. So this is what we do. This is our DNA. Okay. So what we need to add here is the following: is actually have the similar environment, the similar framework for machine learning models. So you give the necessary tools, self-service tools, to the data scientists to develop the model. And then similar to the app dev, he just developed the model. And for us, for the cloud, that will be most probably will be just like a Python workload. So at a certain stage, when you go to deploy the model, the conjunction with the app is happening. So you need that platform that you see here, if I see my cursor, is to do the conjunction of machine learning model creation, which is an app at the end, with the original app, and then do a joint deployment. So if you do that manually, if you do that in islands, most probably it will not work and it will not scale. So you need the cloud platform that give you the right tools to do this kind of conjunction or this kind of streamlining. I still have 3 slides. And that's actually, I'm here bringing the example of the OpenShift AI. I'm basically from Red Hat, so that's an OpenShift AI. And that's the platform that actually the artificial AI, the AI and the machine learning platform that enables our customers, the enterprises, to create and deliver AI-enabled application across hybrid clouds. And hybrid clouds here is a keyword. So it's one unified platform that you may use to streamline the app delivery or the AI-based applications into hybrid clouds. And guess what? This ML platform, actually, it is combining, or the platform is combining the capabilities of OpenShift AI plus OpenShift, which is the classic cloud platform, Kubernetes-based. So the right combination between the both gives the right advantages to telco operators or whoever wants to run ML or AI-based applications. So as you see here from the visualization perspective, the cloud platform abstract all the infrastructure. So the data scientist or whatever working on the app dev doesn't need to care about the resources. That's the role, the classic role of the cloud platform. And at the end, it provides a self-service platform. It streamlines the overall process in terms of gathering the data, developing the model, bringing the right tools, and then deploying the models in the because classically in the app dev, the pipelines classically deploy the application in many environments, like testing environment, sandbox, staging, pre-production, SIT. So that's again the DNA of the app delivery. So we are doing the same for the AI-based applications. One other advantage or the cloud platform can provide, and it's a very well-known argument that we are seeing now in the market, that data scientists or whoever developing the machine learning model at a certain stage, he requires, or the data scientist requires that somehow to run the AI workloads in a distributed manner, what we call distributed workloads. That means that the AI workload or the Python workloads can run at the same time at multiple nodes of the OpenShift cluster or the Kubernetes cluster. And that would most probably require huge resources. So cloud infrastructure admins, and because I work with them, they are very reluctant when working with machine learning flows or machine learning applications, because the resources are unpredictable. And I can tell you that what's happening now, for example, it's a very well known in private clouds. If there is a strategy to embrace or to welcome machine learning based applications, they create dedicated clusters for them statically. But we want to have a smart solution to dynamically create some sort of clusters for such applications and dynamically assign resources to do the testing and then dynamically take the resources back without giving the data scientist more, I would say, headache to care about the resources. For example, if you have a cluster of hardware and some specific servers, they have the GPUs. So there should be a declarative way from data scientists that to tell you that, you know what, my workloads require this GPU. But it's a very declarative way. We don't want data scientists to go into the level of the resources. So this is actually also one of the capabilities that cloud platforms provide to data scientists. So data scientists did not need to go into the infra level, but they can declare what they want. And these are actually the 4 bullets that I brought, that at the end, the joint capabilities of the cloud platform and the ML platform will enable data scientists to just focus on the modeling, not on the infrastructure, to automate the setup and the deployment, so no need for the manual works. All the platform are availing all the tool set that he brings to start the pipeline. Prioritize and distribute the job execution, because there are a lot of jobs are being fed into the cloud, so he can put some priorities and cloud can process accordingly. And at the end, the cloud platform or the ML platform should provide some sort of a certified ecosystem, because at the end, you have to provide capabilities to the data scientist to use, like wherever he sees that it makes sense for him to integrate with to bring value. And that's why you see in the market, there's the necessity of having an ecosystem of certified partners that provide extra value, price values to the data scientists and to the overall value stream. So this is something also that the cloud platform can provide. I will close with like a key takeaways. So the cloud platforms are evolving. Machine learning platforms are there in the market, and as I told you, most of these machine learning models, and when I talk about the OpenShift AI, for example, is based on the OpenShift technology or the Kubernetes technology or the cloud platform technology. So we believe that the introduction of such a cloud platform role and a new scope will heavily accelerate the AI adoption, because what I see in the market, and again, I work in the delivery, most of the operators, because of the 5G, they have already deployed cloud platforms to manage containers, because the 5G core, for example, and the RAN is containerized. So to capitalize on such investment and bring an ML platform, like the example I wrote, OpenShift AI, would accelerate a lot the AI adoption. So the cloud platform and the ML platform will simplify the AI adoption, because at the end, you will have a composable platform that will accelerate the app and ML development and the deployment. The platform will drive the AI ML operational consistency, because at the end, you have the right tool set, you have the right procedures to streamline the overall delivery process. So from the idea till the realization in one place. And third thing, and that's really a very important point, that you will not be limited or locked in to deploy in a specific environment. You can have a unified cloud platform slash ML platform. You develop, test your machine learning model, your intelligent app, and you can deploy that over hybrid cloud, private, public cloud on the edge. And that's one of the strength points and the beauty of the modern cloud platforms. That's it. Thank you. I hope that was useful and informative.
Thank you very much, Karim. I think that's been exactly like last year. You've given us very practical key takeaways. Yeah, please.
Thanks a lot, Karim, for the presentation. That's very insightful. Maybe one question about something that I didn't really see a lot of focus on is the impact of AI on the distribution of the cloud itself, right? Because I think everything that you talked about could be assumed for central clouds, could be assumed for edge clouds, right? Distributed cloud. And now my question is, do you see a paradigm shift in how clouds are deployed because of the new applications that are rising that would probably require a more distributed infrastructure of cloud deployments in comparison to the traditional central cloud that many companies are already having, right?
Yeah, that's a very good question, and actually trending these days in the discussion with our customers. So yes, with the rise of O-RAN in particular, and with the rise of the 5G SA use cases, we started to get like solid requirements for a vision and architecture for distributed cloud. And we are adapting, I think, similar to all the suppliers in the market. So yes, it is coming. And also we have now flavors that fits to this kind of thing. So we have, for example, deployments of single nodes. So instead of going a full cluster, you can just go for a single node with a minimum footprint. You can go, for example, with compact deployments. And we have already certification programs with most of the O-RAN suppliers and vendors. So these solutions, distributed clouds, either it is a remote worker node or a single node or a compact desk, are being verified by most of the O-RAN vendors.
Okay, maybe another question is, where do you see the impact of also the trendy sustainability topic on cloud deployments? Is there some form of energy aware cloud architecture that could actually, improve energy consumption, improve sustainability in networks?
Yeah. Yeah, this guy knows everything, so yeah, he's talk about this topic tomorrow, but it happened that last week I was talking about the same topic with one of my customers. So I will give you the delivery feed, and Azhar will give you the from strategy perspective. So during our certification with these vendors and with the inclusion of our customers, we start to get this kind of request. So we are now assessing all the optimization features that we can use coming from the hardware itself, vendors, from the device, from the Intel, for instance, coming from the operating system. So there are some parameters, some features related to the thermal consumption or power consumption optimization. So we do that. Some use cases, some features to turn off the servers if they're not used. For example, if a remote site that no one is passing by and it's like an antenna in the desert, then all the components constructing the O-RAN stack should adapt. So we are exploring all these features, and yeah, Azhar will give you tomorrow the.
Okay, thank you.
Thank you.
Thank you, Karim. Yeah, stop.
Should they clap for me?
I think we have to stop sharing.
Thank you.
Okay, I think we have, here you go. Can come.
All right. Well, thank you, Vishnu, for having me here again. I'm Tim O'Shea from DeepSig, and we're a kind of a small company in Virginia. And really, we were founded in 2017 to really focus on deep diving on machine learning in the air interface and in the physical layer to help improve communication systems, and trying to take some of the very early research at that time, build it into mature offerings. And now we're really excited to see the industry starting to really accelerate in this area and adopt some of these ideas and extend many other great ideas and how AI and ML can affect the comm systems. So I was going to talk a little bit here about kind of what we're doing in AI native communication systems, kind of how we're doing some of that within the 5G and Open RAN context, but then also talk about kind of how this can evolve into 6G, and maybe talk a little bit about hopefully some of the ways ITU is helping lead a lot of that. So I think three of the key intersection points that I think we see in terms of how AI and ML are really super impactful on any wireless communication system are first of all in spectrum sensing. So understanding what's going on around you in the spectrum, knowing where different emitters are, how to deconflict against them, how to understand when there's anomalies, changes, unintended emissions, or how to interact with other systems in the environment to reduce interference and to improve coexistence within finite spectrum. Then also, I think we've talked a lot today also about kind of core modem optimization. This might be the biggest opportunity. This is really, how do we exploit all the degrees of freedom in a communication system in a base station or many sectors or many antenna elements with many users to kind of use ML to optimize all these degrees of freedom to push the most performance and efficiency we can out of our future wireless systems. And certainly, end-to-end learning is one form of that in the physical layer. And certainly there's been a lot of discussion recently also around this site-specific or hardware-specific or user-specific optimization and trying to leverage all of these data distributions to optimize your comm system. And then finally, there's this idea of a RAN digital twin that's come up quite a few times today. And I think really I see this as, how do you build all of these models of the data distributions. So how do you model the propagation environment, the user behavior environment, all of the emitters in the environment? You know, you really want your future comm system to be able to really model all of these things accurately in real time so that you can simulate, you can optimize, you can test, you know, every function throughout your wireless stack. So I see these as kind of the three top level core functions that ML provides a massive impact on kind of the access layer and the physical layer. So kind of diving into the spectrum sensing one a little bit. I know in the US, there's been a lot of movement on this very recently with FCC and NTIA starting to really emphasize what they're calling a moonshot. I don't really like the term because I think this is not a moonshot. This is really doable. But the idea being we should be much better at sharing spectrum. So there's been a lot of very dedicated spectrum allocations, I guess internationally for space, but also for federal use and different types of users. And we've had kind of the success of the CBRS type spectrum sharing program in the 3.5 gigahertz band, but there's many other bands now where there are incumbent users in these bands, but they're very sparse. They represent different types of emitters, whether they're radars, they're you know, handheld radios, they're different types of emitters all around. And I think CBRS addressed this because they were this band first because they were very high powered, easy to detect, easy to work around emitters. But I think it's been said now that 6G really needs to be sharing native, not only because we're going to need to operate in these much more you know, non-dedicated bands that we need to share with different types of users, but also because we need to pack more networks and more users and more sectors kind of more densely just to get better reuse out of the spectrum. So kind of all of these things are motivation for you know, why you need this pervasive sensing and spectrum awareness in your network to help optimize and provide this kind of SON and feedback functionality for power interference tuning. And if we look at kind of core network optimization, I kind of bucket this into three bins. There's, you know, how do we use AI/ML today with it kind of transparently in implementation to optimize current day standards? There's a lot of work going on in 3GPP right now as well in terms of release 19 standardization for things like beamforming, CSI feedback, and localization. And then there's this whole discussion for as we work towards IMT 2030 and towards the 3GPP REL 20 study items, you know, how can we start to look at more interoperable AI models that are both device and network side, and maybe look at things like an AI native air interface. And so these things can be built out, tested, and proven outside of the standards, which I think is really important to show what's possible. But then, you know, the standardization process, I think, is continuing and complicated. So AI RAN Alliance, I just wanted to point out this is kind of an effort that launched this year. I think NVIDIA was one of the main spearheads of this effort. But the idea here is really not standardization. It's just simply let's build out proof of concepts and show what could be done in the future of standards. And so I think this is kind of an exciting effort to look at what ML can do in future communication systems. So our big focus really has been in using this transparently within 5G systems. So this idea, I think, has been brought up a couple of times today on the neural receiver. Open RAN systems are becoming used much more pervasively. I think there's been a little bit of discussion of that today. Reference designs like Intel FlexRAN and NVIDIA's Aerial are out there, and people are starting to build and operate networks on these sorts of stacks. But we need to really close the performance gap with tier one vendors in the world. And so I think making these stacks more competitive is a place where AI comes in transparently and can do things like improve uplink throughput, sensitivity, and reduce computational complexity. So this is one of the areas we've been focused. And I think, you know, it was a really interesting discussion this morning about how do you test machine learning in a comm system? Because if you try it just on the, you know, 38901 type models, they're statistical models, you may not see the benefits that you would in the real world. So we've been trying to really take these ideas, these and start vetting them, in real channels. So I think that with kind of data science behind communications, experimental research and test becomes super, super critical. Like you need to try this stuff in the real world and then try to match the real world in your modeling as best as possible. So certainly this has been our big focus, is try to take some of these ideas, run quickly with them. We've been working with a couple partners, Viettel and HTC are two that we've mentioned here, in terms of, how can we bring this out into the world and validate it in real world harsh macro cell conditions, which don't really match the statistical channel models perfectly. So I think that's important. And then I think if you look at, how do these things get deployed across the stack? There's, I think, certain pieces of the stack which have been standardized within ITU. There's others within 3GPP, and then Open RAN right now is a little bit of a layer of implementation and standardization on top of that. And so it's really seems to be kind of spread across the three. And I think that if you look at kind of this ORAN model here, you have a lot of this functionality occurring within the baseband or the DU, this kind of real-time inference within a receiver that needs to run on the order of, sub 500 microseconds. But then you have all of this functionality within the digital twin and for modeling and for retraining these receiver models, which can run in a RIC or in a SMO somewhere that's not real time in order to kind of deploy these models. So I think that right now there's still a lot of churn in terms of what should these sorts of services look like, where should they actually live and run, what is the right framework, is it ORAN or is it something else? But I think kind of the general form of this is kind of starting to meld in the industry. So this is some of the work that and I think there was a really interesting discussion this morning about data sets and about simulators, both of which are really critical for R&D and progress in this space. And so one of our efforts, actually this is supported by the NTIA's recent kind of ORAN efforts in the US. But the idea here is that you can take measurement data, but it's very specific. It's often a specific drive test or a specific measurement campaign, and it's often has a lot of privacy concerns. It's often not easy to have different operators release these sorts of data sets. And then you have things like simulators and ray tracers, which can simulate different types of geometries or environments, and they don't match perfectly. And so I think there's been some discussion, certainly Jakob talked about this topic as well, is the idea of model calibration. And I think this is hugely important right now, because what you really need to do is take this measurement data from operator networks and use it to calibrate these kind of generative models or these ray tracing models such that our simulators are really, really accurate now within the real world. And I think this is kind of a critical area to help enable, like, how do we now have a data-driven model that can generalize very well for doing optimization and deployment testing of these future RAN systems. So this is kind of an effort where we have drive campaign measurements of channel impulse response data, and then we're fitting kind of basically a ray trace model to this so that we can represent a really accurate, similar generative impulse response as you would get from the measurement. So then where could this go? I think if you look further on towards 6G, there's this idea of an end-to-end learned air interface. So, rather than using the existing kind of very rigid modulation framing pilot schemes, multi-user schemes that we have today, can we let more of this be kind of learned emergently? Can we let end-to-end learning do the modulation design, the frame structure design, the piloting design, even kind of the multi-user access or non-orthogonal user access, and spatial directivity models within our networks. I think one of the things we've seen is ML is really, really good at these sort of high degree of freedom problems. If we have an accurate enough model or simulation to train it within, and to overfit to the sectors where we're deploying this. So I think this is a really exciting space, and I hope that this is something that will see more consideration in future kind of study areas and work items in the coming years. And it's something we've been doing a lot of work on as well. So we did an early work with NASA doing this over the TDRS satellite system, and now we've been doing more kind of terrestrial and point-to-point type learned autoencoder communication systems that can run at high rates. So this is one example kind of in the RF chamber of a fully learned 2x2 MIMO autoencoder system where we're able to run kind of high data rates with streaming IP and video and so forth over it, and running kind of a web interface. So this is really kind of showing you can take these technologies, you can introduce them into a Wi-Fi like stack. We can really build and use these proof of concepts today outside of the standards, but we really need to start thinking more about how can we make these more interoperable and standardize them and use them, and how can we show really the key impact and benefit of why we should use them in some of these future standards. So that's kind of the last slide is really just looking at, I think there is still a long way to get to standardization of some of these technologies. A lot of the basic pieces have been proven, but I think we've seen, at least in REL 19, that the standardization process is still very complicated. There's a lot of discussion really still about how do two-sided models work, right? If my AI model in a base station has to work with your AI model in a phone, who trains the model? Do we trade weights? Do we trade just loss feedback? What do we standardize? And that's really still a pretty complicated topic that's being discussed. So I think that right now these kind of clean slate POCs and proof points are really hopefully impactful to show how that could be done, before we standardize it. And yeah, so I think that's pretty much it for me. So thanks.
I am very tempted to ask Tim one question. Sorry guys, I'm going to ask it. So Tim, in the morning we had Jakob very dramatically replace a part of the receiver with neural net, basically neural network, and then today Frank very mildly put it by saying that new ways of creating protocols. That's what he told us. But I think he meant the same thing. And today, now you told us about these two-sided models. Where exactly is this going? I mean, if you extrapolate this, where exactly are we going with this?
So I think today, in 5G, we have 3 trials going in Southeast Asia using a one-sided model that's transparent and doesn't change anything in the standard, right? It's just a software change and implementation. So I think that's here today. We can go and deploy these and use them today. But as soon as you need to interoperate and share something new between the endpoints in the network, you need standardization. So certainly in 3GPP release 19, there's a lot of discussion about, if we use machine learning for channel state feedback to help reduce overhead and improve kind of massive MIMO beamforming, there's clear benefits to doing that. But then we really do need to change the protocol fields to support that. And so that's something that REL 19 may adopt potentially here. And then as we get to, but there's still going to be, I think, fixed protocol fields, right? They're going to be well-defined, ASN1 fields that carry some form of that CSI feedback. But then I think as we get further out, we're going to be more comfortable letting AI and ML do more of the design. So maybe it can then come up with, a larger and more diverse set of protocol fields or encodings over the network, and it can kind of take on more of the processing function rather than just something very constrained like a CSI feedback. Like if you let it learn entire, slot encodings and frame structure, that's obviously a lot more than just, a single CSI feedback field. So I think we're going to just slowly see this creep up over time as the industry gets more comfortable with like what works well, what can we handle, what has demonstrated interoperability and maturity and resilience. And I don't know exactly how fast that curve will be.
Thank you so much. The second, I want to just make a small comment saying, if you go to Tim's website, you can see there is an open data set. That is a radio, I think it's called Radio ML, DeepSeek Radio ML data set. And that's the one, actually, I personally know about many analysis, data set analysis, which has actually used that data set, including, I think the one which we did with the Xilinx. So it was a very useful data set. And I asked him last year when he was here, I asked him, are you planning to, that was a great data set and thank you so much and so on. I was telling him, and he kind of brushed me off saying that that's my old ones. So I want to ask you, do you plan to do something more about it? I mean, is there a new version of it coming?
So we don't have immediate plans. I think that it's really interesting. If you look at sensing, like signal detection and classification problems, it has a really nice parallel to image classification. Things like MNIST or the more recent data sets make a lot of sense there for training and test. But then if you look at things like learning receivers or learning end-to-end type comm systems, data sets don't make as much sense. That's where you get more into like a simulator is going to do a better job of simulating a wide range of channel and conditions. And if it's two-sided, you don't have a static data set. You have really a simulator with some sorts of effects. So I think, some things data sets make good sense for and some don't. I think there's also an interesting parallel here that if you look at where all of the computer vision work came from, Google and Facebook and these guys open sourced much of the work because they already had this big data monopoly. And so they didn't feel any sort of competitive issue. I think communications is somewhat different in that like people are trying to build commercial solutions in both the data and the software and the algorithm side, and they have to figure out where to be competitive and where to share and collaborate and figure out where where's the optimal boundary there. And so I think we're always trying to do that and share and open source as much as we can, while also trying to be competitive in a kind of a competitive market. So.
Thank you, Tim. That's a very modest answer. Thank you so much. Okay, so we have demos. So can I request the demoers to be here when and maybe 10 minutes of demo, so we can, you can make it more interactive. We can ask questions or whatever. So yeah, Ammar, please. Thank you, Tim.
Thank you. Hello again. So I will try. I have a suggestion because during my presentation I show some of these application as use case, and Artyom Volkov also mentioned this in his presentation. I will directly go to the video, and then I will try to mention some about use case for this demo. So I prepare presentation. Maybe I will go back to this later. So this is the prototype. Without this voice, okay.
Voice.
No, it's not important. So I will try. So we call this network holotar. The main idea is one of scenario for the metaverse is like one of hot topics now. We prepare this prototype and we are trying in our laboratory to work in many tasks regarding this video. So the main idea is in telepresence. For in this we have like we build the suite. The suite we build it in our lab. We have 3D. This is microcontrollers. It's ESP32, Wi-Fi and Bluetooth. It supports. It was very dangerous because there are a lot for first time, but for first test it was successful. And there are a lot of protocols to connect between and a lot of sensors, actuators for this scenario, for this suite, and also in our this robotics in robotics we include let's see the holographic head. The main idea is we have telemost and we extend this like small monitors in this, and we have camera here. The camera can using OpenCV recognize voice your face, and they can talk with you and can for example we can add your names and the robotics can talk with you and this can be remotely anybody from outside. Also using artificial intelligence in future no students now already start working in this to add some algorithms, maybe to try to learn your voice and talk with like robot avatar. So this is student already did some works in ITU. We tried in focus group metaverse. We tried in Q6 11 SG to prepare map protocols. So it's still under study. We ask we sent this to focus group. We are waiting. I think we will start like protocol maps for metaverse and to interaction between human and robotics, between robotics and between suites. So there are a lot of new protocols, new direction for future research. So this shortly, if you have any question, I am ready to discuss with you.
Thank you very much. Any questions, please, for Ammar?
Very quickly, just technical. This is a projection, right?
No, this is real prototype.
The face is a monitor.
This is 2 monitors. So we 3D, like 3D we are using. It's not holographic. Yeah. It's we are talking 3D video is like yeah.
Quick question. Maybe I missed it if you said that to provide connectivity between the wearable to control the robot and the robot itself, what type of system to connect are you using?
Between suite or yes. Yeah. We are using this system. It's very simple. This is telepresence suite, Wi-Fi router. Yeah, Wi-Fi. No, for video, the latency, yeah, is we use DWDM transport system for terabyte. Our Volga system, or it's very high bandwidth, and with the latency, we don't have problem in this.
Ammar, if I can ask you,
yeah.
What is the next step for this demo?
The next step, for example, we participate in forget UN. We are now we are working. For example, we are trying to find sponsors, maybe to. For example, it can be extended for metaverse for in future, maybe for universities, for teaching. Some of people already asked us to provide some prototype for this for education. Don't know. We are working now in research problems, some scientific problems, but in future, yeah, it will go like product. We are planning to do.
Thank you very much. You can talk to Ammar offline. Thank you very much, Ammar.
So I will stop my.
Yeah, thank you. Can I ask Paul, please?
Right. So this isn't quite a demo, but I do appreciate the invitation from Vishnu and from Thomas to present a little bit about the work that we've been doing. This is also not very technical in comparison to what I've heard for most of today. So maybe it's good that it's an end of the day session. Basically, I'm going to tell you a little bit about the partnership that we've had with ITU for the last 18 months or so. As most of you know, ITU have run a number of machine learning challenges, and we are helping to host those challenges so that they reach a broader audience, particularly in Africa, and we improve the sort of overall quality and volume of submissions. So I'm going to briefly go through Zindi, what Zindi is, just so that you have some sense of it. And the easiest way for me to tell you about Zindi is through a bit of a story about these two guys. This is Darius on the left and Nikhil on the right. They both joined Zindi several years ago, both in the very early stages of their career. I think Darius was working as a data, sort of working in data collection. He wanted to work in data science, but wasn't. And Nikhil was a student. They met on Zindi on the platform, and they took part in a machine learning challenge on Zindi to predict air quality in Kampala in Uganda for an organization called Airquo. They teamed up and they built a model that now allows Airquo to make 17 million annual predictions of air quality. The predictions are 24 hours in advance, and it's publicly, the predictions are publicly available, and they're using it to improve public health outcomes in Uganda. They're now rolling this model out to a number of other African cities as well. And this is relevant in Africa because unlike the developed world, there aren't a lot of air quality monitoring stations or sensors in African cities. This is, for me, an illustration of what a platform like Zindi can do. Darius was based in Nairobi. Nikhil was in Bangalore. I think they've never met in real life, but they teamed up and eventually they actually joined Airquo to implement their model. And incidentally, Darius now works for Zindi, so he impressed us that much. So Zindi now is a competition platform. It's open to anybody to join. We started in Africa, but we really are global now. We 70,000 users and growing, represented basically in every country in the world. We've given away, that number's now out of date. We've given away closer to $700,000 US in prize money, much of it to the developing world. And we've done this through more than 300 machine learning competitions. I'm going to move quickly through this, but the idea really is that we're a professional network for people building a career in data science and AI. But we see ourselves as a sort of a marketplace because we believe we can help companies and organizations solve complex data problems as well as source talent. And that's what we're building towards. So in terms of what organizations work with Zindi to do, it's a way to connect with this network of data and AI talent. We've got ambassador networks and we run events regularly. Our solutions produce, or rather our challenges produce really best-in-class machine learning solutions. And I'll tell you a bit more about that shortly. It's also a great way to find talent for your business or your organization. Yeah. And this is something we're working on quite carefully now. I won't talk about it today because it's not really relevant to this meeting, but we're working really hard to get our users placed in jobs around the world. So about our partnership with ITU, this started, I think, December 2022 or January 2023. We've run, I think, now 15 machine learning competitions, either wrapped up or busy running now. The competitions have had more than $50,000 in funding. That's when I say funding, that's prizes given to participants. So that's money that goes directly to our community. More than 3,000 users across the competitions. We've estimated something like 65,000 hours of work. That's based on how long we think it takes people to build a machine learning model and make a submission on Zindi. That's probably not that accurate, but it's in that region. Representatives from more than 100 countries and fantastic engagement from those representatives. Specifically in the network challenges, what we've called the AI and ML in 5G challenges, we've run 6 competitions. There's been $36,000 in prize money and more than 1,800 contributors. And Huawei has been very closely involved, although there are other partners as well. So I'm not going to go into too much detail. I'll give an example. Some of you in this room have obviously been involved in these, so you know. But these are the challenges we've run. Network traffic scenario prediction, quality of service prediction, energy consumption modeling, which was our biggest prize and our biggest participation, fault impact analysis. And right now we have sort of retrofitting or specializing large language models for use in telecommunications networks. And the next generation Wi-Fi throughput prediction as well. So just diving into a little more detail to show you what a challenge looks like on Zindi. This is what the challenge would look like. You can see almost 800 people involved and almost 300 people active in the competition, and the prize pool of 20,000 francs. The challenge itself, I am not that closely involved in running these challenges. We have a technical competitions team that puts these together in partnership with Thomas, as well as competition hosts on the ITU side. But this is a brief look at what the challenge was, what this challenge was. Participants are provided with a data set, and they are asked to develop a model to do specific things. That is then tested on Zindi. We keep a private test set. So they're given a subset of the data to build their model on, and then it's tested on a subset of the data that they don't have access to in order to get a prediction. So users get a score, they can team up, and then we review the winning models in much more detail. So the winning team was Aussie data scientists, and they, as well as quite a sizable prize pool, they got to present at COP28. And here, this is not Krishna, but he got to present his winning model there. So in terms of outcomes and the impact that this kind of work can have, excuse me, I've included some quotes. Nicola's here today. Hope you don't mind getting called out. But I think so we got some really nice feedback from our hosts. I mean, things like providing valuable insights, seeing relevant features and effective pre-processing techniques, and then, yeah, planning to further test and apply these insights. I also believe there's a continued collaboration with one of the winning teams, and there's been a research paper submitted. From the fault impact analysis challenge, we saw a 15% improvement in fault impact prediction, which I think is pretty awesome. Great insights into how Cat Boost and ensemble learning can be used together with accurate EDA to better predict impact of faults. Exploring related resource directions and interesting models. And then lastly, from the quality of service prediction challenge, some relevant learnings from the features selected, and also learned that certain topics didn't play as important a role as expected. And Rodrigo told us that 9 publications so far have used the data and models used in that competition. So to conclude, we've really had we've seen this as an extremely fruitful partnership with ITU. I'm really excited to say that the partnership continues, at least for the rest of this year. We'll have more challenges hosted on Zindi. It's not just in communication that networks that we've been working together. We also are working with the Geo AI group. We had a fusion challenge and 1 or 2 other challenges as well. But to conclude, I hope to see all of you participating in a ITU and Zindi challenge sometime in the future, and available for any questions or comments. Thanks.
Thanks for the presentation. I have a couple of questions.
Yeah.
So maybe first, do you have like an kind of an internal platform where people directly enter their code, their solutions, and it gets tested, kind of like an automated testing platform?
So right now, no. Right now, we have an internal evaluation system. People submit a file of submissions, and that is scored using one of a number of error metrics against our sort of model answers.
Then maybe the second thing is, having used a couple of these challenge platforms, HackerRank and the likes, there is a tendency that people tend to design their solutions by deducing the evaluation scenario. So I guess that happened also for you. So how do you try to mitigate that?
I wish my colleague Amy was here. She's led our competitions team for the last 5 years. She's seen every imaginable type of devious behavior. We have a number of ways of working around it. I think the best solution actually is that we have a sort of a general clause that if the models you submit aren't useful to the host or the client, you're immediately disqualified. So that it's kind of a good faith clause, right? Like you just don't behave badly. So that works quite well. But then, yeah, there are a number of techniques that we've learned basically through trial and error. We've learned because people have found ways around it, and then we take steps.
Okay.
You can send me an email if you'd like a more technical answer.
And maybe the last one's perhaps a little bit cheeky, but what is, I would say, a differentiator you see in your platform when you compare it to other kind of like global platforms like HackerRank and the likes?
Yeah, absolutely. I think it's an important question because this isn't anything especially novel that we're doing. What we've seen over the last 5 years is that there's a huge population of aspiring data scientists and engineers that are too intimidated to set foot on something like Kaggle. Or either that, or they feel that Kaggle doesn't post relevant challenges to them. And so we've really, in my mind, or to my view, cornered the market in Africa and the developing world. We have much smaller problems, much more locally relevant problems focused. The prize pools are smaller, and that may sound like a bad thing, but like Kaggle has $1 million competition on it. That's quite intimidating. And millions of data scientists. I think Zindi, we've got a welcoming community. We've got a place that people can actually learn from each other and grow. And we're really trying to lean into that now. Like we don't see that just being a competitive data science problem is a differentiator, as you've said. So we see ourselves as a community, as a talent platform, as a professional network.
So if I can add a couple of things, Abdul, for you, I think the interesting point has been to address first timers, the first timers who can come into the platform and solve these problems. We are not, I mean, these won't be $1 million prizes like what we say, but it lowers the barrier to onboard for the student or the scholar or whoever is that. Second thing is for the problem statements that we work on, I mean, for good or bad, we have not been able to fully automate, like you say. We have maybe some baseline solutions, which they are able to take and compare against. That's pretty much the automation. It's not like HackerRank. HackerRank has probably a lot more automation and algorithms than what we have for the problem statements that we work on. I mean, Zindi has other problem statements which probably has more automation. I'm not sure. Yeah, please.
Yeah. It's a good question. It's a made-up word. We stole it from 2 Swahili words. It roughly translates to winning and learning, or the idea of growing through learning, or success through learning. It very much depends. A lot of them are. We work with quite a wide range of organizations. So some organizations, for instance, we worked with RMB, Rand Merchant Bank, recently on a CPI nowcasting challenge. That was that model, those models, the winning models, are very much proprietary. They absolutely will not be sharing that with anyone because they came to us to build a better model that they can put into production. In other cases, we work with, say, Google DeepMind sponsors challenges on Zindi. They explicitly want those models open sourced. So we kind of run the gamut. So Zindi has a GitHub, any model that should be open source, or any model that we can open source, we do. So that's all on our GitHub, or it's on the GitHub of our partner organizations like CGIAR, Lacuna Fund, Radiant Earth, those sorts of organizations that are really trying to promote data set development and model development for development in Africa. A lot of those models are open source. In terms of the data sets, for any given competition, you need to get the data from somewhere, at least the test data. So you can sign up for Zindi, you can join a competition, and you can download the data from any competition that we've run.
Yeah. Thank you so much. Thank you, Paul.
Thanks.
Yeah. Can I make a call for mentors? So we are looking for mentors. So if anybody is interested in mentoring participants, please contact us. Thank you, Paul. Can I call upon Gideon, please? Should I present? Should I present? Should I display?
Yeah, you just
okay. Okay. Yes, last one which you sent me. Is that all right?
Sound
I just use that then.
Yeah, you can just tell me when to change everything. You can use that mic. Sorry? You don't have a copy? Oh, you can share it. It's fine. You can. Why don't you share it?
Hello. I'm Dabuye Gideon. So this is what you'd call an explanation of a solution that was given to one of the problems last year. The problem was called, the challenge was called multi-environment.
Okay. Okay. Yeah.
You started, then I'll be doing for you.
Yeah, sure. Yeah.
I'll just be using this one then. You just go.
Yeah, go ahead.
Okay. So yeah, multi-environment automotive QoS prediction. So basically predicting the quality of service that we have in a network that tries to get cars and users of the road communicate. So the core technology or idea here is the V2X, vehicle to everything communication. So this enables communication between the vehicles and other users of the road to communicate. So this is, the X can stand either for vehicles, infrastructure, network, or pedestrians. So by sharing information, so the ultimate aim is to improve the road usage and ultimately increase safety. So now, obviously, this sounds good, but for all this to make sense, we have to, because we're using communication, we have to make sure that the communication, the no latency, the communication is what you'd call zero latency or like reliable. So one of the easiest ways we can come up with is use machine learning to be able to predict the quality of service at any particular moment in these roads. So to start with this one, we have this data, the Berlin V2X data, that combines data that was collected. This is high resolution GPS data. So collected by using 4 cars in the course of 3 days. As you can see, this is the particular map, the coverage. So it included tiles, roughly a wide range of situations that you can get in the road. So another thing important about this data, it included 2 different operators. This is the network operators, so that we can kind of try to generalize, to get something that's generalized. So brief about the core contents in the data is we have cellular, the side link, position, and also side information. This is like traffic jam cover, cloud cover, temperature. So cellular, there's a lot of technical details for these kinds of data. So we have the physical layer, the signal to noise ratio, the RSSI, the signal strength, all that. So you can see the main thing to look at here is the sampling interval. They were kind of different, obviously, for obvious reasons. So the first thing that I did was to kind of put them into one in the same sampling interval, which is 1 second. So a quick visualization of the data and how I kind of came up to build the model was to first try to find which one should I use for training and evaluate so that the generalization should make sense in the end. So if you see, this is a volume plot of the 2 operators.
on the downlink and uplink data rates. So you can see uplink is kind of messy and doesn't cover a wider range than downlink. And the number of data points and the downlink was bigger than in uplink. So the operators, downlink was selected as to be the measure of the quality of service, and splitted the operators as train and test. So operator 1 was train, operator 2 was test. So these were kind of supposed to be, they're called operator 1 and operator 2 to cover the actual names of the network operators, for obvious reasons, obviously. So this is a quick structure of the solution that I came up with. The main idea is to cross-pollinate some capacity, some capability of one particular model with another. So basically, I'm talking about the algorithm boosting machine. This is LGBM, and an MLP, multi-layer perceptron. So an MLP is some kind of a neural network, obviously. So needs more data to kind of come up with a good prediction capacity or efficiency. So the first thing was to build a pipeline, which does the obvious stuff, removing the missing values, stuff like that. Then taking the operator 1 data, which I made to be the train, and train an LGBM model only to know which features make sense or kind of have more influence on the target, which is the downlink data rate. So then I get important features. So I didn't mention here, I think I have to now. Features were around 106. So if you have a lot of features, you obviously have latency to your prediction. So one of the main ideas was to have very, very small number of features as possible without sacrificing the accuracy. So yeah, so I got the important features. Then I could use the MLP to train on the minimum features and find a model. Why did I use MLP? Because apart from other good reasons, the main one that I considered is that MLP has the ability to learn, to have online learning. So when you have trained it with some particular number of data, when you have more data, you can just add them on and it will just update rather than retraining. Now, does this make sense for this kind of problem? Because we're dealing with, in considering the real world scenario, if a model is deployed doing the QoS prediction, you don't have to retrain the whole thing. It can just be uploading on the air. So that was the main idea. So I don't think I need to go much into that, the MLP in case. So this is like the breakdown of how it was. So I had to try also the training the MLP with the same 106 features to see how obviously bad it would predict. And so you can see the 68 seconds duration for training in roughly 25K samples. And LGBM obviously is quite fast, that's why it's called light. So it did the features in 3 seconds, and it had the 91, that's a good one. So MLP was 85, this is the R² score, which ranges from 0 to 1. So you can see we're almost to 1, the required number. So I use this particular method called the elbow method, which is mostly used in what you'd call unsupervised learning, if you're looking for a number of clusters. So this should tell you that this is like where you should try and select your number of clusters, right? So in this case, I plotted the feature selection graph that came out of the LGBM model. So you can see that where the point, the red line is where you can consider like most features, the next features have roughly the same contribution. So you either take them all or you drop them all. Try and error. So that makes sense. Though So this was 50. I took the 50, then it broke down to 9 features. So from 9 features, I went further in considering without giving any detailed information to the model, so that it's not good by data leakage. So I removed some other features like jitter was within the data. So I removed that, so I remained with 6. So you can see from 106 to 6, and I can see that okay, I didn't say about the phases. So, okay, phase 1 was the training LGBM with 106. So phase 1 MLP, 106 features. You can see the graphs there. So phase 2 MLP, this is without fine tuning, I should say. So it went above the phase 1 LGBM, obviously. Then with fine tuning, it went further. So you can see there's a significant difference and advantage from 106 features to just 6 features and more performance. So this was a good thing that I kind of saw that comes out of cross-pollinating capabilities of various architectures or models. So this is evaluation graphs, regression analysis, and the distribution plots for the actual and the predicted values. So you can see the close match. So for something like this, you just need more data to have something you can deploy immediately. Yeah, so although the data collection process from the paper of data collection, you can see it's a costly and time-consuming thing. So obviously, it's not a 1-week thing to do, or, you know. Yeah, so, but for this one, it's a good start. The evaluation went well. So I tried to compare other models off the shelf. Still, the MLP, the one that I came up with was good. You can see this is the mean absolute percentage error, range from 0 to 1. The lower, the better. So this is very good. You can see that. Also, others in the R square score, still good. So yeah. So this was just some discussion on what best can be done. Obviously, the missing values, more data, time also, but is an indication for a good start of this kind of approach. 6 features, 94% with like a very small latency. And that's for training. So if you're just inferencing, you're getting few samples in a second. So it's just roughly 0, just, you know. So I think that's it. So this was a certificate from ITU. Thank you. Yeah.
Yeah, thanks. This was very insightful. Thanks a lot for the information. Maybe I have a couple of questions. So when you finalized the feature extraction, you ended up with these 6 features.
Yeah.
Did you notice that from a physical meaning of the features, it made sense that a domain expert could have selected these features from the beginning without doing the elbow method or the feature minimization? So just by looking at the different measurements.
No and yes. So an expert would actually think of, okay, I can't leave that one. I can take these, but it's just hard to dump some features. So I could say yes and no if he's actually intending to have less features. But if just considering his expertise and what he knows about the features, he would end up on 30s or 40s, somewhere there. Yeah.
So up to a certain point, you really need to do it mathematically.
Yeah, you just have to
get the impact.
Yeah.
Okay.
Yeah.
And the second question is, did you try to cluster the data at the beginning based on trends, like perhaps looking at classic time series prediction methods like Bayesian or ARIMA models, some form of trends?
No.
Like time of day would affect maybe different models for different times of day.
Yeah, considering the duration was just 3 days, and that was just like almost the weekend.
Yeah, makes sense. Yeah.
So it was useless.
Yeah,
you kind of biased. You get biased answers.
Yeah.
Yeah.
Yeah. Thanks.
when you compare with the other models, are you using the 6 inputs in there?
Yeah. Yeah.
Very good.
Any other?
Okay, thank you very much, William. Okay, so if no other questions, will Anthony? Yeah, please.
See if it work. Okay. Okay. So this is a demo I presented in a MWC this year. So I wanted to share with you, and we can discuss it a bit later about. So it's about digital twin. I think today we discuss about this technology, and obviously it's very important for us as well. I can tell you that Huawei spend a very large amount of money every year with drive test to collect data characterizing our networks and to enable then network optimization. And obviously we think that digital twin empowered by AI and other technology can be a way to reduce this cost and provide even further optimization, especially because there is some kind of loop, closed loop optimization that is allowed by digital twin that you cannot do only by collecting measurement in a given environment, then maybe optimize the network and then afterward collect again the data, because obviously this is limited, and also you have I mean, drive test is only for a specific area outdoor and so on. I mean, there are many limitations. So here what we wanted to do is first of all we develop a specific technology to collect different type of measurements that are typically used in through drive test, not only MR, not only maybe also cell level data, engineering parameters, but actually LiDAR data, which could be collected through the car going on. I think you can see it. Well, I will show you. This LiDAR data is basically used to reconstruct the environment and embedded in an AI model here. At the time, we were mainly looking with NERF. I think Jakob talked about NERF in one of his slides. Today, we are looking also at different, more efficient, like say, computational efficient model like Gaussian splatting. Here you can see that for NERF, we had to work a lot on reducing the complexity to make this feasible actually from a solution perspective. So basically the idea here is that to use all this type of data to reconstruct the environment, and actually after that, understanding the radio propagation characteristic of this environment, thanks to the AI, to understand how the network signal propagates in this environment, and then do optimization on top of it. And I have a couple of examples of this, let's say, use case for this kind of technology. You can see here on the left side, basically you have an area here, two areas actually, which are red zone. So the coverage is pretty limited here. And typically one way of resolving the problem would be to put on top of this building here, maybe a new base station, which obviously has some cost. With, let's say, with this digital twin, what we could understand is that actually there are some reflection properties of this building here that could be exploited. And by using some remote control of our antennas that today can control both azimuth and tilt remotely by using AI actually, we can swap the antenna toward the direction of this building, or maybe create another beam and resolve this problem. So this kind of solution has been tested in the digital twin, allowed to increase 2 to 3 times the edge rate of the user, the downlink rate. Another use case which for us is interesting is this energy efficiency use case. So you can see that during the day, obviously there is traffic going around in the network. In particular, you need to serve user maybe going to the office and so on. So you have a base station specifically deployed around railways. But during the night, user move, go home, etc. So the capacity requirement of the network decrease in a given area. So you can start to switch off some of the base station and actually exploit nearby base station to provide coverage. So capacity is reduced, but coverage is not affected. And if I remember well here, there are around 20% of energy saving gain. Yes. What I want to say, so another thing here, so regarding this technology, let's say that the hardware technology that allow us to design, I mean, deploy this digital twin is it's something, it's already a product actually that we can integrate in different, let's say, equipment, could be cars, drones, etc. From, let's say, the digital twin perspective, the AI part is still, let's say, we are still researching, in the sense that, as I said before, NERF was initial solution, then we moved to Gaussian splatting and so on. So there is still room for improvement. Yep. So this is from my side. If you have any question, I'm happy to discuss about that. Thank you. Well, yeah.
Yes, Zoran, please.
So it's also a source that can be used, yes. But no, it's not always available everywhere. And so one goal here, it could be also was to use a technology, design a technology that could allow us to refresh let's say, our understanding of the environment. Not only using a 3D map that you can buy on the internet and so on. Okay, so I think, let me see. We should be able to. Okay, there was a car here walking around and showing that we can collect data about this, using this. I think, yeah, I think there was a colleague there. Sorry? What is NERF? So NERF is a technology that has been, I mean, it's very popular in computer vision. And yeah, basically to reconstruct the environment for car, autonomous driving and so on. Basically, with this NERF technology, you can use the light's propagation effect when lights hits obstacles and so on to reconstruct the environment. And here, instead of using to work on light, we were using on RF signals. But let's say that the technology is the same.
Did you use any open source based digital twin framework, or this was done as part of the program from scratch?
I mean, this is part of our products design and research and so on. Yeah. I think there was another colleague for, yeah.
Yeah, it's a bit about the time scale that this allows you to work with. So if you can add something. Because I guess that this is quite computationally expensive.
Yes, definitely. So this is more an offline, let's say, from our perspective, especially what we look for in our department are mainly offline solution, okay, that allow us to optimize the network, but it's not something running on real time and so on. It would be too expensive, obviously. I mean, this is a product designed to optimize thousands of base stations in a big city, basically. So yeah, yes.
Thank you very much for the demo. It's really impressive. I had a sort of like maybe similar question.
Yes.
So for once you reconstruct the 3D geometry from, you know, like the data lake that you mentioned using the NERV.
Yes.
For actually working on a digital, you know, like on your analytical level to kind of work with your 3D geometry, for example, the render you are using in your slides. Are you using any game engine like Unreal 4, Unreal 5 or Unity, or did you use something like Cesium, or is it just rendered in an OpenGL or something like that?
So for this the level of detail I cannot say.
You don't know.
Yeah, because it's not me that I've designed that part of the architecture. Yeah,
I was just curious.
No, but I can if you drop me an email, I can. Okay.
Colleagues, thank you very much. We would like to. I mean, we understand that you all want to discuss with Antonio, but let's try to close for today. Thank you very much.